Wow, preparing is very
Okay.
slow.
We are live on YouTube.
Okay.
Yeah, I think
the programming environment is very slow.
Do you want to share the link on our Slack channel as well for explicit Zoom link for people to join?
Yeah, so it's the programming environment is very slow. Yeah, it's on.
Yeah, it's working. Yes.
We're streaming, Pramod, by the way, and you're sharing your screen. So.
Okay, sorry.
Okay, we can cut the first part. We can cut it later, so no problem. Anything that we say now, it's live, but worst case, we can cut it later. So no.
Yeah, but I mean, if people are already on YouTube, maybe don't show your emails. Or...
Yeah, that's true.
They're full of trash, anyways.
I think they get access 10 minutes before, right? So I think don't reveal award winners or anything like that.
Yeah. Also.
Actually, I committed the award certificates on our website, and then I realized that our EuroSys GitHub page is public. So if someone go and check in the commit logs, they can find out the certificates. Yeah, I didn't want to rebase the GitHub. So yeah.
But this being said, we do have all the award winners accounted for. They will join, right, to say a couple of words. That was the plan, right?
Yes, I think I got an acknowledgement from the folks. Yeah.
All right.
So we just passed 1,600 registration.
Oh, congrats.
Amazing.
Wow.
That's crazy. Yeah.
That's crazy. Really.
Fantastic.
1,700 even on Slack.
No, I think Slack actually has a lot of volunteers who participated in AMA. It's not AMA, sorry. Artifact evaluation.
Oh, okay.
Yeah, so Slack was used for artifact evaluation coordination and also for Shadow PC, I believe. So this is why you have more people there.
For Shadow PC, no, we weren't on the Slack.
So the AMA session with Andy yesterday was fun. The story of his joining the university was, I didn't know about that story, but it was fun. Yeah.
I'd only heard it about 50 times.
So we should start seeing the participants now, I guess, because
in 1 minute, I think.
Can we paste the Zoom link also publicly in the, at least in the Slack channel?
Yes, I can do that.
Mm-hmm.
So some people join via Zoom, some via YouTube, right?
Yeah.
Yes, we have more than, I mean, the number of actually people that are connecting to YouTube is increasing.
What's the capacity for Zoom?
1,000.
1,000.
Mm-hmm.
Anyone else that want to do some test? No.
If not, then I suggest we mute all of us, I guess.
Okay, that's good. Pramod, do you want to play the video, or we can?
Yeah, I think we can leave it, I guess. Yeah, I don't want to goof up my screen setup.
No, it's okay. I mean, I think maybe Matthias or I can play the video.
Okay, then I have to give away my screen, I guess. Yeah. Okay. Yeah, it would be nice to be in Edinburgh right now. How is the weather there?
Well, I mean, I can show you, but I don't know how much you can see. But yeah, it's raining. Yeah. It's raining. Actually, it was sunny since a very long time, and I mean, I would say not cold because saying warm maybe is a little bit too much, especially coming from Italy. Yeah, this morning I wake up with the rain. It's okay. I like it, to be honest. But it was a little bit unexpected because I remember previous year, May was particularly hot. I mean, warm, I would say. So we are going through May. I mean, it's like last few days of April. So I was thinking, yeah, maybe summer is really here, but apparently no.
Usually last week of April is very good in Edinburgh, actually. I don't know, this is exception.
I think it could have been super good to be here, especially with what we had organized at the beginning. Yeah, unfortunately, guys. The number of attendees is increasing, so someone logging with ACM EuroSys 2021. No. Okay, guys.
Yeah, I don't know who that is, but
yeah, let's write on the volunteer. So maybe if you want, in this 5 minutes, you can play the video that Pramod sent you on the Slack. If at least if there are no questions from the other panelists or test.
Matthias, do I let you do that, or?
Can do that, yeah, sure.
I mean, the person with the ACM credential is not going anywhere from attendees anyway, so.
I removed him. I removed him or her. I removed because yeah, okay. Otherwise they don't go anywhere.
Yeah, I mean, yeah, they would just as an attendee.
Yeah.
So did someone promoted Luis also in the session, I would say, because he's the session chair immediately afterwards? Okay, wait, I promote him. We have one of the award winners right now. Oh, not this one, maybe you can play this.
Other one?
No, it's okay. We can play the Edinburgh.
The sound, that's lower volume there.
This one?
At a lower volume, maybe, if you can.
Yeah, also the music is relaxing. We have Victor actually. So Marius,
Should I start sharing?
No, go ahead. Go ahead. I was just saying that we have the awardees. So yeah.
Sorry.
But, yeah.
It's lower volume.
Please lower the volume just a little bit.
Can you lower the volume on the video, not on your speakers, because the speaker volume on your doesn't change the Zoom volume.
Yeah, the volume from YouTube. Yeah, great.
We can stop it. I can share the screen now, I guess. Yeah,
You still have 4 minutes before.
yeah, that's okay.
Thanks.
I think people are. Yes, it's okay.
Pramod, I need around 3 minutes 30 seconds, not more than that.
Okay.
For my part. Lorenzo, what time is it? What time is it for you?
4:58.
So did you do it through, or did you sleep and then did you wake up?
No, I slept. I was sleeping with half an eye, and at 4 I was basically awake. So I said I'll just get out of bed.
Well, very tough, really. Thank you for doing that.
Of course. Thank you guys. You've done an amazing job.
Oh, thank you.
Yes, I concur. It's
Yeah, I appreciate that.
Amazing. I want to see the 1,600 participants though, since I woke up at 4. I want to see all of them.
Okay, someone is raising hand. Who's raising hand? Petros Menites.
Oh, Petros.
Petros,
Yeah,
do you
he
want to speak?
he just had a question in the chat, I think. He asked
Okay,
if the video
Petros,
should
do
be
you want to speak?
Hi, everyone.
Yeah.
Can
Hi.
you hear me okay?
Yes, we can hear you.
Okay, I'm just checking because I don't see any of the attendees' video. I don't know if it was configured to be one way.
You can't see the attendees' names or videos.
Actually, I can't see anything. All I can see is the EuroSys presentation screen.
Yeah, that is all. We are waiting for it to start, I guess, in a few minutes, I would say. So we can start actually.
All right, just checking that I'm not missing something. Okay, thanks.
Okay.
Now, also, if you see also on YouTube, there is, for example, in this moment, I mean, I can see it not live, but after a couple of seconds, you can see Pramod or me or the person that is speaking. Okay. Anyway, it's 10.
So should we start, I guess?
I think so.
Okay, great. So welcome everyone, wherever you are. Thanks for joining in for the welcome ceremony of EuroSys 2021. And it is our pleasure to actually welcome you in this conference. So myself, Pramod Patodia, and along with my colleague, Antonio Bablas. So I'm a professor of computer science at the Technical University of Munich and the University of Edinburgh, and Antonio, who is a faculty member at the University of Edinburgh. We, as a general chairs, would like to welcome you to the conference here. So as you remember, last year during EuroSys 2020, we promised you that we will take you to Edinburgh, and our promise was not fulfilled, unfortunately, due to COVID, where we actually went through a lot of work in organizing everything for physical conference. And unfortunately, because of these unplanned circumstances, we need to change everything. So we are happy that we are now holding the conference, but in the virtual world. So as you can see that our dolly shape is now, will be organizing this conference through a set of virtual tools. And in the next slide, I would actually help you understand our arrangement. So we are primarily relying on 4 online tools for running the conference. The first and foremost is SCED. So SCED is our central platform for managing all information. So if you can go to this link as EuroSys21sced.com, you will find all the information regarding the sessions, session chairs, Slack channel, how to find Zoom link, and all other events that we have planned are in SCED. So we highly encourage you to actually go in SCED to find out all the information. Please note that you will only see the Zoom link when you register for an event. So if you have to actually explicitly say that I want to attend this particular session, and then the Zoom link will appear 10 minutes before the session start. As you can see that we are using Zoom for video conferencing or streaming service, and we have license for only 1,000 people. And that's why we are using also YouTube for scalability reasons. For the safety of the conference, we have decided that we will operate conference or Zoom in the webinar mode, which means that we will not allow synchronous communication for all participants, but we will only allow synchronous communication between panelists, between the session chairs and the conference speakers. The rest of them have to use Slack, which is our last tool. So Slack is used for all sort of communication. So you can ask questions, you can have other networking opportunities out there. Please find appropriate channels. We have designated channels for asking questions, and you can find this information again in SCED. So while organizing this conference, we actually have worked really hard to make sure 2 important things in virtual world. First of all, we are able to keep the conference registration fully free, and it will, thanks to our sponsors, generous support. So we are able to have 100% free registration fees. And secondly, the conference is also sort of scheduled to suit different time zones. So we have day 1, which is the first day of the conference. Today is a sort of Asia-friendly time zone and intersecting with the EU time zone as well. And tomorrow we will shift our schedule slightly late so that we can actually align ourselves with the folks in the North American continent. So a few words on our team or our participation. So we are very, very happy that we are able to actually accommodate a large number of people in this conference. So we have more than 1,600 registrations so far. And just to emphasize the point that we don't have fake registrations so-called in these 1,600, because we have gone through the list carefully and try to prune out people who are actually somehow trying to abuse the system. But it's mostly reflects our systems community, and we are very proud of what we have achieved in attracting so many people. And this is an artifact of our free registration program. So I would not bore you with a lot of breakdown of how the participation looks like here, but just to emphasize few good things and a few things that we need to reflect as a community on how to improve things going forward. So as you can see that we have a large participation from our European systems community. So it forms the bulk here with 49%. And the second good thing that we are seeing here is the number of students that are participating in this conference. So we have 46%. I mean, this is the landmark of our community that we always encourage students to participate. And we are seeing very good numbers there for student participation. Unfortunately, something that we as a community need to worry about is the female participation here. And this is reflected in very low numbers here with only 13%. So this is something that we should also discuss in General Assembly going forward. But overall, we are very happy that we are having a record participation in EuroSys this year. Going forward to the program, we have our conference proceedings ready online. You can check out the proceedings by going on this URL, eurosys2021.org proceedings. And this is the hard work that is done by our program chairs and program committee members to produce a phenomenal program. And in this overview, just I want to highlight two things that we were able to achieve in this year. The first one is the revision stage. That is something new that we have adopted from the database and community, and program chairs will talk about this in more in detail later on. And the second thing that we are also very proud here is that we were able to introduce artifact evaluation in a record time. And this was the hard work that was done by our artifact evaluation committee chairs as well as our team, who actually were able to incorporate both of these new features in EuroSys, and we hope that this will continue in the subsequent editions. Next, I would give it to my colleague, Antonio Babalas, who will talk about a few more editions that we have in program.
Okay, thanks Pramod for the introduction. So the program this year features a few new additions compared with the version of EuroSys. We have a total of 5 Ask Me Anything sessions with well-recognized members of our community, including Andrew Tannenbaum and Anne-Marie Kermerak, which already ran yesterday, Willy Zwenapol today, and Ejit Attia and Peter Ducher tomorrow. We have several awards, and amongst others, this year we are delighted to offer the Best Paper Award sponsored by ACM Europe Council and ACM Europe SIS chapter, which will be presented soon by the ACM president. Finally, we have All-Way Tracks, which many of you may have tried already. We did our best to organize them in a way that avoids the use of any additional software tools other than the one that Pramod presented already. So next, with an effort of helping everyone to find their own way among the different software tools, we compiled the guide that explains how each of them should be used for the best experience. And this can be easily found at eurosys2021.org/guide. So next. We value your experience. Therefore, EuroSys supports freedom of thought and the open exchange of ideas. You can read our code of conduct at eurosys2021.org/conduct. Moreover, EuroSys is dedicated to providing an harassment-free conference experience and abides to the ACM policy against discrimination and harassment and ACM Code of Ethics. To strengthen that, we organize the Slack channel and a daily office hours, the details are on Slack, on SCAD, for the SIGOPS committee to aid reporting on discrimination and harassment policy violation, CARES. Micho and Dilma are available to talk with you about that. So next slide. Other than this, please remember that for anything you may need, for any help, the volunteers and the organizers are here to help, and we are reachable at any time on Slack and on the volunteer channel, or by email at organizer-2021@eurosys.org. Next. Before starting the conference, I need to thank all the EuroSys sponsors for this year, including Huawei, Microsoft, VMware, Apple, Google, Facebook, Red Hat, ARM, Cisco, Intel, Oracle, Mate1, and Coldplay. Each of the sponsors has a Slack channel for advertisement or recruitment, while Diamond and Gold sponsors have also a Zoom room. You can find details in Slack itself or on SCAD. Also, let me mention that for this year, ACM EuroSys is running in cooperation with Userix. So the last slide is about people that help, right? So it was impossible to organize the conference without the support of our sponsors, but also without the help of multiple people. Most of them in this picture, including PC chairs, workshop chairs, officers, and award chairs. But also our awesome volunteers that are helping behind the curtains to make sure that everything runs smoothly. A big thanks to all of you. So next, this concludes our message. I will let the stage to the PC chairs, Lorenzo Alvisi from Cornell and Christian Kader from Imperial College London.
Thank you very much, Antonio and Pramod, for the great organization of the conference. I'm Christian Kader from Imperial College London. I'm joined by Lorenzo Alvisi from Cornell University as program chairs. So first of all, Lorenzo and I would like to also welcome you to EuroSys 2021. We have an exciting technical program coming up. So first, I'm going to tell you a little bit about what it has taken to assemble this great program. So we started with 191 submissions. 10 of them were either withdrawn or rejected. So we're left with 181 valid submissions. So each of these submissions received 3 reviews in the first round. And at the end of the first round, we rejected 66, which didn't have enough support. So this left us with 115 submissions going into the second round, where they received between 3 and 5 additional reviews. And then after some online discussions, we rejected a further 57 of them. So we're left with 58 papers that went to a PC meeting. We had a 2-day PC meeting online because of the pandemic. And we had 3 outcomes at the PC meeting. So one of them was accept, right? So 27 were directly accepted, 18 were rejected, and a further 13 went through this revision stage that Pramod has already mentioned, and I'll give more details shortly. And out of these 13 papers, 11 were accepted and 2 were rejected. So our acceptance rate overall was 21%. Now, this rigorous process, of course, would not have been possible without our fantastic program committee, which had 63 members, excluding the chairs, grouped into 22 heavy PC members and 41 light PC members. And together they produced an amazing number of 880 insightful reviews, and they also shepherded every single accepted paper. So now let me tell you a bit more about the revision stage, which was something new from EuroSys, but we were inspired by other conferences, particularly from databases and programming languages. And here I'm quoting from the call for papers, right? So we decided to request revisions only in constructive scenarios. This is a very specific request. And here you have like some examples of such requests, such as justify a crucial assumption or compare against some relevant previous system. And in particular, we decided not to request revisions, to address lack of technical depth or novelty, or where the revised paper will end up being completely different from the paper that was initially submitted. Now, we believe that this was highly successful, and we recommend it for other conferences and, of course, for future editions of EuroSys. And we base this on the fact that our reviewers praised the revision stages, leading to significantly better papers in most cases. And in fact, one of our of the 2 best paper awards for the conference was given to a paper that went through the revision stage. So we think this process has saved strong papers, which broadly met the acceptance criteria, except in some particular aspects, which were in most cases handled via the revision stage. And overall, we think this can help unnecessary resubmissions, thus decreasing the overall reviewing load in the community. So the final thing that I want to tell you is that we are very pleased, as Pramod also said, that all accepted papers were given the opportunity to participate in the artifact evaluation process, something that has been used successfully at other conferences already. And we think that's important because this encourages open science by promoting reproducibility. And it was great to see that in this first offering of the Artifact Evaluation Committee, 22 out of the 38 papers submitted artifacts, and more information will be given in the General Assembly. So now I'm going to pass it to Lorenzo, who's going to give you more stats about our submissions and accepted papers.
Thank you, Christian, and good morning, everyone. Yes, I'll just give you some traditional statistics that one gives at this point about the distribution and some other data about the papers that have been accepted. First of all, as Christian said, we have accepted 38 papers, 235 authors are behind them. And as you can see, ours is a very collaborative community. Papers tend to have a median of 5 authors, but you can see that we are moving towards becoming a real science because at least some of the papers are starting to approach the kind of the number of authors that you see in experimental physics. We have a paper with 22 authors and several papers that have 10 or more authors. Next. One of the things that is classically we are interested in is the separation, the distribution between academic and industrial contribution. And you can see that although the number of authors in industry is about 1/4 of the total, so this conference is clearly rooted in academia. When it comes to the number of papers that are accepted, about 44% of the papers, 17 out of the total, have an industrial presence. In most of them, it looks like industrial partners served as the kind of spice that make the soup particularly good. You see how many papers had an industrial, at least co-author. Yes, next. Geographic diversity, we are still short of being able to engage Antarctica, but except for that, we have succeeded with having participation from the other continents. The representation, as you can see, per country is, there is a strong representation from the United States and China, and then down it goes. Antonio and I are the representation from Italy. Now, one thing that Pramod already mentioned is the other, a very important projection of diversity, which is gender diversity. We don't pretend, we appreciate that gender diversity is significantly more nuanced that can be captured in a slide, but we hope that this slide at least provides some degree of signal. As you can see, there is much more that we can do in terms of having a more diverse set of authors and a more diverse set of participants in our community. And we hope that data like this will inform our discussion. Finally, I thought that it would be interesting to give you a sense of how successful were papers that classified themselves under different titles, areas when they were submitted their work. You can see that we are centered around, distributed and cloud are certainly the most popular areas that our work happens to be in. ML is growing. And you also see that if you wanted your paper to get in, and I can guarantee you that Christian had nothing to do with it, working in language support and runtime system was a good idea this year. Mobile computing didn't work so well, but as they say for my favorite soccer team, there is always next year. And speaking about papers that have been accepted, is my great pleasure to pass the baton next to Gabriele Cozzis, that is going to tell us about the paper that are winning our Best Paper Awards this year.
Thank you very much. It is my pleasure to present 2 Best Paper Awards. The first one is sponsored by the ACM Europe Council and the second one by ACM SIGOPS in Europe. ACM Europe Council was founded several years ago with the idea and objective to promote the visibility, but also the activities and services that ACM does in Europe. And one of those activities would be giving a Best Paper Award to selected ACM conferences held in Europe. The papers for both awards have been chosen by the PC, and the winners will receive quite a nice amount of money to sponsor future of their research activities, and also a plaque, respectively a certificate. Let me continue now with disclosing who the winners are. And before I tell you who was winning the ACM Europe Council Best Paper Award, I would like to present to you some of the comments that have been given to this paper, why we have selected the paper. So the paper is addressing a significant and challenging problem that is relevant to the EuroSys community. I'm not going to read all of this. What I liked most was that there were simple, refreshing ideas presented in a way that are easy to understand and also fun to think about. So with that, please join me in a big applause for the winners of this award, which goes to the paper PASH, Light Touch Data Parallel Shell Processing, and the authors are Nicholas Vasilakis, Konstantinos Kallas, Konstantinos Mamouras, Achilles Benetopoulos, and Lazar Zvetkovic. Congratulations, and I think Nikos and Konstantinos, you're here, so you will hear our applause. Let me now move on to the EuroSys 2021 ACM SIGOPS in Europe Best Paper Award. And again, I will start with reading a few lines from the comments that we received why this paper has been chosen. The ability to deploy existing unmodified POSIX applications in a unikernel is very impressive. It's a big step towards realizing the unikernel dream of democratizing the LiveOS model for wider usage among application developers. And this is also something that I would like to personally emphasize, I'll be pointing my students at this paper for latest and greatest in-library operating system advancement and system research. And this award goes to a large group of authors. It's not the record, but it's 12 authors. Simon Künzer, Vlad-André Badoyo, Hugo Lefevre, Sharan Santanam, Alexander Jung, Gaultier Gain, Cyril Soldani, Costin Lupu, Stefan Teodorescu, Costi Radonaccio, Christian Bano, Laurent Matti, Razvan Diaconescu, Costin Raicciu, and Felipe Huici. And congratulations also to this team of authors for the paper Unicraft, Fast Specialized Unikernels the Easy Way. I encourage all the participants to look out in the program for these two papers that have been selected for the Best Paper Award. I'm sure this will not only be best papers, but also inspiring talks. Thank you very much and enjoy the conference.
Thanks very much. With that, we will thanks the ACM president for coming in and presenting these awards for us. Thank you very much. So we have Peter next.
Yes, thank you very much. So my name is Peter Pizzo from Imperial College London, and I'm currently the chair of the ACM EuroSys chapter. And it's my great pleasure to announce the 10-year Test of Time Award that we give out each year. So the process for this award is that the EuroSys steering committee looks over papers that were published 10 years ago at EuroSys 2011. And we consider the most cited papers and then think about the impact that they had. And based on that, we then decide who should win the award. So when we looked at the EuroSys 2011 papers, there was one paper that really stood out. It had a much larger number of citations, and I think it is a very worthy recipient for this award. So without further ado, the award goes to Clone Cloud, Elastic Execution Between Mobile Device and Cloud. And the authors are Gonchun, Sungwon Im, Petros Maniatis, Meyer Naik, and Ashwin Patti. So congratulations. I think Petros and Gon are also here. Congratulations. So this paper was quite influential in terms of proposing an opportunistic offloading model to run computation from a mobile device in a cloud environment. And it led to a lot of follow-on work, a lot of interest in this kind of execution model. And also with current edge computing models, I think this work is more relevant than ever. So well done and congratulations again. And with this, I would like to pass the word on to John Crowcroft, who will announce the Roger Needham PhD Award. Thank you.
Yes, thank you. Hi, everyone. So it was my pleasure to chair the Roger Needham PhD Award Committee. we had a lot of work to do because Europe is doing a lot of very good systems work, and we had 16 dissertations that we had to get through. The committee has 10 members. It's very global. It's not just European members of the committee, it's people from south of the equator and North America and other parts of the world. We had a 2-phase process. We scanned through the dissertations and the submission overview. Everyone had a kind of a favorite few. We shortlisted, and then we actually read through everything. And we should move on a slide so I can announce the winner of this year's is Victor van der Veen from the Vrije Universiteit. I cannot pronounce that, excuse my Dutch. And the thesis titled When Memory Serves Not So Well, Memory Errors 30 Years Later. This is a beautifully written piece of work. I recommend everyone rush off and read it if you haven't read some of the papers from it. And we also decided that there should be an honorable mention. If we could have more, we would have had more, but the EuroSys, I think, tends to have a winner and an honorable mention, and that went to Marius Kogias from École Polytechnique Fédérale de Lausanne, and that was the operating system network co-design for latency critical data center applications. And Victor and Marius are online. I don't know if they'd like to say a couple of words. Victor, maybe, if you wish.
Yes, well, yeah, so of course I didn't prepare anything. I just want to maybe spend a minute on just thanking everybody. So I would like to thank the committee for granting me the award. I'd like to thank Herbert and Cristiano from Vrije Universiteit Amsterdam for helping out submitting the thesis, but also helping out in the process of delivering the thesis and helping with all the writing of the papers. I'd like to thank all my co-authors. I'd like to thank my family and my friends and all the reviewers, of course.
Cool. And Marius, do you want to say anything?
Yeah, thank you very much. I would also like to thank the committee for granting me this award, and also the SICOPS the chapter, and also my advisor at Buñol at TPFL, which was very helpful throughout the course of my thesis. Thanks.
Great. Thank you very much. And I should really say, you know, this was a really tough competition. There were a lot of really good dissertations submitted. It was I read every one of them, and believe me, it was fun. Actually, very interesting. I learned a lot. Thank you for your great work and all the others. Okay.
Thanks very much, John. So we will hand over next to Herbert Bose, who actually will be presenting Jochen Littke Young Research Award.
Okay, so due to circumstances, this is actually the third time I'm on this committee, and I'm not normally a fan of extra work, but I'm very happy to hand out the award this year because I am a fan of the winner's work. I'd like to say that the other people on the committee were Manuel Costa and Christian Kadar, and the 2021 edition of the Jochen Littke Young Researcher Award had 6 strong candidates, and there is probably more than one candidate that would deserve the award. Nevertheless, the award committee this year was unanimous in its choice for the winner, who is an all-round systems researcher with accomplishments in various areas where he published influential work with tremendous impact, not just on academia, but also on the real world. He is the past president of the FreeBSD Foundation and the co-author of the book on the FreeBSD operating system. He's published papers in top venues in the domains of operating system security, programming, hardware, networking, and so on, and won best papers in many of these tier 1 venues. But what's interesting is that one of his earliest papers is the paper on FreeBSD jails, which I absolutely love. This is a paper that was on isolating programs in a Unix system, and it was published at a really minor venue. But nevertheless, it's become this really influential paper. Anyway, so perhaps his most impressive and important work is that on capabilities, first in Capsicum, and later in the Cherry project, which offers hardware enforced capabilities that guarantee strong spatial and temporal memory safety. And now funded by the UK government and various industrial partners such as ARM, Cherry is not just research anymore, but it's leading to a workstation-grade ARM-based chip and board for commercial and academic evaluation. As the committee, we could think of no candidate more suitable and more deserving to win this award. So the 2021 Jochen Liedtke Young Researcher Award this year goes to Robert Watson of the University of Cambridge. Congratulations. And maybe Robert would like to say a few words also.
Thank you very much. So thank you to the committee and to the conference for the award. I'm truly honored, a bit surprised to receive. I should also thank my spouse, Lee Dano, for her support. I do want to thank, especially though, my mentors and colleagues and my co-investigators, especially Pete Neumann, Simon Moore, and Peter Sewell, my colleagues, my research staff, and my students, not just for their support, but also the contributions to the research. This would not have been possible without them. It has been quite an amazing decade. Every day we sit down as a research team, we work in microarchitecture, in operating systems, in compilers, in formal modeling and proof. It is a great joy to work with these people, and they're amazingly talented. 10 years ago, we imagined a research project centered on hardware, software, theory, co-design, tightly integrating a team across all of those disciplines. And I think it was, I think we were all optimistic and hopeful, as one is at the start of a piece of blue sky research, but I don't think any of us imagined that ARM will be shipping a processor and a system on chip in 2021 based on our work on Cherry. So thank you again for this award. I greatly appreciate it. I also look forward to the rest of the conference. It looks like a very exciting set of papers. Thank you.
Congratulations again.
Congratulations, and that concludes our welcome opening ceremony, and we will move to the session 1 right now. So that's, thank you very much. Enjoy the conference. Right.
Okay, I'm not sure if I'm on screen or not, though.
Yes, you are on screen.
Yes,
right now.
okay, awesome.
So great. So we will hand over to you, and Matthias Hille as well as Vedha will be the volunteers for this session. And
okay,
great. In the meantime, I believe all authors are also in for that.
We can also take a picture before screenshot before that.
Okay.
Yeah, if everyone opens their
camera,
also for the awards, we take a screenshot very quickly and then we go ahead. Yeah, but the award
it's okay. I think many of them left. I guess I think many of them left. It's okay, so that's fine. I suggest. Or do we have the people here?
Yes.
Yeah, I'm not seeing the award winners, but I'm seeing the session 1 folks. So that's okay. Okay, so let's move on because we are all on time ahead. I'll just hand over to Luis, and who will be the session chair. Luis, take it over. Thank you.
Thanks very much, Pramod. So, okay, welcome everyone to this our first session of EuroSys 2021, and thanks for attending. In this session, we are going to see 6 great papers on operating systems, language support, and security. And oh, by the way, I forgot to present myself. I'm Luis Vilanova from Imperial College London. So with further ado, let's switch over to the first paper, which is going to be with the title Mitigating Vulnerability Windows with Hypervisor Transplant. And this paper is going to be presented by Chu Ding, who's a PhD student in the Edith Sepia group at the University of Toulouse in France. And his research interests mainly include operating system and virtualization techniques, with some forays into security and performance evaluations. So please go ahead with the presentation. Thank you.
May I ask everyone to switch off their videos for the when the videos are played? Thank you.
Me too, and thank you for being here with me today. Today I would like to present our recent work, which is HyperTP, a solution for reducing the vulnerability window of hypervisors by replacing one kind of hypervisor with a completely different one. So first, one thing about large data centers is that you cannot afford to bring down whole system. So most of the time you need to perform live migration to upgrade your hypervisors. And as you can imagine, this method uses a lot of computing resources and bandwidth, and in fact can be very slow. So Alibaba, for example, reports needing 15 days just to patch one cluster in the public cloud. And this time window is long enough for attackers to exploit and break into your system. That's why the main idea of our work here is to move a running VM from one hypervisor to another. for example, from Zen to KVM, and we call that hypervisor transplant or hyper-TP. Our idea here is that we have a large pool of different hypervisors, and by switching between them, we'll be able to adapt our attack surface to any emerging vulnerabilities. And hyper-TP is also helpful for data center operators because they're no longer locked to one single hypervisor, and we'll be able to choose between multiple of them without having to worry about the migration path from one to another, especially if you manage the VM using an abstraction layer like libvirt or OpenStack. So you can imagine the following timeline of handling a security issue. Previously, your best choice to deal with any vulnerability is to wait for a security patch. But with hyper-TP, switching to another hypervisor lets you mitigate the vulnerability while you're waiting. So you have a choice to return to your original hypervisor once it's fully patched. So in general, what it does is that it shrinks the vulnerability window of the system, as you can see on the figure here. So for hyper-TP, our solution is a combination of two approaches. One is that you directly replace the running hypervisor with another while preserving a VM on the same host, and we call that in-place hypervisor transplant or in-place TP. Another approach is that you migrate the VM that is running on the source hypervisor to a different destination hypervisor on another host. This is similar to live migration, so we call that approach migration-based transplant or migration TP. So both of these approaches depend on a couple of main principles. The first one being memory separation or classification of memory types of the VM, and the second one is an unified VM representation across all hypervisors. So here I have the main workflow of hyper-TP, which consists of 5 steps. Firstly, you need to preserve the VM state and memory of a running VM that you want to transplant, and suspending it at the same time, which are steps 1 and 2. Next, you transplant the VM to the new hypervisor, either using the in-place technique or the migration technique. Once the transplant is done, you restore the VM state and resume its operation. For the principle of memory separation, we identified 4 categories of hypervisor memory. These categories range from the most VM-specific states, like guest memory, which does not concern the host, then the states that partially involve the host, like VM memory maps, and also there are states that are hypervisor only and not related to VMs at all. We identified that the first 2 categories of states are needed to reconstruct a VM on another hypervisor, so these 2 categories need to be saved and translated in hyper-TP. So next, we identified that on the same host, the states of running VMs tend to have elements in common with each other, even across different hypervisors. This is because these hypervisors can either use hardware virtualization, which actually enforces this commonality, or there is a common API like virt.io, which is shared by multiple implementations. From the viewpoint of the VM also expects a common hardware interface, for example, things like timers, interrupt controllers, and so on. So with each of the device, we implemented a pair of functions to translate them from the hypervisor state into a format of our choice. And finally, we can extend this kind of representation into you can call it an unified virtual machine API that can be used by any guest kernel on any hypervisor. So for our actual implementation, we based it on Zen and KVM. For KVM, we focused our implementation on top KVM tool, which is a lightweight utility for running virtual machines on top of KVM. Overall, we implemented hyper-TP in about 8,500 lines of code, of which around 90% is based in user space. So this leads to a very flexible implementation that also minimizes the security impact of our solution. For in-place TP, we implemented it from Zen to KVM and from KVM to Zen, as well as from Zen to Zen, which you can use for upgrading from one version of Zen to another. For migration TP, we also have an implementation from moving from Zen to KVM. So next, I'll be talking about how the components of hyper-TP are done in detail. So first, let's go into devices. Actually, saving and restoring virtual devices is already part of most hypervisors. So what we needed to do was just to adapt these hypervisors to use the same device format. So we ensured that the critical platform devices are preserved, and then for any devices that are not compatible with the new hypervisor, we unplug them before performing the transplant. However, like what I mentioned for the unified VM representation, these devices can be eventually integrated as part of an uniform virtual machine API that is consistent across many hypervisors. So during hypervisor transplant, besides saving guest state, we also need to take care of guest memory. In the particular case of in-place TP, we don't want to save this guest memory to disk because it would take a long time to save everything. So instead, what we do is we try to keep all guest memory pages in host RAM so that these pages can be reused by the next hypervisor. And what we did is we used an in-memory file table structure to keep track of these pages and represent each VM's memory as a separate file. We call these metadata table pages PRAM, and the way we construct the PRAM pages is that first of all we allocate some temporary memory. We then define some regions of physical memory that must be preserved in the host, and then copy any VM memory that's living there into the temporary region. We finally use the remaining temporary memory to construct a PRAM table for each VM. So this is the structure of the PRAM table. It starts with the PRAM pointer value that points to a chain of root directory pages, which I've colored in red here. Each root directory page contains 5 pointer entries that point to file info pages, which are colored in green in this figure. Each file info pages themselves are like inodes, and they contain the metadata of the VM memory file, including its size, file mode, file name, etc. Each file info page also contains a pointer to a chain of nodes, each containing page entries which I've highlighted in blue here. Each page entry finally is the guest physical to host physical mapping of a memory page so that this mapping can be restored in the new hypervisor. So now that we have constructed the memory structures, I would like to proceed with the third step, which for migration TP is just like normal migration. But for in-place TP is a bit more tricky, which is you have to replace the running hypervisor. So while we replace the hypervisor, we don't want to lose the existing memory content that contains the VM memory. So we use kexec to boot the new hypervisor without going through BIOS. We made some fixes for this kexec feature so that we can boot smoothly from Xen to KVM and vice versa. Also, we pass the PRAM table address using the kernel command line to the new hypervisor so that it can be processed. So once the transplant is complete, we had to start the step of restoring the VM on the new hypervisor. We added code in KVM tool to map each VM state between Xen's VM state and KVM, and then we restored each device with the corresponding mapping. So during this process, we also had to make sure that the structures of the virtual devices on both sides matched up with each other. For example, we had to make sure that the number of virtual I/O APIC pins on both sides matched up, and to make sure that devices like virtual clocks would continue to function after the transplantation. Aside from the VM device states, we also needed to restore memory of the VM. In the case of in-place TP, the new hypervisor parses the PRAM structure to detect the existing memory regions and present them to the new VM being restored. For KVM, we present the PRAM memory as a file system so that the new VMM like KVM tool can just mmap the file and have the memory ready for use. But for Xen, we had to implement new hypercalls to traverse this new PRAM file system and assign these files to the memory of domains that need to be restored. And that's all the steps of hypervisor transplant. So we evaluated HyperTP on 2 machines that we call M1 and M2. Since we have quite a few different transplant cases that we needed to examine, here I will go into detail the case of Xen to KVM transplant. Here's a figure that tells you how long each step of the process takes for a VM with 1 vCPU and 1 GB of RAM. You see that for M1, the time for transplanting this VM is only 1.7 seconds, which is to say after 1.7 seconds of downtime, the VM is already resuming its operation. For M2, the transplant time takes a bit longer, which is around 3 seconds. For some devices, it takes more time to restart. For example, the network card on M1 takes around 8 seconds of downtime before it can be resumed. But we also implemented some fixes into a Linux kernel to allow fast resumption of devices. For example, the RAID card, which normally would take around 30 seconds to a minute to start and we hold up the entire boot process. With our patch, the RAID card can be resumed right away and will not hold up the process. Here we have a figure of Redis performance under in-place TP and migration TP to show the impact of the 2 solutions. The left side is comparing in-place TP to a normal VM running on Xen without any transplantation. We see here that with in-place TP, the process starts and then 9 seconds later, the VM resumes and you don't see any impact to Redis performance before or after the transplant. On the right side with migration TP, you can see that regardless of whether you're doing Xen to KVM or normal Zen-to-Zen migration, the performance is the same. In this case, the Redis server had bad performance for 76 seconds, as well as a short period of downtime before everything goes back to normal. So we can see how a solution like InPlaceDB can speed up the process of patching of a data center, since you spend much less time on migrating the hosts, and all of the VMs get transplanted at the same time without consuming any network bandwidth and doesn't have a long period of impacting performance. So the factor of impact on upgrade is also something we consider for our solution. We use the tool called Better Place to simulate the upgrade of a cluster which contains a number of VMs. In the cluster, you can denote some VMs as being compatible with InPlaceDB and some others as not compatible. We set up the upgrade process so that you can migrate the VM from one kind of hypervisor to another. It can be from Zen 2 KVM or Zen 1 to Zen 2, for example. In any case, you can see that the more VMs that we have that is compatible with InPlaceDB, the more time you save in upgrading the hypervisor cluster. So if you have 80% of your VMs that are compatible with InPlaceDB, for example, you save 80% of time upgrading the hosts, and this is with all hosts having 10 gigabit Ethernet. With this, you can see how HyperTP will help shrink the vulnerability window of a data center by helping you speed up the upgrade process. And that's it for the presentation of HyperTP. Thank you very much for listening.
Hello, my name.
All right. Thanks very much, Tuling. So now we're going to open for questions. Please post them on Slack on the session channel. And in the meantime, I'm going to start with a question that I have myself, Tuling. And it's that given that in some current systems we have today, like AWS Nitro, we have like substantial portions of the hypervisor that are now living on a separate card that has an independent upgrade cycle. I was wondering how this changes the balance on how necessary it still is, or is not, that's the question, to have this type of upgrade cycles on the host hypervisor, or if moving those into this AWS Nitro card, style of cards would reduce our necessity for having these kind of features. And if you could comment on what the trade-offs you think would be in that case.
Sorry, could you repeat a bit on the AWS, because I'm not too clear on that.
Oh yeah, so Amazon Services has this card that they have developed in-house that you can just plug in through PCI Express, and it contains some cores together with some infrastructure to virtualize devices, and part of the hypervisor is living on that card itself. So you are effectively moving some of the hypervisor into this separate card that has its own upgrade cycle, and their motivation is exactly the same, is so that they can more easily control the virtualization and upgrade cycles of critical devices. So I was wondering how do you think this plays into the role of hypervisor transplant, where you're providing this feature at the host hypervisor, and whether the change of this balance still necessitates both, or one becomes more important than the other?
I think this card solution of AWS can be combined with our solution, because the card solution, basically it is a hardware level feature, and we are more targeting the software level. So for example, if you have any things that need to be patched in the software level, for example, some para-virtualization drivers, you might use our solution to be able to upgrade the host side of the software side of the host, and then the hardware side, of course, you can replace it with the card. And for me, these two solutions, they can be combined with each other.
Luis, you're muted.
Yeah, there we go. So thanks, Julie. So I see there are no questions. So in the meantime, while people get warmed up, I have another question. It's like, I don't know if you are familiar, Tuling, about some work from Cristiano Giuffrida on Minix, where they basically looked at automated live update of programs through some compiler support, compiler and runtime support. And I was wondering if something like that eases extraction of these critical points of when state can be migrated between different code versions. And in your case, it's like an extreme case, right? Where you can even change between hypervisors. But I was wondering if this software support would make our lives easier in transporting or migrating this state across versions and versions of and types of hypervisors, instead of engineering the software to deal with that in some format.
I think that from the question of whether this solution can help, I think that when you're moving from one hypervisor to another, there's a difference because you're changing the underlying API. So, for example, if you can imagine there is some already accepted hypervisor API for all virtual machines, for example, you can imagine having something like that. But if not, because basically the hypervisor, it takes care of not only the VMs but also the underlying hardware. I would say that it's more difficult to say we have an underlying layer.
Okay. Okay. So it seems good. Okay. Maybe it wouldn't help that much because there's just too big of a gap. So let me check. Well, we still have like 3 minutes before we switch over to the next presentation. So I have one last question, and is that you talked about virtualization in your previous answer, and I was wondering what happens with the guests that have virtualization detection support at runtime for features that go beyond pure devices, like some kind of virtualized shortcut that is specific to the hypervisor. And how do we deal with that? Do we have to, let's say, pull back from all of those hypervisor specific optimizations if we want to be able to support that? Or could we come up with some way to make some changes on the guest state as part of the hypervisor transplant? Or what do you think about that?
I think this comes back to the question of whether we have a hypervisor API or not. Because when you look at, for example, emulated devices, they're basically one kind of API. So when you're saying, okay, I provide some virtual APIC implementation, that is basically an API that you're offering to the guest. So if you can provide this API for para-virtualization purposes, you can imagine that you can just smoothly move from one hypervisor to another, or a solution also it can be used to move from one version of hypervisor to another version. So you can imagine it can also be applied in that same case. But if you cannot guarantee this level of API, I think it's going to be difficult.
Okay, thank you. So it seems that some people are getting warmed up. There's a related question that came up, and is that the question basically says, for incompatible devices, typically para-virtualized devices, how would you imagine modifying the guest operating system to support changing device models?
I think the ideal case is, like I explained, to have a API that you can share between all hypervisors, and all you need to do is just shift over the para-virtualized device state. But if not, I think the easiest and most reliable way is to just unplug the para-virtualized device from one side and then replug it on the other side.
Okay. Well, thanks very much, Chuding. I think that's the end of the Q&A, and we should be, if there's no any last short question, we should be switching to the next paper. Thanks very much, Chuding. So our next and second paper has the title of memory mapped ion steroids, and it's going to be presented by Anastasios Papagiannis, who has completed his PhD in the computer science department at the University of Crete in Greece, and also was a graduate research assistant at the Institute of Computer Science in Forth. His research interests are in the general area of storage systems, and we will see some work now that he has done. So please go ahead with the presentation.
My name is Anastasios Papagiannis, and I'm going to present our work with title Memory Mapped I/O on Steroids. This is a joint work with Manolis Marazakis and Angelos Bilas, who is also my PhD advisor. Today, the majority of storage devices are block addressable. These include traditional hard disk drives, but also fast storage devices like flash. This will not change anytime soon due to capacity and cost reasons. Block addressable storage devices require I/O caching over DRAM for several reasons. These include performance, because DRAM is much faster compared to persistent storage, and also granularity, as applications tend to access data in a word rather than block granularity. The introduction of emerging fast storage devices aggravates storage caching issues. First, the heat path requires expensive software cache lookups, and this results to spending many more precious CPU cycles for cache management rather than user processing. Additionally, in storage caches, one size does not fit all. As an example, applications use specific techniques to reduce small random writes. They separate reads and writes for cache pollution purposes and other application-specific optimizations. Memory mapped I/O has the potential to solve these issues. In memory mapped I/O, a file or device is mapped to a process virtual address space. Applications can use process or load store instructions in order to access data. In this case, the kernel is responsible to fetch and evict pages on demand. In memory mapped I/O, hits are handled entirely in hardware through the memory management unit and the TLB. In the case of a TLB miss, an additional page tape walk is also required. As hits are handled entirely in hardware, this provides less overheads compared to software cache lookups. On the other hand, misses require a page fault instead of a system call, and this introduces additional overheads. The 4 kilobyte page size that a page fault relies on also results in small and random I/Os. Another issue is that Linux memory mapped I/O does not allow customization as it relies on the Linux page cache. Because of these issues, today user applications prefer to do I/O caching with system calls. Next, we provide the common ways to do storage caching today. A kernel space cache, as we see on the left figure, requires system calls for hits. On the other hand, I/O does not require any system calls. A kernel space cache contains raw, serialized device blocks. On the other hand, as we see on the right figure, a user space cache requires cache lookups in the case of hits and system calls only for misses. It is generally used to store application-specific deserialized data. To avoid system calls for hits and enable customization, today applications tend to use a user space cache. However, it still requires system calls for misses. On the other hand, software cache lookups in the common path introduce overheads, especially in the case of fast storage devices. This table summarizes the benefits and drawbacks of different ways to do storage caching today. First, in terms of the hit cost, a kernel space cache requires system calls for hits. A user space cache removes the need for system calls. Linux EMMA provides the lowest overheads as hits are handled entirely in hardware. The miss cost with a kernel space cache is high due to the system calls. A user space cache can remove system calls by using dedicated storage devices and user space I/O frameworks. With Linux EMMA, the miss cost requires an expensive page fault. Finally, the kernel space cache and Linux EMMA rely on the Linux buffer cache and the I/O stack. Both of these are not customizable based on application needs. A user space cache enables the use of custom caching policies and ways to access storage devices. Our work, named Aquila, overcomes all of the Linux EMMA disadvantages. We leverage the efficient hit path of memory mapped I/O, and we provide an optimized miss path that removes the need for protection domain switches. We also enable customization in DRAM caching and device access, similar to a user space cache. Our approach combines the advantages of a user space cache and memory mapped I/O. Aquila is a novel memory mapped I/O path that collocates the user application and memory mapped I/O path in a high privilege domain, non-root ring 0 in Intel terminology. Our approach requires minimal application modifications and provides strong protection semantics similar to Linux memory mapped I/O. Aquila allows user applications to customize the DRAM caching and device access based on application needs. Our approach also reduces significantly software overheads in the memory mapped I/O path. Now I'm going to provide more details about the design of Aquila. We observe that cache management with memory mapped I/O requires several distinct operations. The first operation, during the hit path, uses load store instructions that are handled entirely in hardware through the memory management unit. For this reason, the hit path does not result in any software overheads. On the other hand, the miss path requires virtual address space manipulation, which also includes page faults. The second operation includes the DRAM cache management in the case of a miss. First, it checks if the page already exists in memory and also handles evictions and writebacks. The third operation includes data transfers between the device and DRAM. The fourth operation is a management operation. In memory mapped I/O, it includes file or device mappings that are handled by mmap and munmap system calls. The last operation is physical memory management, which also includes the dynamic resizing of the DRAM cache. In Linux, all of these operations happen inside the operating system, and they require a protection domain switch from the user to kernel space. Today, page faults are handled in ring 0, and user applications run in ring 3 for protection. For this reason, all operations in the miss path are expensive. These include virtual address space manipulation, cache management, device I/O, and other management operations. We design and implement Aquila that uses ring 0 for performance and non-root mode for protection. In this case, page faults in ring 0 incur lower costs, and non-root mode still provides strong protection. To achieve this, we use hardware virtualization extensions. Intel VTX is a family of hardware virtualization extensions that targets the acceleration of virtual machine management. Except from the 4 traditional protection domains, it includes 4 additional protection domains, and they are separated into root and non-root mode. The root mode is intended to run the host operating system and the host application. The non-root mode is intended to run the guest. Even in this case, a transition from ring 3 to ring 0 in both modes requires a trap. In order to change mode, for example, from non-root mode to root mode, a VM exit is required. This is a heavier operation compared to a trap. We categorize storage cache management operations to common and uncommon path operations. Common path operations happen for every miss, and they are handled in ring 0. These operations include virtual address space manipulation that happens with page faults, DRAM cache management to check if a page already exists in DRAM and also handle evictions and writebacks, and data transfers between DRAM and storage devices. Uncommon path operations happen at a lower frequency, but they require a VM exit. These include management operations, such as file or device mappings with mmap and munmap system calls, and also physical memory management that includes the dynamic resizing of the DRAM cache. Both of these operations mainly happen during application initialization and do not change for large periods of time. In Aquila, common path operations do not require a protection domain switch, and this results in less costs in the common path. On the other hand, uncommon path operations with a VM exit are heavier than before, but this is not an issue as they happen at a lower frequency. Today, operating system runs in root ring 0, and user applications run in root ring 3. The main idea is that Aquila runs user applications in non-root ring 0. This enables to handle all common path operations without the need for protection domain switch and serve page faults in a trapless manner. Aquila also requires the host operating system to serve uncommon path operations. In this case, it requires a VM exit, and uncommon path operations are heavier than before. This is not an issue as uncommon path operations happen less frequently. More details on the common and uncommon path operations and other implementation details can be found in our paper. Next, I'm going to talk about our experimental analysis. For storage applications, we use RocksDB, a state-of-the-art persistent key value store from Facebook. The common configuration is to use a user space cache and read-write system calls to interact with storage devices. RocksDB also provides an option to use memory mapped I/O. In this case, we use Linux mmap and Aquila. We use YCSB with a 32 GB dataset and 8 GB of DRAM cache. Additionally, we evaluate Aquila in terms of extending the available DRAM over fast storage devices. In this case, we use Ligra, a graph processing framework. To achieve that, we translate all malloc and free calls to be over a memory mapped storage device and not DRAM heap. We use the BFS algorithm with a 64 GB dataset and 8 GB of DRAM cache. First, we compare Aquila with explicit read-write system calls and we provide an evaluation in terms of throughput using RocksDB. In this figure, x-axis shows the number of threads and y-axis shows the throughput in millions of operations per second. We show 3 bars here. The orange one is for RocksDB with Linux mmap, the blue one for RocksDB with a user space cache and system calls, and the red one for RocksDB with Aquila. With a single thread, Aquila provides about 1.2 times higher throughput compared to a user space cache. With 8 threads, this increased to 1.4 times, and with 32 threads to 1.6 times. Aquila outperforms a user space cache with system calls to access persistent storage. The benefits of Aquila compared to Linux MAP are even higher. With a single thread, Aquila provides 7.5 times higher throughput. With 8 threads, 7.2 times, and with 32 threads, 10.4 times higher throughput. This shows that Linux MAP is not appropriate for data-intensive applications, and Aquila overcomes these limitations. To understand where do these benefits come from, we provide a breakdown of the storage cache management overheads. We show two bars, a user space cache configuration on the left and Aquila on the right. In both cases, we use RocksDB. Y-axis shows the number of cycles. Each bar consists of a purple part, which is about the I/O, a green part, which is about cache management, excluding the I/O costs, and the light blue part, which is about the remaining costs of RocksDB. With a user space cache, 69% of the total execution time goes to cache access and cache management. With Aquila, we reduce this cost by 2.58 times, and this results in 43% of the total execution time. This leaves precious CPU cycles for further user processing. To conclude, we propose Aquila, a novel memory mapped I/O path that significantly reduces I/O overheads and provides customization based on application needs. To achieve that, Aquila collocates application and memory mapped I/O path in non-root ring 0, a high-privileged domain. This design enables a fast MIPS path and customization for both cache management and device access. We evaluate Aquila as a way to manage the storage cache and in order to provide heap extension over fast storage devices. With RocksDB, Aquila provides up to 40% increased throughput, and this comes from a reduction of up to 2.58 times in CPU cycles for cache management. With Ligra, Aquila results in up to 4 times reduction in terms of execution time. This concludes my talk. Thank you for your attention. If you have any questions, you can reach me via Slack or email.
All right. Thanks very much for that presentation, Anastasios. So let's start with the questions. I don't see any on the thread in the channel for this paper, so I'm going to start when people get warmed up. And I was wondering that whenever I see this type of works, there's a tiny computer architecture voice inside my head that asks me if we should be redesigning or operating systems to use the approaches like the one presented here in Aquila, or if we should instead put efforts in and look for ways to optimize our microarchitectures. I don't know what you think, Anastasios.
Hello. So what we take the first approach where we try to modify the operating systems and the hypervisors in order to get rid of the existing microarchitectures in order to gain benefits and accelerate the I/O. For sure, I believe that there are cases where we can optimize the microarchitecture as well in order to provide better solutions towards this direction. But this work shows that for now, optimizing the operating system itself and the hypervisor, it's enough to gain benefits, and I feel that there is still more work to do before moving to do changes in the microarchitectural level.
All right, thanks very much, Anastasios. So we have a question on the channel from Jakub Silksik. And the question is, it's a technical question, and does the MMAP path you tested include appropriate M-advice hints before accesses? And also, have you looked at what the impact of the new I/O U-ring infrastructure in Linux, as it allows for reduced system call overhead?
So the first part of this question about the M-advice hints, no, we haven't evaluated the M-advice hints. I think this is similar to both Aquila and Linux MAP, where we don't use M-advice system calls, and we see it's fair for our comparison. Having M-advice system calls is something that users should take aware of, and this can improve the performance further. So about I/O U-ring, we don't have a straight comparison between IO-Uring and Aquila or Linux EMAP. What we have proposed in our case, in Aquila we use SPDK to access NVMe devices. Aquila can use other backend systems like SPDK, other user space frameworks, read-write systems, and also IO-Uring. We can use this in order to accelerate Aquila, but we haven't compared to IO-Uring. Another issue here is that IO-Uring still requires a user space cache, and we still have the hit cost, the software cost. So memory mapped IO removes this cost, and we can also leverage IO-Uring to access storage devices.
All right. Thanks very much, Anastasios. So just one last very quick question that we have here. Edward Staniloiu is asking if the project is open source and how would one go about to reproduce the experiments?
It is not open source yet. We haven't gone through the artifact evaluation, but we are preparing an open source version of Aquila. We believe next 2 or 3 months we're going to have this project open source, and for sure there will be guidelines on how to reproduce these experiments.
All right. Thanks very much, Anastasios, for your paper. Cool work. I hope that everyone else is also clapping from wherever they are. The next paper in the session has the title "Bridging the Performance Gap for Copy-Based Garbage Collectors Atop Non-Volatile Memory." And it's going to be presented by Mingyu Bu from Shanghai Jiao Tong University. So please go ahead with the presentation.
Hi, I'm Ming Wu from Shanghai Jiao Tong University. Now I will present our work, Bridging the Performance Gap for Copy-Based Garbage Collectors Atop Non-Volatile Memory. This work is done together with my colleague Yanfei Yang and my advisor Haibo Chen and Bing Zhao. Non-volatile memory is known for its features like non-volatility, like SSD and HDD, and byte addressability, just like normal DRAM device. But it's also known for its large capacity, power efficiency, and lower price. So it can be used as a large alternative memory device for DRAM. People can organize DRAM and NVM together to form a large capacity memory. This usage is welcomed by managed language, especially for applications already have large appetites for memory resources, just like Spark, Flink, and HBase. For example, Spark can cache its data structure RDD into memory. To support this usage, the OpenJDK community has allowed heap allocation directly atop NVM. This proposal, JP 316, allows Java applications to allocate objects or large heaps atop the NVM while maintain other data, just like metadata for classes and methods on DRAM. In this usage, most memory accesses will touch NVM instead of DRAM. However, NVM also have disadvantages, and prior work has uncovered performance problems of NVM compared with normal DRAM devices. The first one is the random read and sequential read operations. The latency is actually larger than DRAM. Secondly, both maximum read bandwidth and the maximum write bandwidth is much smaller than DRAM. The third problem is the bandwidth asymmetricity. We can see that the maximum read bandwidth for NVM is much larger than the maximum write bandwidth. This leads to a problem that NVM is quite sensitive to workload. When the write ratio increases, when number of write operations increases, the overall bandwidth will drop dramatically. Now we have known the disadvantages of NVM, but the memory behavior of Java applications atop NVM is still unknown. So we have conducted some evaluation. We run Java applications atop a CPU with 28 physical cores and SMT enabled, and we use 6 Intel Optane DCPM devices to maximize the NVM bandwidth. We extract 6 applications from Renaissance and Spark. We also break the applications into two phases, APP phase and GC phase. And the results shows that the GC time is actually severely affected compared with the APP phase. Slowdown is 2 times to 8.25 times. As comparison, the access latency is about just 2 to 3 times. Before analyzing why GC time is severely affected, we will first give some background about the copy-based GC. It is a very important algorithm, and many modern collectors in managed languages are copy-based. For example, the G1 and PS in OpenJDK, and a Mark compact algorithm in a common language runtime in C#. A copy-based GC collects the key by moving live objects together. After GC, it will organize the consecutive free space for fast memory allocation. However, since it needs to copy a lot of objects together, it will introduce large bandwidth consumption. The bandwidth is actually the culprit for the GC slowdown atop NVM. We use the page rank in Spark as an example. For the DRAM case, the bandwidth can increase during GC because it has not reached its limit. However, for NVM, although we use the same workload, the bandwidth does not increase but decrease during GC. So we need to understand why the bandwidth decreases during GC and why it reaches its limit. Now we will dive into details of the copy-based GC. We use G1 as an example because it's default in OpenJDK. It's region-based, which means that it partitions the heap into regions for ease of management. And it's generational, which means that it only uses a few regions for heap allocation, and those regions will be collected in most cases. This can avoid a whole heap collection and reduce the pause time. And it's also multi-threaded. Each working thread has its own stack, which store references to the heap region. And during working, the thread will use these references to process objects and find all live objects and copy them. By adding more working thread, the algorithm can reduce the GC pause time. The G1 algorithm on reference processing can be divided into 5 steps. The first step is to fetch a reference from its working stack and find the object it points to in the G1 heap. The second step is to copy the object from the current region to another region. Step 3 is to update a forwarding pointer in alt copy in its header. Next step is to inform other threads that its object has been copied, and other threads can avoid repeatedly copying this object. The fourth step is to update the reference, which originally in NVM with its new address. The fifth step is to find if the object contains unprocessed references to other live objects on NVM. If it does exist some unprocessed references, its reference will be pushed to the stack for future processing. Okay, after this object or reference has been processed, the working thread will repeatedly pop the reference from its working stack and processing them until all objects has been processed. Okay, now we put the 5 steps together. We can see that all the 5 steps can introduce many read operations and write operations to NVM. If we consider more threads, then we will introduce many read operations and write operations. That is the main problem. The G1 algorithm mixes many writes and reads together. If we consider the previous figure, if we have many writes, then the bandwidth will be jobs. So we will propose design to separate read operations and write operations, and thus improve the bandwidth during GC. The first design separates the data update. We introduce a region write cache for NVM update. It maintains a one-to-one region mapping for NVM regions on DRAM. When an object needs to be copied, it will be copied to DRAM in the region cache instead of NVM. Before GC ends, all live objects will be contained in the region cache. At that time, those objects will be flushed to NVM. Note that also we use the non-temporal instructions to avoid because it's NVM friendly and it can maximize the NVM bandwidth. By introducing the first design, we actually split GC into two phases, read mostly and write only. In the read mostly case, the first step and the fourth step has been replaced with the write operations to DRAM. While in the write only phase, there will be only write operations to NVM. There will be no read operations interfere with write. So in these cases, we can maximize the bandwidth. However, there's still a remaining problem, the header update, which is the third step. So we propose the second design to reduce the header update. We introduce a header map to store forwarding pointers. That map is organized as a hash map, which maintains a mapping from old address and new address. When the GC thread wants to update the header, it will become an insert operation to the header map. The workflow is as follows. That will be hashed with the hash function and find the corresponding slot in the header map. And secondly, we use a linear probing to find the suitable slot to store the mapping. A third step, if we find that a slot is empty, we can store the map from old address to the new address in a slot. However, if we cannot find an empty slot, we will go to the NVM to directly update the header. Now with the second design, we can now modify the third step so that it modifies the header map on DRAM. However, since the header map is use linear probing, it can fail, so still some NVM will occur when the linear probing fails. Now we'll briefly introduce the evaluation. We use 26 applications in all from Renaissance and Spark. And the figure shows that the 23 of the 26 applications can be improved with our optimization. And for the average GC time reduction, we can reach 1.69 times GC time reduction if we use both two optimizations. And if we only use write cache, we can improve 1.17 times. We also notice that the performance gap between DRAM and NVM now drops to 2.28 times, which is close to the latency gap, which is 2 to 3 times. And for the bandwidth, the figure shows that we can increase the average bandwidth during GC by 55% on average. And the best bandwidth improvement would be 2 to 58 times. We also show an example, the Spark PageRank, to show how bandwidth changes during GC. For the vanilla case, there is only one phase and the bandwidth is not satisfying. And for our optimized version, we can clearly see that there will be two phases, the read mostly phase and the write only phase. And both phases can be, the bandwidth in both phases can be improved. So the result shows that separating reads and writes helps. Okay, to conclude, the commodity NVM can be used as alternative memory devices, which is welcomed by memory-intensive applications in managed languages. However, GC performance actually suffers due to NVM's limited bandwidth. Our optimizations sufficiently utilize NVM bandwidth by introducing two designs, write cache and header map, to separate the read operations and write operations. Thank you. That's all.
Great. Thanks very much, Emilio. So we have some questions on the Slack channel, on the thread for this paper. And it's from Jacobos Kolokasis, who says, dear authors, congrats for your work. Some questions. And there's a list of 3. So the first one is, do you use applications that cache a large amount of data in Spark? Second question is, which applications did not improve and why? And the third one is also, do you believe that we need new approaches to check objects lifetime and locate long lifetime objects in NVM? If we know object lifetime from the application, we could locate them in non-garbage collected heaps and avoid copying.
Okay, can you hear me?
Yes, we can hear you.
Okay, thank you for your questions. And for the first one, we actually use some applications in the Spark examples, and we use 256 gigabytes configuration. So if the application wants to cache the data, which usually is the data set, for example, a page rank is actually the data set originally stored in the disk, and we can cache them in the memory, actually in JVM, and in the NVM configuration, we store them in the NVM. And for the second one, we actually test the applications from Cassandra and the applications in Renaissance benchmark and in Spark, and we find that some applications did not improve because the garbage collection time is quite short, and some of the bandwidth is actually not saturated. And for this case, we do not improve them much. But for most applications in Renaissance and for all applications in Spark and Cassandra, we have reached the improvement for GC, because most of the applications are quite memory intensive, and they can easily saturate the NVM bandwidth during GC. And for the third question, I think it's good to provide object lifetime, and I believe in about 2018 there will be papers in EuroSys, and they profile the object lifetime and tries to allocate them or pre-tenor them in some non-garbage collected space, or the spaces which is not collected frequently. I think it's good for both DRAM configuration and NVM configuration, and perhaps it helps in NVM because the write latency and the write bandwidth is not good in NVM. Yeah, that will be all. Thank you.
Thank you very much, Mingyu. I see that there's another question, but unfortunately, we are running a bit late with the presentation, so I'm gonna switch. So before we switch over to the next paper, I, of course, would like to thank again the authors for this good work. And so now the paper that we have is the one that was just presented before as the best paper award. And it's Unicraft, fast specialized unikernels the easy way. And we have with us Felipe Wisi, who's going to present this paper. And he's the chief researcher at NEC Laboratories in Heidelberg, Germany. And he's passionate about systems research and virtualization, and a firm believer that unikernels are on the brink of finally enjoying widespread or wider spread adoption. So please go ahead with the presentation. Thank you.
Hello, good morning. I'm here to talk to you about Unicraft, or how to build fast specialized unikernels the easy way. Unicraft is a Linux Foundation project and part of the Zen project, and this is work that we've done together with people at the University of Bucharest, Manchester, Lancaster, and Liège. So if you're interested in high performance, specialization is one really good way to get it. And whether you're doing it in software by building custom-built virtual machines for runtime environments such as OCaml and JavaScript, or you're interested in high-performance networking and you're using DPDK for it, or you in hardware using TPUs and so forth for machine learning workloads, specialization is one really good way to get high performance. In the virtualized world, the way to do that is unikernels, which are essentially specialized virtual machines. There are a number of goals that unikernels should accomplish. The first one is that they should be easy to build and run. This hasn't always been the case, including past projects of ours. The second one is there should be ideally no application porting. This is something that also not all unikernels have been managing to do in the past. And the third part, of course, is that they should provide great performance. So in designing Unicraft, we had two main principles. The first one is that we wanted a fully modular kernel so that we could do full customization of the entire software stack. The second part is that we wanted to have a number of high-performance specialized APIs as first-class citizens. So the first one, how to make a fully modular kernel. And the question is, why don't we just do it with Linux? And for this, we built a dependency graph between Linux's main subcomponents. An edge means a dependency, and a number above an edge means the number of dependencies. And it should be pretty clear from this diagram that removing one item from this diagram and from Linux requires significant engineering effort. Instead, Unicraft is built from scratch to be fully modular. The second design principle, specialized APIs. To give you an example of what I mean, imagine you have an application that is network bound and it's going to compile it against glibc. Under that, POSIX sockets, the network stack, and eventually a high performance API. Of course, it's not going to get high performance because by the time it gets to the API, there's all these intermediate layers slowing it down. And maybe if you could code just against that API, because maybe you only care about UDP, you could go really fast. Of course, this is a form of bypass, and there's been a lot of work in the past for this. But in Unicraft, this is a first citizen construct, and it's really easy to code and slightly modify an application to get even better performance through a specialized API. This is the main Unicraft architecture diagram. At the very top, you have the application. We support two libcs, musl and newlib. Under that, we have an entire POSIX compatibility layer. I'll speak a little bit more about it later. And under that, you have the core of Unicraft. And the black boxes you see on here are the specialized APIs I mentioned. For instance, just like in the example, if you cared about high-performance networking, you could code directly into our UK NetDev high-performance network API. Likewise, if you were interested in retrieving files very quickly, you could bypass VFS and code a specialized file system just to do that, and I'll show you an example of that later on. Finally, you could use different memory allocators, and Unicraft supports multiple of them, and you could even have concurrent different memory allocators in the same image. So getting back to our goals, the first one is that it should be easy to build and run. And there's no easier way to show this than just do a little demo. So for here, we're going to be using the craft tool. It's a tool that wraps around Unicraft. So we're going to say craft up. We're going to choose our application, Nginx in this case, at staging. And we're going to name our unikernel my Nginx unikernel. And the first thing craft will do is fetch all the sources. Once it's done, it'll immediately start building. And after that, it'll immediately run Nginx, in this case on KVM. So there it is. It's up and running. And to make sure it's the case, we're going to run a little curl to get one web page. Okay, there it is. One time. Let's do it again. Make sure it's still working. Maybe do it a third time. Okay, so you can see it's pretty easy. The second goal is there should be almost no application porting. Binary compatibility is one way to do it, where you grab an ELF and unmodified, you put it on top of a unikernel. And some projects have attempted to do this. The ultimate problem is that the difference between the cost of a system call and function call is significant. Instead, what we do is what we call auto porting from sources. Basically, we take an application's native build system, just take SQLite for instance, and we're going to have it generate its standard object and archive files, and we're going to link those directly into the Unicraft build system. In Unicraft, we have a port of musl. Musl, of course, expects Linux to be underneath, so it's going to try to do syscalls. So we add a syscall shim layer to trap those. Under that, we have syscall implementations, but under that, instead of Linux, of course, there's Unicraft. So what about syscall support? So far in Unicraft, we support about 146 syscalls, and this is constantly incrementing. Just to give you an idea of how useful that might be, we took the Debian Popcorn most popular 30 server apps. Here they are plotted on the x-axis, things like Apache and SQLite. On the left-hand axis, we have the percentage of syscall support that we have for each application. And in green, I'm going to plot how much support we have. The main takeaway from this graph is that it's almost all green. So we already support a number of applications, and for the ones that we don't support, we are a few syscalls away from supporting those as well, and we are actively working on those. Just to give you a little taste of what Unicraft supports, there's a number of language environments such as Go and Python, Ruby, and so forth, applications such as SQLite and Nginx, and frameworks like DPDK and TensorFlow Lite. The third goal is, of course, great performance. So the first question we want to answer is, if we do this auto porting, are we actually sacrificing performance? And to do this, we did a quick test with SQLite, where we're going to compare our manual port of SQLite versus the auto port version. We're going to do 60,000 insertions, and we're going to measure how long it takes to do that. And as a baseline, we're going to use Linux. It takes about 1 second. We compare that against our manually ported versions of SQLite on top of New Live and Muscle, which perform just as well as Linux. And then the most important part is this last one, where we use the auto-ported version on top of Muscle, and you can see that basically auto-porting doesn't negatively affect performance. So this is good. Okay, so let's look at some of the performance benefits that you get if you transparently port things in this fashion. The first one is Unicraft boot times. So on the left-hand side, we have the actual boot time. On the y-axis, we have different VMMs. So first QEMU, then QEMU, and we're going to add a NIC, QEMU a micro VM, which is a faster version of QEMU, and then Sol 5 and Firecracker. And we're going to split the cost between the VMM cost and the actual time it takes the Unicraft VM to boot. And just to pick on a few results, QEMU takes about in the order of 40 milliseconds, so pretty quick. You do take a little hit when you add virtual devices. QEMU micro VM is much quicker at 9 milliseconds, but the fastest are Solo 5 and Firecracker, so about 3 milliseconds, including the VMM time. In terms of memory requirements, we took a few applications, Nginx, Redis, SQLite, and we measure how much memory you need to actually initialize them in Unicraft, all the way on the left in the y-axis, against other operating systems and projects. And you can see Unicraft requires anyway from 4 to 7 megabytes. And just to pick on another point, Lupine, which is a Linux-based unikernel, requires about 20 megs, and Linux Alpine about 30 megs. Nginx throughput. So in this case, we have average throughput in terms of requests per second, thousands of requests per second. And again, we're comparing against a bunch of different projects. Again, we're going to pick a few points. Let's start with Linux under KVM, which gets about 100,000 requests per second. Secondly, if we look at Linux bare metal, that jumps up to 175,000. Lupine, the unikernel project, goes to about 190,000, and we have Unicraft all the way up here at about 292,000 requests per second. Finally, let me show you a little taste of what you can do with a specialized API. In this case, we're going to be operating here in the area of a specialized file system. Imagine that what you want to do is just retrieve some static files, and so for this we built a specialized file system called SHFS, which is based on a hash table. We're going to compare against Linux. We're measuring how long it takes to retrieve the files in cycles, whether the file is there or not. As a baseline in Linux, going through the VFS, it takes in the order of 4,000 if the file is not there, and 2,000 cycles if it is. If you disable mitigations, because that hurts performance, you're looking at 3,000 versus 2,000. On the Unicraft side, if we go through our VFS, it takes about half what Linux can do. But the really interesting bar is when you use SHFS, and it's purpose-built, it bypasses VFS, and as a result, of course, you get an order of magnitude faster performance. So we believe that with Unicraft, high-performance POSIX unikernels are now a reality. There's a lot more information at unicraft.org if you're interested. As I mentioned, it's a Linux Foundation open source project, so all of the code is on GitHub. You can check it out there. And we have the 3 reproducibility badges, and there's a separate repo for those. So thank you very much.
All right. Thanks very much, Felipe, for this really nice piece of work. So I have one philosophical question that I would like to know what you think about. Is like, but would you say that unikernels are our latest reinterpretation of the exokernel ideas? And if so, why do you think that this approach will gain more traction?
Yeah, so to some extent, yes. I think what didn't work with unikernels in the past is that pragmatically they couldn't really run anything that was really useful. There's some exceptions. I don't want to get into the details. There was OSV and some other projects. But ultimately, what was killing them is that there wasn't a very pragmatic approach to here's good performance, but then you can also run all these things without having to do a lot of manual effort. And it turns out that that took us in a 3-year journey towards a lot of pre-engineering effort from us, so that you could support all these syscalls, and that the underlying unikernel was both modular but still mature in terms of OS features. So perhaps the barrier was a lot of engineering effort needed to be sunk in before you could get to the point where unikernels were actually useful.
Okay, yeah, thanks very much. So we have a question from Antonio Barbalace. He says, interesting work. glibc and musil are not binary compatible. So for example, you need to use musil-c includes to compile an application. If you use GNU libc includes, it is not going to work most of the time. Not clear how your auto processing works about this. Can you explain?
Yeah, so the order porting doesn't do binary compatibility. Although in Unicraft we are working on supporting binary compatibility. We do have a version that works, but that code is not yet public. Under binary compatibility, you do need to trap and then rewrite the syscalls to the underlying layers. We support Muscle for that. So there's two versions of Muscle. Muscle for order porting, that's the version I presented, and a Muscle for binary compatibility, which is not public yet, that needs to be slightly modified to be able to trap the syscalls that the binary compatible image expects. We don't yet support glibc, mostly because it's a bigger project. It's a bit of a, it would be a lot more engineering effort, and Muscle is mostly glibc compatible anyways.
Thanks very much, Felipe. So one last quick question, and then we will have to change to our next paper. This is from Manolis Marazakis, and he's asking, can you elaborate on I/O device access? Do you encapsulate device driver code?
So that's a good question. So Unicraft mostly deals with virtualized devices running in a VM. So we basically support networking and block I/O and so forth natively. If the question maybe has to do more with running on bare metal and how do you deal with those devices, Unicraft can run bare metal. The support is really early there. And for that, we are working on basically building a shim layer that can abstract the underlying drivers from the actual functionality of Unicraft, but that's ongoing.
Okay. Thanks very much, Felipe, and all the authors of this paper. Thank you.
Thanks a lot.
Okay, so let's go on to our next paper. This is on a different topic, and the title of the paper is Characterizing, Exploiting, and Detecting DMA Code Injection Vulnerabilities in the Presence of an IOMMU. This paper is going to be presented by Alex Marcuse, who is a recent PhD graduate from the Technion and works on fast and secure kernel networking. So please go ahead with our presentation. Thank you.
Hi, my name is Alex, and I'll present our paper, Characterizing, Exploiting, and Detecting DMA Code Injection Attacks in the Presence of an IOMMU. First, let's start with DMA. DMA, or direct memory access, is a common hardware feature that allows an attached device to access the main memory without involving the CPU. That's devices like GPUs, SSDs, network cards, USB dongles, and many others. DMA also allows a malicious device to read or modify memory that it was not supposed to. This is called a DMA attack. It's a side channel attack where a malicious DMA capable device compromises the system. One notorious example is this thin FireWire unit, which is basically a Lenovo ThinkPad with a FireWire adapter and can be used to take over a target machine. You just approach the target machine, plug in the dongle, and gain control. Easy enough. To prevent arbitrary access to the memory, modern systems have IMU hardware. The IMU works for devices just like the MMU works for processes. It provides virtual memory support for the attached device, meaning that the device can access only pages that are listed in the IO page table, and the page table is controlled by the operating system. So within an IOMMU, the device can access the main memory only via IO virtual addresses, IOVAs. And this prevents the device from accessing any memory pages that were not explicitly set up by the operating system. And this way, the IMU is supposed to prevent DMA attacks. First, let's see an example of how IMU is used in the DMA API in Linux, and then I'll explain briefly why IMU is insufficient to provide security. This is an example of a sent packet. First, the device driver maps the buffer. That's the virtual address of the buffer in red. It allocates an IOVA. It updates the DMA map operation. Updates the page table. That's the blue box on the side. And now we have a mapping. Now the red virtual address and the yellow IO virtual address point to the same physical page. Next, what happens? The device reads the buffer using the IOVA, which populates the IOTLB. The IOTLB is has the same function as a TLB for MMU. It provides fast lookups for translations. Now, when the operation is complete, the device driver unmaps the IOVA. It removes the entry from the page table, and it flushes the IOTLB. So without flushing the IOTLB, the device can still gain access to the physical page because of the fast lookup. We flush the IOTLB and thus prevent the device from accessing this physical page, and we free the IOVA. Now, a problem is the problem, and the problem is something that's called a sub-page vulnerability. In the case of IO, many packets are much smaller than a whole page. It can be like an ARP packet, an ICMP, DHCP, any control packet. And in this case, a small chunk of the page is actually used. But when mapping it, the whole 4K is exposed to the device. And unsurprisingly, there were a couple of projects recently. One of them is the Thundercloud project, and it was showcased in NDSS in 2019. That shows an FPGA that can masquerade as an Intel NIC, and among other things, and gain access and act as a malicious device and compromise the system. Another was a work by Kupfer in his master's thesis, where he was able to take advantage of a DMA vulnerability bug in the FireWire device driver and actually execute a code injection attacks on the target machine. So the problem with these two jobs, what is missing is that there's no structured way. We don't know how to find new DMA vulnerabilities. We don't know how to assess a DMA vulnerability. Is it something that is very dangerous or not? And the most troubling one is we know that there are vulnerabilities, but how many are there currently in the operating system that we use? How leaky is the ship? And I'm here to try and answer some of these questions. So first, we'll talk about characterizing the subpage vulnerabilities and the code injection and attack attributes. And then we will talk about the rest of the contribution. So subpage vulnerability has 4 types as we see it. One is when a device driver for some reason, maps its own metadata because it collocates the IO buffer and its metadata on the same page. But more often what happens is it's by OS design. And examples are FreeBSD and Windows, where and macOS, where the IO metadata sits just in front of the IO itself. So there is no way actually to map the IO without also mapping the metadata. The third type is when you have two IOVs mapping the same physical page. One problem with this kind of vulnerability is when you unmap one IOV, the device can still access the same physical page because it can use the second IOV, which renders the unmap operation essentially useless from a security standpoint. And lastly, we have the incidental exposure. This happens usually randomly. Well, the first three are easily detectable, detectable with static analysis. The last one has a random nature. What happens is an IO buffer is allocated and another buffer of a similar size is allocated from the same page. So when the IO buffer is mapped, all of the other buffers that reside on this physical page are also exposed. And we see how it can become a problem in the next slides. So let's see an example of something live. One example is NVMe fiber channel driver. And in the init request, well, when the host wants to read something or write something for a storage device via the fiber channel, the communication happens via DMA. And in this case, what happens is this command data structure, it's 96 bytes long, is mapped to the device. The second thing that happens is the response is also mapped, and its size is 32 bytes, sorry. And it allows the device to write to that page. So innocuous enough, but when we look into the data structure, we see that the command and the response both reside one next to the other, and essentially allowing the device both read and write access to the same page at the same time. And it also exposes all the other fields in this FCP operation data structure. One of those being FCP request, which contains none other than this callback pointer, which when overwritten will allow the device to effectively gain control of the machine, for example. Which leads us to the attributes needed for successful code injection attack. So you need three things. You need the virtual address of the malicious buffer. So how do you override this callback? And with the both read and write access to this page, we can learn the page address, the CPU address of this page, because it's one of the fields. One of the fields points to the head of the data structure set. The other thing we define is the callback function to override. And the third thing, we need an opportunity, namely that once the callback function was overridden, it will not be reset and instead be executed by the CPU. And that's exactly what will happen in the case of the NVMe fiber channel operation. Next, now we see how dangerous subpage vulnerabilities are. Let's talk about detecting them. So we provide static analysis for the first three types, dynamic analysis for runtime analysis of your system, and we provide a kernel 5.0 analysis showing what kind of numbers or how many vulnerabilities are there today in kernel 5.0. We call our static analysis SPADE, and it works recursively. It starts from a DMA map operation, and that's an example. We see that pointer is mapped, and we look up and we see that it's a void pointer, which is kind of useless. But let's see where's FC DMA map signal function is called. and we see that we find it one example in NVMe init request. We find that the pointer actually is an op pointer, and if we scroll up the screen, we find the name of the data structure, and we analyze this data structure with tools like PA-hole. We find callbacks inside of it, and thus we find the vulnerabilities that we were looking for. Second, we have DKSAN. It's a runtime analysis used on a kernel address sanitizer, and you can read more about it in our work. And she provides these 4 types of vulnerabilities where a buffer is mapped randomly, in essence, and you find multiple examples of non-IO buffers being exposed. Both tools are open source. You can find them on GitHub. And finally, we provide a new compound attack. So the example is Linux kernel, where an IO buffer has SKB shared info, and it happens for specifically for all network buffers, and it contains a callback function. The problem is that it's not enough. We have no opportunity because the structure is overwritten after the DMA map, and the problem is we don't have the CPU address. And because we have no more time, I can't go into details of a DMA attack, of a compound DMA attacks. So I urge you to read our paper. Thank you.
All right. Thanks very much, Alex. This is really interesting work. And let's check the questions. There's no questions so far on the Slack channel thread for this paper. So I'm going to start with one myself. Is that, but when seeing this, I was wondering, are we bound to go down the same rabbit hole of attacks and mitigations fighting each other as we already have for control flow hijack problems triggered by the CPU, or is IO different in any way that makes this problem either more difficult or simpler to tackle?
So it's different. So that's why we see that the vulnerability is there. We see that IOMU is not sufficient to protect us. But there are other ways, and it kind of my research goes backward because we started a couple of years ago with the defense. And so the essence of security here is you have to isolate your data and metadata, and it's in the programmer's hand. So once you allow the device to see only the data, and eliminate any exposure, and that's why we provide the tools and the theory and the analysis. Once you have this, you can build fairly secure systems. So mainly, the only thing that the device can still do is a type of talk-to attacks, where you show one type of data, and then you allow the CPU to make some decision, and then you modify the data. But other than that, there is no when we eliminate the callback function, there is no way for the device to make you execute any other code. And the way to do it is memory segregation. And again, it's the other papers that we've worked on in the recent years.
Yeah. Okay. Thanks. So, I mean, we need to switch over to the next paper, but one really quick follow-up question that I have about this is, do you think that we should be using the code annotation tools that Linux already has to make sure that without changing the hardware, we can deal with this by segregating data structures, or do we need much more than that?
Segregated memory should be enough. Hardware, there's a lot of works, and we have nearing, the end of Moore's law, and leads to many of the papers that we've seen today. But for this problem, software is enough. Just that's my research. Unlike yours, if you're, let's break things up and build it anew. And like, okay, this is the limitations of the hardware that we have today. And so I believe that yes, we can have secure compute with untrusted hardware. Today, just some modifications.
Thanks very much, Alex. Really cool work.
Thank you.
Thank you. All right, so with this, we are going next with our last paper of the session, which goes with the title Rocket.io, Direct IO Stack for Shielded Execution. And this paper is going to be presented by Jörg Thalheim, who is a PhD student in TU Munich in Germany, working on operating systems and especially in OS and hardware-based virtualization. He will be looking for a job next year, so you will have a great chance to discuss future opportunities with him during the rest of the conference. So please go ahead with the presentation. Thank you.
Hello, my name is Jörg Thalheim, and in this talk, I'm going to present you Rocket.io, a direct IO step that we developed for trusted execution environments. So Rocket.io is around the question, how can we protect the user application when it runs in an untrusted cloud from both tenants and cloud operators? Luckily, if we look into modern CPUs, we see that most of them come with something called trusted execution environment, and also cloud providers are offering these technologies to their clients. A trusted execution environment allows us to do the following. You can run an application in a protected environment, and from there, not the operating system or other tenants in the same host can access the application in the memory. However, when we want to do something like a system call, we need to leave this trusted execution environment. This is done in a word switch. After that, the actual system call can happen, and when we return to the application, we have to do another word switch to get the result into the trusted execution environment. It turns out that this word switch is 5 times slower than the actual system call. To counter that, in the past, so-called switchless designs have been proposed. There are 2 of them that I want to present here. One is based on the host operating system, and the other one is embedding a library OS. The host OS version works like this. You have the application running inside the trusted execution environment, and it's interfaced with an asynchronous I/O interface. Whenever it wants to do a system call, it would do though in a system call request queue, and an I/O thread running outside the trusted execution environment is then processing the system call and put the result into a system call response queue. Library OSs work similarly. You also often have asynchronous interfaces, but on top of that, they put more of the OS functionality inside the libraries so that they only interface with the host operating system through low-level interfaces such as FOC devices or NIC TAP devices. We can see that both approaches somehow avoid word switches on the I/O path by having some unconditionality. However, they still have some problems. For instance, there's still operating system of the host and the I/O path as a bottleneck. Then they need dedicated I/O threads that need to be tuned according to what the application pattern looks like. And then there are additional data copies. For example, if you have the data inside a trusted execution environment, you need to first copy it into untrusted user space before you can give it to the operating system. On the other hand, libraries approaches often only provide you with a subset of the Linux API, which then imposes problems when you want to port applications to this environment. Rocket.io, on the other hand, combines the libraries with direct IO interfaces. This works like this. So the application talks to some system call interface, and this goes then to libOS. This libOS, in our case, provides full Linux compatibility, as I will show later. And as well, it's connected to a direct IO interface that can talk to the hardware directly through shared host memory. This allows us to bypass the OS and perform less copies and other optimizations, as we'll show later. Just as a preview, here I have a little benchmark that we did. So you can see here on the x-axis, this system call is implemented for in an asynchronous and synchronous manner, as well as direct IO, where we talk directly to the hardware. And this is compared with the native execution where the application runs outside the execution environment. So you can see here that synchronous and asynchronous is significantly slower than the direct version. So we can see that direct IO gives us a significantly performance advantage here. With this in mind, I want to go further into the design. This is divided into 3 sections. First, I want to show you how the I/O stack is separated from the host, how we handle hardware events, and how we can optimize the data path. First, how do we become independent from the host operating system? So that we use the following technique. For the network access, we depend on something called DPDK, which allows us to directly access network interfaces from within the trusted execution environment. However, this has some disadvantage because DPDK itself doesn't provide any TCP/IP stack, and also doesn't provide the socket abstraction that applications expect. For the storage side, we use SPDK, which is the equivalent to access NVMe devices from user space. Also here, we have no file system support from their side, and also no file abstraction in this case. But the question is, how do we maintain compatibility with these low-level interfaces for existing applications? And here the answer is we provide libc, which is linked against the application, and it also provides the Linux API. We're using the following trick. We have a library OS called the LKL. So this is actually a library port of the Linux kernel. So this gives us basically all system calls that you find in Linux itself, as well as the network stack and file systems that you can find on Linux. This under this layer, we implemented DPDK and SPDK as drivers that they can, and they provide their functionality then to the network and file system stack. This allows us to bypass the host and access the hardware directly. Now a bit about how we handle I/O events. So traditionally, if you have a network driver, the NIC will send at some point NICs interrupts to the NIC driver. This allows them to, so the NIC driver knows when he can insert more data into the queue, as well as when there is data in the receive queue. However, this would cause world switches because we cannot receive interrupts directly inside the execution environment. So the solution here is to go for polling. And the thing about polling is that many modern network drivers use polling anyway, because there's so many interrupts that polling at some point is more efficient than handling interrupts. So when the TCP/IP stack wants to send data, it would just send them to the send queue. And when it wants to receive data, there's a polling thread that will watch for the receive queue, and it will also watch for the send queue in case there's data removed from there. And so it can notify about both events the TCP/IP stack. So this works then also similarly for file systems and the clock device. And yeah, we use polling then in this case. As a last point in the design section, we also did some optimizations to the data path itself. So for that, I want to show you what a naive implementation for a libOS would work like. So if you have a write system call, we need to perform a copy for the reason that the write buffer that the application uses and write needs to be reusable after the write return. And we cannot write every we cannot write through every write to the hardware itself, because that would be quite slow. So what happens if later at some point when we have enough data, there must be a second copy that goes outside the trusted execution environment, and it would be perform a second copy, which is something we actually want to avoid for performance reasons. So how do we do that? Here's the same thing shown from the network side again. So before it would work like this, we had to have the TCP/IP stack, and then when it wants to copy data to socket buffers, it would then have a second copy when we want to actually write it to the network interface. So what we did is we modified the TCP/IP stack of Linux to do the following. It would allocate the already encrypted network packets and write them directly into untrusted memory, where the hardware can read them. And then when we actually about to send the data, we no longer need to do a copy because we can just reference it. And this works then similarly for encrypted blocks that we want to write to block device drivers and allows us to save a copy. With these design decisions in mind, I want to now show about what we have done for evaluation. So we have some synthetic benchmarks. For example, for storage we use FIO, and for network we use iPerf. And then we also have a couple of real-world applications like SQLite, Nginx, Redis, and MySQL. And as a baselines, we have the native version of Linux, so the application running outside the normal Linux. And then for the secure baselines, we picked Scone, which is representative for host-OS-based SGX enclave, and then we have SGX-ACL, which is also library OS. In the interest of time, in this version of the talk, I only will show you MySQL, and the longer version you can also see it on the other benchmarks. So when we evaluated MySQL, there was something interesting happening. So we can see here on the y-axis the throughputs in seconds, and on the x-axis the different systems, native, SGX, ACL, Scone, and Rocket.io, and the same thing for the latency. And we see that SGX, ACL is fast, and Rocket.io is faster than both native and Scone. So what did happen here when we looked at the system calls itself of the benchmark, we saw that few text in the native version is faster than is more often used than any other system call, and this is because MySQL performs table locks whenever you do a query. So it turns out in our case in libOS, few texts are implemented in user space, so and context switches as well, so it can fast switch between the different query threads in MySQL, and this gives us a performance advantage in this case. So with this last result in mind, I want to conclude my talk. So what have we learned today? That SGX implementations are not designed for high performance I/O. The OS is still still a bottleneck in the I/O path. I/O threads are requiring tuning to find the optimal number of threads. Then there's still additional data copies that can be avoided. Rocket.io, on the other hand, provides fast and transparent access to I/O devices. We maintain full Linux API compatibility, and it's performant, and you can download it from here on this link. And with this, I want to thank you for your attention and end my talk.
Thanks very much, Jörg. That's a really nice piece of work. So we do not yet have any questions on the Slack channel. So in the meantime, I was just wondering that I think that this is a really clear example of how fine is the line that we have to walk for trading off between performance and security. And I was wondering, how do we make sure that, for example, this IO stack partitioning doesn't open up new side channels? So for example, cases where the host could be reading these SKB socket buffer contents to infer information about the application state.
Well, the thing is that eventually you need to write all this information anyway to the hardware, so you need to make sure that that's encrypted and beforehand, and also make sure that the attacker cannot tamper the data. So it's just put out a bit earlier than that. It could leak more information about what type, what part of the file system is used more. For example, if you have the page cache. But yeah, that's mainly about that. We could also get this information if you, for example, lock pages and let the MMU leak this information in SGX itself.
Okay, thank you. So we have another question on the Slack channel from Marius Kogias, and he says, thanks for the great work. How would Rocket.io compare with SafeBricks for running network functions?
How does it compare with what?
SafeBricks for running network functions.
I'm unfortunately not familiar with SafeBricks.
Maybe I can comment on safe breaks then, if
Okay.
you don't mind. Yeah, so I think so. Safe breaks is basically a very customized and secure version for running network functions. Whereas what we are providing is a generic stack that not only can be used for network appliances as well, but also for entire storage systems as well. And as far as I know, SafeBreaks is not building on direct IO technology, right? So it is only using enclave, but it still uses OS on the path, right? So that is the major difference. And yeah, that's that's a very high level difference. Yeah. Okay. Anything else? If
well, I'm not sure that we all came silent. So,
okay.
If we don't have any other questions in the Slack channel, I would. Sorry,
there's one question here.
That's the one from Marius that we just went through. Yeah. So I have one last question, and then we can wrap it up. Is that I was wondering about a much higher level, whether we want to move an entire network and file system stack into the TE, when previously we had a much smaller application that was running there, and potentially it has less potential for vulnerabilities. Like, how do we need to think about that that idea of moving much more code into this TE TCP?
So it's also it's not just more code, it also provides some advantage. For instance, it doesn't expose the application that might be not designed with SGX or with any other trusted execution environment in mind. And usually you have, if you expose the application to every system call of the host, you might actually increase your attack surface, because you can, if you implement, for example, the OS secure once, then this is done, but you don't need to rethink the security for every application that you run in the end in this environment.
Okay, thanks very much. That's a really interesting answer. So thank you very much again, Jörg, for your work. And I would like to thank everyone, every one of the authors of these papers. I think these were 6 very interesting papers that we had here. And well, that's the end of our first session. And I hope that you will enjoy the rest of the conference very much. So see you around.
Bye, thank you.
Okay, maybe Vasya can take over now. Yeah.
Hello, everybody. So, hello. Hi, Willie. Animesh, are you here? Excellent.
Yes. Hey.
Hello, welcome. How are you? Okay, so are we going to start right away, Antonio, or do you want to take like two-minute break?
No, I think let's go ahead.
Let's start. Okay, excellent.
Thank you.
Okay. Hello, everybody. Welcome back to the second day of the Ask Me Anything sessions. So I don't have anything more to say. I think I will just pass it over to Animesh and Willie.
Thanks a lot, Salike, and welcome everyone to Ask Me Anything with Willie Zofnapol. Willie, thanks a lot for being with us today. Also, brief introduction about myself. I'm Animesh Trivedi. I'm assistant professor at Vrije Universiteit in Amsterdam. And generally, I do research in a broader area of storage system, distributed systems, and use of high-performance networking to build efficient distributed systems. And today, we are very happy that we have Willie Zofnapol with us. Willie was born in Belgium, and he studied at Ghent University before completing his master's and doctorate studies at Stanford. He spent almost 2 decades at Rice University in the United States before serving for 9 years as head of EPFL's School of Computer and Communication Sciences. Willie joined the University of Sydney as Dean of Engineering in 2018. And as you can probably guess, his research interests are in operating systems and distributed systems. He is a fellow of ACM and IEEE, and he has received numerous awards, multiple best papers, and he has co-founded multiple startups, including the recent one, iMimic and Bugbusters. Both were acquired by Cisco. Willie, thanks a lot for joining us. And I'm not sure exactly what time zone or what time it is, probably late evening.
It's 9 here, 9 p.m., 9:20 p.m.
I hope we can run an interactive and fun discussion session with you that will keep the energy going, and we can just get started with. We already have actually a few questions on our Slack channel. Let me scan through. Okay, let me start with the question with the highest number of votes. So Pramod Bhadotia from TU Munich is asking, your relocation to EPFL was a catalyst event to accelerate systems research in Europe. And you further co-initiated EuroSys to strengthen the community. So what advice would you have for the EuroSys community going forward?
Well, I guess do good research. That is the core of everything, however simple it seems. You have to do good work and try to produce good students and try to find positions for good students in Europe. It's occasionally a problem. That's sort of the core of any research endeavor, whether it's EuroSys or anything else. One thing that I sort of feel about the conference is that, well, it's in Europe, of course, and that sort of makes it unique among systems conferences, but there's maybe also a way of making it more unique in the way, the type of conference that it is, that I feel like it shouldn't be an SOSP lookalike contest. It should try to be different. And maybe advice for future program chairs or something like that. That is my view. I think if you want to be successful, first you copy and then imitate and then change. And I think need to be a little more bold there. That's my feeling.
Yeah, I think so. Some of these themes actually we saw in the opening remarks today, right? Like at least half of our authors are student authors. So I'm guessing we are still a young research community, and promotion of junior students and faculty members is definitely probably a way forward. A related question on the theme of EuroSys working in Europe and how to position is from Saurabh Bakshi from Purdue. And he's asking that you are in a unique position to have been done systems research in US, Switzerland, and now in Australia. So what are some silent advantages and constraints for doing systems research in these 3 locations? Or furthermore, what potential advice you may want to give for the young, fresh masters or PhD students who are considering to work in one of these 3 continents?
Well, there is obviously no reason why you couldn't do good systems research in any location, in a sense, you know. I mean, it's whether it's in the US or in Europe or in Australia, it's the same thing. And certainly now, with sort of the availability of cheap computers and cloud computing, you can basically access tremendous resources from everywhere, which certainly when I started was not the case. When it's actually an interesting war story. When I did my PhD, there were 3 Sun Microsystems workstations outside of Sun Microsystems, and you know, you had to have access to those to sort of do that kind of work, like I did for my thesis. Now you can do that from everywhere. Now, why is it more developed in the US? than in Switzerland or in Europe, and more than in Australia. I think sometimes there's just initial conditions that, I mean, why is most of the innovation in IT in Silicon Valley? Well, because the initial conditions were such that it happened there and it didn't happen somewhere else, and it's very hard to catch up, although not impossible, as you can see with some regions like Seattle, who's now very innovative too. So there's that. I mean, in terms of advice to young people that want to study or want to become professors, for the ones that want to study computer systems, I think you should look at the institution and the people at the institution and not at the geography. I don't think the geography matters for that. For the people that want to become academics, it's a little more tricky. You want to be in a place where you know your work is going to be appreciated, and especially if you're in a tenure track system, you want to be in a place where you know that if you do good work, you're going to get tenure, basically. It's as simple as that. So, I mean, in the US, I think that's pretty much the case. I mean, in Europe and also in Australia, there's still many places that look at journal publications as superior to conference publications. It's certainly not true in our field. In fact, it's almost the opposite. So that I think you want to be a bit careful about. Now, you can also change things. I mean, I don't think, sort of to rephrase what's said in the previous question, that I was a catalyst, but you can change things. I mean, basically, before I came to EPFL, there was not much in the way of systems research. There was some, but not sort of in the traditional, what we think of as systems research. And, I felt like I could change, the criteria by which people got tenure and by which people were hired. And I think you can do that in other institutions too. So it's not an impossible quest. It can be done.
So I feel like there's a story behind that. So why did you choose to join EPFL? As you said, right, there was not much systems work. So what was the appeal there? So
it wasn't so much systems per se as so I had been in the US for a long, long time, and during that time, I had several times I had the opportunity to return to Europe, and these things usually sort of stopped, and they sort of stopped at the point where I said, well, if you want to be a good computer science department, you have to promote young people, you have to have a tenure track system, you have to have conference publications considered as important as, so that happened to me several times. And then I'd sort of given up, basically. And then I visited the EPFL and I interviewed, and the president there said, well, this is exactly what we want to do. We want to have a tenure track system that promotes young people. We want to have a graduate program that produces competitive PhD students. And so I felt sort of taken at my word, and I thought, well, okay, let's try this. And so it did work out, I have to say. I'm very happy about what we were able to achieve there.
Absolutely. So we have a little bit now technical series of questions. Let's just start with a bit of high level. So Antonios Katsarakis from University of Edinburgh is asking, is there any underappreciated line of research which you believe and probably want to share that could positively impact the future of operating system and distributed systems?
That's a tough one. I mean, that's something that's gotten a lot better too, I have to say. So when I was a PhD student, the only conference was SOSP pretty much, and that was only once every 2 years. Now there's SOSP, there's OSDI, there's Unix that's gotten much better, there's EuroSys. So you can basically much more opportunity to publish, and I think that's a good thing. And I don't think that's a bad thing per se, it's a good thing. So in those days, it was certainly much harder to get something in, and there were really very good works that never got published or never got any visibility. I think now it's much better in this regard, and I don't feel like I'm waffling, but I can't really think of an immediate answer. I mean, it seems like, you know, now if you do good work, you can get it published in a respectable place. So I don't know if there's really underappreciated areas of research right now.
Okay, great. Let me pick up the next question, which is also along the research line. So Antonio Barlex from University of Edinburgh is asking, well, 2 questions. So it's getting a bit more technical. You did several work on distributed shared memory in the past. And so what about the idea today? So point being, the network is becoming as fast as cache coherency interconnects. So do you see this as a potential topic of reality? And as a parallel idea, what he's pointing out is that your work on NV, a non-volatile main memory storage system, which actually is one of the, I think the first paper I wrote at the start, right at the start of my PhD, I remember quite well. It's quite nice work. And now you can see that non-volatile main memories are commercially available, Intel Optane, right, as an example. So did you expect that?
Yes, but it didn't sort of come to pass quickly enough for, you know, I mean, I in retrospect, especially the Envy paper was sort of too far ahead of its time. You know, sometimes there's right times for certain things, and this was just too far ahead of its time. I remember that we tried to actually build the system with what were then the early flash chips that were available, and they were just too unreliable and too slow to do anything useful with. Did I expect that this would become commercially available? Yes. I mean, that's why I wrote the paper in a sense, because I thought this was a good idea. I didn't think it was going to take 25 years, because I think that paper was published in the mid-90s or something like that. So, in fact, to the contrary, I sort of thought it was going to become available pretty soon, and it didn't. And DSM, yes, I think shared memory is a good idea. Shared memory is just easier to do than many other paradigms for parallel computing. Now, the methods that we used at the time were specifically to get around slow networks. And so those are probably not applicable anymore right now, but the concept, I think, is still has always been very valid, and I think will continue to be, and more so if these networks are really as fast as cache coherence interconnects, it will become the reality.
Mm-hmm. So a related question from Rohan Puri from Veritas is that, so your thoughts on transitioning a research into practical systems. Is there a particular approach or things that you try to make sure, or at least try to maximize the probability from your side that the systems that you are building or ideas you're working on would actually result in a practical system?
Well, I always try to do things that could be practical, but and I have sort of a theory about what is practical, and I'm sorry to say that many papers don't live up to my theory. This is something that somebody once told me when I did my first company. Said, well, you don't have a good idea until you can explain it to an average master student. You know, if you have a company and they're going to run with your idea, the people that are going to build it, that are going to maintain it, are going to sell it. There's the average people, right? With average, you know, maybe good people, but sort of average people. If they need to be some PhD genius from MIT or Stanford to explain it or to build it, it's just not a good idea. And I think that's where a lot of research suffers, and where our paper selection system also suffers. I feel like we often sort of accept papers because they're very complex, and we sort of think, well, boy, this guy must have been a genius that thought of this. And I sort of feel, well, no, you know, he made it just way, or she made it just way too complicated to have ever be a workable idea. So I think this is something that we could do a lot better on in terms of selection of papers. I think simplicity and sort of understandability is not valued enough in our paper reviewing contest. Now, if you want to do a startup company, and I've done a few, my suggestion is that rather than starting from your research, go and look around and start looking for real problems, you know, that people actually want to pay money to have a solution to, you know, that is, so I occasionally advise venture capital firms, and, you know, sort of they come to me to evaluate some ideas. Sort of the standard mistake, you know, that researchers make is, you know, in these circumstances at least, is sort of, they start their presentation with, here's my beautiful research. And, you know, by that time, the VC has already tuned you out. You know, the way you want to start is by saying, here's a problem, and the problem is important, which in the VC's mind means there's money to be made in solving this problem. And then you give your solution, and then you can talk about your research. But it's sort of the other way around. You know, we sort of think of innovative things to do, and that's good. That's our business. I'm not saying that it's not good. But if you want to go the company route, you have to have a problem, and preferably a problem that, you know, like I said, people are willing to pay money to get it solved. And you have to make that mental switch. And I must admit, it took me 3 tries before I really figured out how this works. So, but, yeah, I mean, maybe now that you get this advice, you can avoid a few of the errors. So that's what I think. I think we need to sort of more focus on simplicity. And then if you really want to go to the company world, then you really need to think of the problem first and not of research.
So speaking of simplicity, so one of the questions yesterday in Ask Me Anything with the Annie-Marie Carmack was, what was her favorite paper? Can I ask you what could be a favorite example from your side, a work or project that you would consider is a very good example of this simplicity?
Well, this is a really old paper, but still very relevant today. But the original Burrell Nelson paper about remote procedure calls, RPCs, you know, that just sort of, you know, how could it be more simple than that, right? The procedure call, we all understand that. I mean, to me, that was a, well, it was a game changer, clearly, but it's also something that you can do something with in practice. You can explain it, you know, to return to my previous comment, you can explain it to an average master's student.
Absolutely. Thanks. So stepping out a little bit from the technical details now, Andrew Moore is asking that, yeah, speaking of the research context. So Ron Pike wrote a famously unhelpful paper on operating system research that did not much to motivate other work such as Zen at Cambridge, and also ignored a great amount of work done in Europe, Minix, Amoeba, etc. Is there an advantage of not being crucible or being aware of this kind of work to enable new thinking?
I have to be a little careful what I say here because Rob Pike now lives in Sydney and I see him on a regular basis actually. So I don't want him to clobber me next time I see him. I mean, there's definitely an advantage to trying to think out of the box. And sometimes, you know, you can get so caught up in what is the hot thing of the day that, and, you know, I feel like there's also, I'm sorry, this is an old fart comment, but I feel like there's just so much pressure on the young ones these days to publish, publish, and publish that, you know, you almost have to sort of do the short-term thinking. I think it certainly would be nice if we could more extricate ourselves, and especially the young ones, from this sort of heavy pressure. So the best thing I ever did when I got tenure at Rice, I decided to go take a sabbatical as far as possible away from everything. So I went to Australia, actually. That was my first visit to Australia. And besides, and you know, this was sort of before the days that there was the internet and email. Well, email was there, but it was not so common. You know, I think that really gave me a chance to sort of take a step away from the day-to-day. And that's actually where a lot of the ideas in trademarks came from, the things that I was able to think about. And then I spent another 6 months with Mark Shapiro in INRIA, in Rocancourt at the time. And again, it sort of was sufficiently separated from the normal day-to-day thing. So I actually think that Europeans don't take enough sabbaticals. You know, you should sort of really get out of your, you know, hole and see what else is there in the world. And even if it's only like for a summer, you know, to spend the summer in Silicon Valley or something like that, I think that's a really refreshing experience.
I think we have to wait probably until the world is in a better place before we could start traveling again.
Yes, right now it's not a good thing.
So, so next set of questions, perhaps let me see if I can combine together. So Pierre-Louis Roman from USI Lugano and Andrew again. So they're asking that, so I heard both Animere, Kermarek, and you say that computer scientists would benefit from being nicer to each other. So essentially the spirit of collaboration.
Absolutely.
So, so where do you see the most negativity? Or specifically, Andrew is asking, why are systems people in particular notoriously mean to each other?
Okay, let me tell you something that I don't think ever became very public, but at one point, the National Science Foundation in the United States, when you submit a proposal, when you review it, you get to mark it from 1 to 5. So, you know, that sort of gives you 5 is the best. And so they did a study of the averages and the variances in different fields. And computer science on a scale of 1 to 5 was 1 point on average lower than the lowest of any other field. And on top of that, the variance was 1 point higher than the highest of any possible field. So this is a real problem, you know, and where does it come from? I have this sort of perverse theory that it comes from our training to debug things. We always want to debug things. We want to find faults in things, and we sort of get obsessed with the little fault, you know, where you say, well, the overall thing is fine, but you know, there's this little problem here. And so we write these reviews, say, you see this all the time in reviews. And I say, well, it's a nice paper, but, and then there's sort of 2 pages of drivel, you know, complaining about this and that detail. I think this is a real problem for our field. So when I was still in EPFL, I was on the panel for the senior ERC grants, the most senior ERC grants. And so basically, first of all, the computer scientists would rip each other to shreds, and then the systems people would do even a better job of that. And so I remember thinking, going to the panel, my goal here is going to be to get one systems proposal through, you know, and oftentimes that was very hard, you know, because you have to, sort of people have to get into their mindset that you're being compared to others, right? And if you're much harsher than the others, you've done yourself in, right? And you know, today you're doing somebody else in, but tomorrow he's going to do you in. And we really have to get much better at this and sort of realize that reviewing of proposals and papers is not debugging, you know, it's, you know, trying to see the overall picture and, you know, appreciate it. And some stuff is not good and it should be said. But so, you know, trying to take a more positive attitude, because we really hurt ourselves. I mean, and I see the same thing now, and now Dean of Engineering, so I have a number of schools underneath, sort of all the classical engineering schools, you know, civil, mechanical, and whatnot. And, you know, you're looking to sort of recruiting, and again, they're much more positive, you know, I don't have any other word for it than we are. I mean, it's rare that you find one candidate that all the computer scientists can agree on is actually any good. And I don't know, we really need to learn this. I keep on saying this at every meeting that I go to, and I really would sort of like to encourage the senior people that are listening into this to teach their students that this is how it is, this is how you review papers. And I would like the young ones to really learn this too, because it's your future. You know, if you know, do this to yourself, you're not going to be as successful as you can be.
I guess you already answered the second half of the question where Pierre was asking, do you have any practical examples of things we could try differently? So
I
be
think
aware of
we
the
just
process.
have to, we have to train ourselves and the people that we train, you know, to understand that reviewing is not debugging. You know, it's that's sort of the key thing.
Great, thanks. So Marco Canini from KAUST is asking, what is your advice to young people for choosing problems to work on? Is there a recipe that has worked throughout, or did you see your approach of choosing problem change over time?
I actually have a fairly unusual approach to choosing problems, I sort of let my students choose problems, basically, and I fared very well with that, I must say. I'm not the type that sort of says I'm going to work for 5 years on this, and I just sort of try to work on things as I see them becoming important. So a lot of the work I've done recently is on storage systems, on key value stores, basically Juan Abalmau and Laurent Binchadler's work. And much of that was actually, well, the work on key value stores was in big part originated at Nutanix, the company that I was involved in, because we saw problems there that we thought we could have good solutions to. I think one thing to look for is sort of changes in technology that are fundamentally going to change the operating system or the system software. So right now, in my opinion, the biggest change is the commercial arrival of persistent memory. That's just fundamentally going to change how we do things. In the past too, I mean, in a sense, the trademarks, the DSM, although the networks at that time turned out to be too slow to do what we wanted to do, the reason that we actually looked at it at all is because at that time they became an order of magnitude faster. And so we believed that we could do things that weren't possible earlier. So I think one way is to look at technology. Another way, I think, is to spend some time at a sort of forward-looking company and see what their problems are, and try to see if you can come up with creative solutions to this. Sometimes just things also come out of the blue, out of just pure curiosity. I mean, the other thing I did quite a bit on recently was this causal consistency. I don't know whether it's ever gonna really become practical or widespread, but I just thought it was very interesting, the sort of concept. And that's another, if you find it interesting, probably other people find it interesting too, and it's going to go somewhere.
Great. Yeah, but so absolutely. And I think I also agree the whole persistent memory is, I think, one of the most exciting things to happen. I think fundamentally is reshaping the whole storage hierarchy.
Mm-hmm.
Okay, so really one last question to you. We have talked about your research, your journey, different how things work. What do you do outside work in your free time, if ever you get any? How do you decouple or unplug from the system?
Well, it's getting harder and harder. We're always connected. I like traveling, and I like traveling to remote places. And in Australia, that's quite possible. There's plenty of interesting remote places. So that was actually not the main reason, of course, but one of the reasons that my wife and I decided to come here, that we wanted to see this part of the world. COVID has run havoc with it. We're sort of restricted to Australia, and we wanted to go into the Pacific and stuff. It didn't happen. So that's something that I do. One of the big downsides of living in Australia is that you're 8 hours of time zones away from decent football games. That's a major problem for me. I'm a big football fan, and I like to watch games. I used to play, but I don't play anymore. So I have to get up at some ungodly hour to watch a Premier League game or a Champions League game, which is what I'm planning to do tomorrow morning. So there's that. And I sort of consider myself an above average backgammon player, so I like to play board games, and like I said, I think I'm above average in backgammon, so I find that a good way. The other thing I do once in a while is do puzzles, these three-dimensional puzzles.
Mm-hmm.
I find it's something that it's possible while I'm doing a puzzle for me to completely forget about everything else, just completely concentrate on this. And I don't know, you have to find something to, to get out of it.
Great, thanks a lot. If we were in the conference, we were talking, and then I will ask you more about your soccer, football teams, and your opinions on what's going on recently. But we will leave that for the next time when we will meet. Willie, thanks a lot for your time and participating in Ask Me Anything, and for all the participants who asked the questions. And this is it from us. Thanks for tuning in. And I believe we have a next session of the conference, which will resume now. Thanks, everyone.
Okay. Thank you all. Bye-bye.
So the next session will be chaired by Yuho. Yuho, take it over, please. Can you... Okay.
Okay. Hello, everyone. Welcome to this session. And this session is the distributed system and networking. And in this session, we have 6 great papers to present that covers the wide areas such as the data center network, blockchain, and the distributed transaction, and also the edge computing. And for each paper, we will have totally have the 15 minutes, and you can ask questions in the using the Slack. And the first paper is we'll discuss the paper title is towards the time outlets transport in commodity data center networks, and this is a great paper that will try to have a near zero timeout by using the commodity data center hardware. And so please play the video.
This is Huijun from KAIST. In this session, I'm going to introduce our system named TLT, which improves the tail latencies of transports by drastically reducing the number of timeouts. In data center networks, we still experience packet drops due to numerous reasons. Data centers use shallow buffer switches compared to their link bandwidth reaching 100 G. And microbursts, which are short spikes in network traffic, happen very frequently and cause packet drops. Furthermore, reactive data center congestion controls need 1 RTT to detect and react to congestion, which may generate queue buildups and eventually packet drops. However, why should we bother with packet drops? This is because some packet drops cannot be detected in a timely manner. We rely on retransmission timeouts to recover from the losses. Timeouts cause significant impact on the flow completion times, FCT in short. This is because retransmission timeout, RTO, is much greater than the round-trip time. While average RTT reaches tens of microseconds in modern data center networks, minimum RTO is for few milliseconds. In data center networks, short flows are usually transmitted in less than 100 microseconds. However, when a loss occurs, the sender might need to wait for timeout to detect and recover from the loss. This takes more than 4 milliseconds, which leads to the performance degradation. The most straightforward solution to mitigate this would be using aggressive timeout. In TCP, RTO is calculated by smoothed RTT and the variation of RTT bounded above RTO min. Some research suggests using aggressive timeout by reducing the RTO min to 200 microseconds. Although this may be effective for stable background flows, it is not enough for bursty foreground flows. Our simulation with background flows and in-case foreground flows show that calculated RTO value is much larger than the RTO min, especially foreground flows. This is because transient traffic bursts cause queuing delay, which eventually increases the variation of RTT. Thus, reducing RTOmin is not enough due to the large variation of RTT. Then, what about using aggressive static timeout? Our simulation with 200 microsecond fixed RTO reduces the tail latencies of foreground flows. However, this comes with severe penalties in throughput. This is due to 51-fold increased number of timeout, most of which are spurious ones. Furthermore, this may raise undesirable interaction with network diagnosis. They use timeouts and retransmissions as key features to infer failures. Excessive, spurious timeout may generate false alerts and interfere with them. Some work solve this problem by improving the loss recovery, but they are protocol specific as TLP is designed for TCP and IRN is designed for RDMA. Also, PFC is one solution to prevent timeout by making Ethernet lossless. PFC is widely deployed in Rocky, but it comes with many side effects, including congestion spreading. Finally, some suggested solutions which modifies the behavior of the switch. Unfortunately, they need to modify switch ASIC, so it isn't readily deployable. Our question is, can we minimize the impact of the packet loss in general and deployment-friendly way? Our solution for this question is TLT, which stands for Timeoutless Transport. TLT is a building block for a variety of transport protocols and works without change in switching chips. Instead of making all packets lossless, TLT mitigates timeout by making only some portion of packets lossless. We focus on the fact that not all packet drops have the same impact. For example, assume a flow with 3 packets. When the last packet gets lost, the sender can do nothing but wait for the timeout. After the timeout, the sender will know that sequence 3 is lost and it will be retransmitted. However, in another scenario with also 3 packets, assume sequence 2 gets lost. In this case, the sender can infer the loss from the duplicated act and there is no timeout. From these examples, we can find that only some packet loss may trigger timeout. In TLT, we prevent those packets from being lost. From now on, I'll present the design of our system. TLT is an extension for existing transports for data center network designed to mitigate timeouts. As mentioned at our key observation, only some packet loss can cause timeouts. Thus, we aim to prevent those packets that might cause timeout from being lost. To this end, we mark those packets as important and keep them lossless inside network, while leaving others unimportant. First, the sender selects and marks some of the packets as important to prevent timeouts. To prevent important packets from being dropped inside switches, switches proactively drop unimportant packets to reserve a room for important ones. When the size of unimportant packets inside the buffer exceeds the threshold, it will begin to drop new unimportant packets. In this example, the threshold is 5. As there are already 5 unimportant packets inside the queue, the switch will drop any arriving unimportant packet afterwards. By doing so, important packets will remain lossless inside the network. There remain 2 key challenges in TLT. First, which packet should be marked as important? We should prevent the packet loss which may trigger timeout, but which packet is it? The number of important packets should be minimal. Second, how should we selectively drop the unimportant packet inside the same queue? We can use the queue separation, but this would cause severe out-of-order problem. How can we differentiate unimportant packets inside the same queue? From now on, I'll talk about how TLT solves these challenges. To select packet to mark as important, we should first know which packet loss may trigger timeout. Transport protocol generally fall in 2 categories, window-based and rate-based. We find that the packet whose loss may cause timeout depends on its category. The common example of window-based transport is TCP, and the example of rate-based one is RDMA. Window-based transport controls the number of in-flight packets under the window limit, but the rate-based one controls how fast the packet is injected to the network. Thus, for window-based transport, new WAC will slide the window and trigger the new packet transmission. However, for rate-based one, rate limiting timer triggers the new packet transmission. However, there is one common rule regardless of the category of transport. We choose always to mark all control packets as important. Control packets in general have very small size and carry crucial information. Their loss may trigger timeout even if data packet does not get lost. ACK loss is a great example that may cause timeout. In the example, even if 2 data packets are delivered, timeout is triggered due to the loss of ACK. We can handle this by marking all control packets important. I'll first explain the challenges with the window-based transports. For window-based transport, maintaining self-clocking is critical. Self-clocking means the data packet triggers an ACK packet and it triggers another data packet, and so on. If the self-clocking is broken, the flow is exposed to the risk of the timeout. This example shows the broken self-clocking. ACK triggered by sequence 2 triggered sequence 3, but it got lost during transmission. Sequence 3 should have triggered another ACK here. Our key idea to keep self-clocking is always keeping exactly one in-flight important data and echo packet. To achieve this, we first mark one data packet as important data. When the receiver receives an important data packet, it will mark the ACK of the packet as important echo. When the sender receives an important echo packet, it will mark one outgoing data packet as important data, and it keeps going on. This keeps exactly one in-flight important data and echo packet. One may raise a question here. What happens when the base transport does not allow further transmission? For example, due to congestion window reduction or no available data in the send buffer. In this case, ACK clocking is broken and failed to reserve one in-flight important data packet. To keep this important ACK clocking, TLT retransmit a power packet by marking it as important. To minimize the impact of the retransmission, we also developed an algorithm to adaptively change the size of retransmitted packet. Please check for the paper for details. Now let's talk about the important packet selection in rate-based transport protocols. In rate-based transports, there is no ACK clocking. That is, the whole flow will be continuously transmitted. Thus, assuming control packets are not lost, timeout only occurs at following two cases: at the end of the flow, and when the retransmitted sequence gets lost again. When the packet at the end of the flow gets lost, there will be no ACK or NACK, so the sender needs to wait for timeout. Thus, TLT first marked the last packet of the flow as important. Preventing the loss of the last packet will help the sender to detect the loss before timeout. The sender can optionally mark every end packet as important for faster loss detection, where n can be a greater number than the switch fan-in degree. Second, when the retransmitted sequence is lost again, the retransmission becomes ambiguous. For example, here, the sequence 10 is lost and retransmitted due to NACK. However, if the retransmitted 10 is lost again, the sender can't immediately figure out if the retransmitted sequence is lost. Since NACK does not proceed at both cases, the sender may think that the retransmitted packet is in flight. Thus, TLT marks the first packet during the retransmission as important to eliminate the ambiguity. At Switch, to implement selective dropping at commodity switches, we leverage color-aware dropping. Color is a metadata inside the switch pipeline, and we can map specific DSFA value into color using ACL table. And we can set different thresholds for different colors even in the same queue. We map unimportant and important packets into red and green. We limit the queue buildup of red packets, and if queued red packets exceeds the threshold, it will drop the incoming red packet. Still, green ones can be queued as long as the buffer allows. From now on, I'll show some of the evaluation results. We measure the application response time at the client side using Redis and Nginx web server in testbed. When the client sends an HTTP request to the web servers issues a set operation to the Redis node. While the baseline shows long response time and large variance, TLT shows very stable FCT increase as the number of flow increases. This is the large-scale simulation result with 96 hosts in lib-spine topology. For DC-TCP, when PFC is not used, TLT performs much better than TLP and baseline that use small RTOMin. TLT also performs better than the baseline when PFC is used. Overall, TLT reduced the tail FCT of foreground flows by up to 81%. With Rocky, we also evaluate APCC, RN, and DCQCN. TLT shows better tail FCT for both background and foreground flows up to 96%. TLT also greatly reduces the number of timeouts and PFC pause in many transports. Actually, we find that TLT virtually eliminates timeout and greatly reduces the number of PFC pause. To sum up, I have introduced TLT in this talk. TLT is a building block for existing data center transport to eliminate congestion timeouts, and TLT achieves timoutlessness by making important packets lossless in the network. We plan to open source our simulation code on GitHub. Thank you for your attention, and I'll be happy to take them during live Q&A session.
Hello, everyone.
Okay, hi Jun, are you here?
Hello.
Okay, can you hear me? Okay. Okay, I have one question that you mentioned that you leverage the RDMA as a rate-based example. And my question is, the RDMA is one-sided or two-sided RDMA? And if you have some different impacts on by using different RDMA models?
So for all RDMA models, I consider that the all flows are transmitted without intervention during transmission, which is different from the window-based transport such as TCP and TCP. So for all kind of RDMA transport, I think we can follow the model that I used in the paper.
Okay. So attending any question? Okay, I will check the slide. Okay, another question that I noticed that in your design there is a switch, and the switch have a limited size, the quick, and so you also leverage the proactive drop. So my question is that for the packets that have been proactive dropped, so this packets can be also needed to be retransmit or not?
Yeah, so the base transport will retransmit the proactively drop the packet. So we also measure the performance of the flow using throughput, and we confirm that we do not degrade that much performance.
Okay, so any question from attendees? Okay, very interesting work, and thank you very much. Okay. So we'll move to the second paper, and the second paper is from the Seoul National University, and this paper will discuss the very efficient design in the context of the account-based blockchain. And okay, so please play the video. Thank you.
Hello everyone, my name is Jae-yoon Kim, and I'm from Seoul National University in Korea. Today, I will present Etanos, efficient bootstrapping for full nodes on the account-based blockchain. These days, account-based blockchains like Ethereum, Cardano, Polkadot, Solana, and Algorand have become popular. This is because the account-based model supports smart contracts, a tiny program that allows people to program money themselves. However, the account-based model suffers from a huge storage size and long synchronization or bootstrapping time. For example, Ethereum requires 6.9 terabytes and few weeks to catch a current block with archive sync, and it requires 740 gigabytes and few days with fast sync. The most serious overhead of the storage size and bootstrapping time is caused by the state trie that saves account states. So, before we talk about Etanos, let's review Ethereum to learn some background. Ethereum stores each account at the state trie, of which structure is Merkle-Petrusha trie or MPT. In MPT, the character sequence of an account address determines the path to its account data, and each node is labeled with a hash value. This MPT is implemented by LabelDB, that each node is stored with its hash as a key. Accessing an account requires multiple hash-based LabelDB accesses, which is a main bottleneck of synchronization. And MPT also allows efficient verification. First, it can prove membership with a Merkle proof. For example, we can verify that an account 0x7a1c.df exists in this MPT with a Merkle proof, including branch node 0, extension node 0, branch node 1, extension node 1, and the account, which is represented as bhash0, bhash1, bhash2, bhash3, and bhash4, where b is the LabelDB. Second, it can also prove non-membership with a void proof. For example, we can verify that an account 0x7a14a0 is not in the MPT with a void proof, including branch node 0, extension node 0, and branch node 1, which is represented as b-0, b-1, and b-2, since there is no path to 4 in the branch node 1. If a new node wants to join the network, it has to be a full node by downloading the blocks and reproducing the current block, called synchronization. And there are two synchronization processes in Ethereum. Archive sync downloads all blocks and reproduces all state tries from the Genesis block. Archive sync records all histories of the blockchain, so it takes a huge space and a long time. Meanwhile, fast sync downloads all blocks but also downloads the state trie of the pivot block, that is 64 blocks before the current block, and reproduces only the state tries from the pivot block. Fast sync can reduce the cost of synchronization, but it is still slow because we need to traverse, transmit, and rebuild every node of a huge state trie, which suffers from intensive disk I/O. To accelerate synchronization, we first investigated Ethereum data and observed that most accounts are dormant and only a fraction of accounts are active. About 3% are active for 1 week, and about 5% are active for 1 month. And we also found that once an account is activated, it's likely to be accessed soon again. An account is updated in a week with a probability of 76%, and in a month with a probability of 89%. So, we proposed Etanos that sweeps dormant accounts periodically by an epoch lambda. For example, the lambda can be 40,000 blocks for a 1 week period. We call the last block of an epoch a checkpoint, since it is extremely expensive to traverse a state trie to find and remove dormant accounts. Etanos simply creates a new empty trie every time a new epoch search, and frees it with the active accounts used by the transactions in the new epoch. Because the trie is initially empty, however, so no account is available. So Etanos caches the state trie of the checkpoint as well. If an account is not in the current trie, but in the cached trie, copy it to the current trie. However, if an account neither in the current trie nor in the cached trie, it should first be reactivated before it is a sender or a receiver of a transaction. There are two cases. If it is a sender, it should first restore itself with a restore transaction. If it is a receiver, it is created as a Chrome account, as if we create a new account, then merge later when it becomes a sender. In Ethereum, when someone sends some value to an arbitrary address that does not exist, a new account for that address is created in the state trie. However, we cannot distinguish the created account is new or reactivated. So, we call the reactivated dormant account as Chrome, which can be a sender of another transaction if it has enough balance. If the Chrome account does not have enough balance, it should transmit a restore transaction, which will merge the Chrome accounts with the original account. To avoid cheatings, a restore transaction includes Merkle proofs and void proofs to prove that it is a dormant account and that its last state. Since a Merkle proof cannot distinguish between a Chrome state and a restored state, we use the restored flag to prevent an already restored account from behaving as if it is a Chrome account. A valid state generated by a restore transaction can be expressed during a regular expression like this. If a proof sequence of restore transaction does not follow the regex, it is rejected. Therefore, an attacker has no choice but to follow the regex, but it is only generates a correct state. For synchronization, Etanos downloads state tries of both pivot and the latest checkpoint blocks, and each trie size is small. If we omit to download old transactions before the pivot block, which we call compact sync, we can significantly reduce the storage size and the bootstrapping time. Also, other techniques like LipoPo, omitting less important block headers, the bootstrapping cost can be much reduced. And we think that bootstrapping with less than 1 GB within a few minutes would be plausible for ordinary people. We used the real Ethereum data to evaluate Ethanos. We evaluated 300,000 blocks from 7 million block to the 7.3 million block, where 30.6 million transactions update 4.6 million accounts for 2 months in early 2019. And the experiment was run on the real gas client. We instrumented gas client version 1.9 to implement Ethanos and to compare it with the original gas. And we set the epoch size 40,320 blocks, which is about 1 week, and the number of restored transactions was 198,121. The specification of the host is i7 9700K, 3.6 GHz CPU, 64 GB RAM, and 6 TB SSD. And the client is i7 7770, 3.6 GHz CPU, 16 GB RAM, and 1 TB SSD. And we connect the client who bootstraps and the host who provides the bootstrap data via Ethernet to reduce the impact of network fluctuation on synchronization time and the peer draft areas. Experimental results show that the total storage sizes at the 7th checkpoint are 997 MB for gas and 374 MB for Ethanos, where the state try size of gas is 831 MB and that of Ethanos is 220 MB. Therefore, the total storage size for compact sync will be under 594 MB, which remains almost constant unlike Ethereum that continues to grow. 594 MB would be reasonable for a client to bootstrapping as a full node. We also measured the synchronization time and found that Ethanos becomes tangibly faster than gas in both fast sync and compact sync. The bootstrapping time of Ethanos compact sync is almost constant over time. In summary, Ethanos successfully reduced bootstrapping cost by periodically receives dormant accounts, rebuilds the state try only with active accounts, and restores dormant accounts when needed. Ethanos enables bootstrapping under 1 GB within a few minutes, which would be plausible for ordinary people, and it will allow occasional online users to be a full node whenever transmitting transactions. Thank you for listening.
Okay. Yun, are you here?
Yes, I'm here.
Okay. Hello. Yeah. So
Yeah,
a very interesting work. Yes. So my question is that I noticed that in your design you leverage the checkpoint and you have some many evaluation about the checkpoint performance. So my question is how in your design how to decide the frequency of the checkpoint. For example, this will be on the epoch or it have some fixed interval. So can you provide more details about the frequency of the checkpoint?
Yeah. In our design, we have a fixed period. So the checkpoints are made at the end of each period, and the period is 1 week in this paper. And we evaluated many periods about 3 days, 1 week, and 1 month, and 6 months, and we evaluated them in the paper. So you can check it in the paper, and we think that making the period dynamically will improve the performance of this Ethanos, but we cannot evaluate it all because the evaluation is very hard and takes very time to take many times.
Okay.
Yeah.
So, any question from the attendees in our session? Any question from attendee? Okay, I have another question. I think this is, topic is very interesting, and because I am interested for the checkpoint. So I noticed that in your evaluation, you also leverage the DRAM and the SSD and also hard disk. So in general, when we do some checkpoint, we need to flash the data in the checkpoint into some non-volatile device such as the SSD or hard disk. So this will can support some quicker recovery once have some system crash or power off. So my question is that in your design, your checkpoint will be flashed into the SSD or even the hard disk, because that in your evaluation, I noticed some SSD, right? So when you have some, you need to maintain this data and flash this data into the non-volatile device, right?
I cannot exactly understand, but your question is that why we didn't evaluate with hard disk drive? Is it right?
Yes, I mean that when you aim to complete the checkpoint, you don't need to maintain the checkpoint into the memory, right? So because the memory, so if there is some power off or crash, right, the data will be lost. So you need to flash the data into the non-volatile device, such as the SSD or hard disk, right?
Yeah. And the data of the checkpoint are all stored in the SSD, and not all the data are used for the evaluation, because every transaction uses the data of the state trie, but only there are frequency of the data. I mean, frequently accessed data are tend to be accessed more, and the Ethereum GET client caches those data in the memory. So if even if the device is crashed and the data is cases are heavily lost, but it is okay because all data are stored at the library, and those data will be cached to the memory, and every transaction uses that memory data in the memory, and not in the memory, then it searches for the library of the disk. So,
Okay.
Yeah.
Any question from the attendee? Okay. So thank you very much. Okay. Very good work.
Thank you very much.
Okay, thank you. Yeah. Okay. So the next paper to present is Antonios. The presenter is Antonios. I'm from the University of Edinburgh. And this paper will discuss very efficient distributed transactions. So please play the video. Thank you.
Hello everyone. Today I'm excited to present to you Zeus, a distributed data store that allows for locality-aware distributed transactions. This work has been a collaboration between the University of Edinburgh and Microsoft Research. Let me start by saying that modern distributed data stores keep the data in memory, replicated and sharded across numerous nodes of a data center. These data stores are the backbone of emerging transactional workloads that reside in the cloud and demand distributed reliable transactions with strong consistency for an intuitive behavior and fault tolerance in order to remain available despite node failures. Moreover, these workloads mandate high performance to satisfy the numerous concurrent requests. However, it is well known that traditional distributed reliable transactions are very expensive. Fortunately, we observed that many transactional workloads, including network functions and peer-to-peer payments, exhibit dynamic locality. To better understand this, let's see an example of a cellular control plane, which manages phone connectivity and handovers among base stations. This application exhibits locality because every phone user repeats transactions involving the same phone context and its nearest base station. However, the locality is dynamic and changes at runtime. For example, if the user commutes, its base station changes through a handover operation. So a key question here is, can state-of-the-art reliable data stores exploit this dynamic locality? Let's see. State-of-the-art reliable data stores rely on static sharding, where objects are placed randomly on fixed nodes. This allows to easily locate and access objects and affords reliable transactions regardless of the workload's access pattern. However, the reliable transactions are expensive, mainly for two reasons. First, most of the accesses are remote, and some of which are also necessarily blocking, for example, if they involve control flow or pointer chasing. Secondly, related objects reside on different sites, and thus they require a distributed transaction commit, which is especially costly under the uncertainty of faults. Overall, we can conclude that state-of-the-art data stores cannot exploit locality, and therefore they offer expensive reliable transactions. To resolve this issue, we propose a distributed data store which is inspired by hardware transactional memory and exploits locality for fast, reliable transactions. The basic idea behind Zeus is as follows. Each object has a single node owner which stores its data and has exclusive write access to it. The owner can change dynamically and is tracked by a replicated directory. This allows for two things. First, the coordinator can execute a transaction by first acquiring the ownership of the transaction's object. This allows for an efficient single node commit. Moreover, the ownership stays with the coordinator, and therefore future transactions on these objects can enjoy local access. Great, but let's see the exact steps to execute the transaction. A transaction in Zeus proceeds in three main steps. First, the coordinator executes the transaction as the owner, which means that prior to accessing an object, if the coordinator is not the owner, it needs to get the ownership. But how can it get the ownership reliably? There is an ownership protocol for that, which lets the coordinator to get the ownership from the current object owner, but also ensures that the directory replicas are kept consistent. For brevity, we call all of the directory replicas and the current object owner as arbiters. And the ownership protocol proceeds in three steps. First, the coordinator sends object's ownership invalidations through one of the directory replicas to all of the arbiters. Secondly, the arbiters acknowledge the coordinator directly. And at this point, the ownership is acquired by the coordinator, who can proceed with its transaction. Finally, and out of the critical path, the coordinator sends validation messages to all of the arbiters to inform them about its ownership acquisition. Note at this point that the ownership protocol is across object concurrent. Meanwhile, conflicts to the same object are resolved through logical timestamps, and we have also ensured that the ownership protocol is idempotent and can thus guarantee fault tolerance. Similarly to our previous work, Hermes. We have also verified the correctness of the ownership protocol under conflicts and failures. So let's get back into steps to execute the transaction. Remember that once the ownership is acquired, it stays with the coordinator, which when combined with the locality of transactional workloads, this means that the coordinator is already the owner in the common case and simply can proceed with local access. Once the execution of a transaction is finished, and because it is done so using the ownership, the transaction can commit locally, simply by using a traditional single node commit. However, note that at this point, any updates performed by the transaction remain local to the coordinator, and if the coordinator fails, those updates will be permanently lost. Therefore, we have a third and final step to complete the transaction. This is a reliable commit where we simply update the replicas. Great, but how efficient can this reliable commit be? Let's see. First, because the transaction is already committed, the reliable commit does not need to perform any conflict resolution, and therefore it can complete transactions fast. Simply, the coordinator sends updates to the replicas and waits for all of the acknowledgements before completing a transaction. Note at this point that read-only transactions have no updates, and therefore they do not even need to execute a reliable commit. Secondly, because there is no need for conflict resolution, this means that reliable commit is non-abortable, and therefore it allows for pipeline transactions. In short, subsequent transactions can proceed without waiting for the replication of previous transactions. Instead, they use the local state with certainty and issue updates. To ensure that the replicas apply those updates in order, the coordinators also sequence those updates. Finally, and similarly to our ownership protocol, we have ensured that each and every step of the reliable commit is idempotent and can be replayed by any of the participants, therefore guaranteeing fault tolerance. So overall, we show that the reliable commit is very efficient, and we have also verified its correctness under failures. So to recap, today we show that locality-aware transactions in Zeus proceed in three main steps. First, the coordinator executes the transaction as the owner. This means that occasionally, when the coordinator is not the owner, it needs to get the ownership, which can occur after just 3 hops, as we saw. However, in the common case, the coordinator is already the owner and proceeds solely through local access. Because the transaction is executed with ownership permissions, it can commit fast locally, and at this point, any read-only transactions are also completed. For write transactions, there is a third and final step, a reliable commit, which, as we saw though, is very efficient. Because it is non-abortable, it can complete fast after a round trip and is pipelined. Finally, in our paper, we also show how by extending this reliable commit with just a single extra message, we can allow for local read-only transactions from all of the replicas, even though they might not be the owner. Great, but does this translate into performance? We have evaluated Zeus in a 6-node cluster and using 3-way replication over 40 gigabit network. In a handovers benchmark and using a real-world observed locality, Zeus achieves 10 million transactions per second, which is within just 9% of the ideal with all local access. We have also evaluated Zeus in a TATP benchmark while varying its locality. And we also compared with the state-of-the-art static sharding approaches, such as FAST and FARM, which use a higher-end networking of 56 gigabit with RDMA. As we can see, Zeus achieves up to 43 million transactions per second, which is 2 times the performance of the state-of-the-art, despite its lower-end networking. You can find out many more results, including measures for the ownership and latency in our paper. So to conclude, today we show that state-of-the-art distributed data stores provide reliable transactions based on static sharding. Therefore, they cannot exploit dynamic locality that's exhibited by many transactional workloads. Instead, they incur expensive remote access and costly distributed transaction commit. To resolve this, we present Zeus, a novel distributed data store that is based on dynamic ownership and offers reliable transactions that exploit locality. In the common case, transactions in Zeus proceed using local access and through a single node commit, which is fully local for read-only transactions, while for write transactions it is fast and pipelined. We show that Zeus achieves performance in tens of millions per second and up to 2 times the performance of the state-of-the-art. As a bonus, Zeus provides better programmability than the state-of-the-art, and you can find out more about it in our paper and in Zeus web page. Overall, if you have reliable transactions with locality, then you should definitely consider using Zeus.
Hello, my name is... Okay. Hello. Antonios, are you here?
Hello?
Hello,
Yes.
can you hear me?
I
Okay,
hear.
hi. Yeah, okay. Very interesting work. Okay, we have a question from attendees. Hi, Paul.
Can I speak? Can I ask the question?
Okay.
It's a very nice work. Thank you very much. But my question is, you are acquiring ownership of various objects. Imagine if there is a conflict between ownership. For example, transaction A has already acquired ownership on object A, while transaction B already has ownership over object B, and they want the other ownerships. So there could be a conflict, and how you end up, it's more like locking, right? Ownership is more like locking. So I want your views on that. I'm sure you would have addressed it, but I'm interested in knowing it. Thank you.
Yes, that's a great question. Ownership is very similar to locking in that sense, and you could have situations like the one that you described, where you can have deadlocks. So this is typical for all of the transactional works, and we use a fairly simple technique, which is not very sophisticated, to resolve deadlocks through through a typical back-off mechanism. There are more details in our paper. Thanks for the question.
Okay, so ask question from attendee. Okay, I have one question that I noticed in your design. There is one coordinator to handle that in the multiple nodes. So my question is that if the entire framework includes just one coordinator, how to handle the potential access bottleneck or avoid a single point of failure?
So let me see if I understand the question. So are you asking about the coordinator if it is a single point of failure, or?
Yeah, because that you are just only one coordinator, right?
No. So any node can be a coordinator.
Oh,
any
okay.
node that wants to execute the transaction is a coordinator. The coordinator essentially gets the objects, like in a typical DSM, for example. It would get the ownership of the objects, and then it will execute a transaction locally instead of distributed a transaction, which is more costly than that.
Okay, that's good. Okay, I will check the. Yeah. Have any question from attendee? Okay, a very interesting work. Okay, thank you very much.
Okay, I think there are two questions in the Slack, but yeah.
Okay.
Time, yeah.
Okay. Yeah. Okay, that's good.
Yes. So Job asks about if I can clarify further about the real-world locality that I showed in slide 11. Yes, actually, we have based on a study that it is. So this actually a real-world locality that is based on the mobility of users in a telecommunication network that was from the Boston metropolitan area, actually. So this, how we got this real-world locality there. Marius Koyas also asks, how do you assign incoming requests to servers and guaranteeing load balancing? Yeah, that's a very good question. We haven't, load balancing is not the main focus of the work. It's definitely, you can use our approach for load balancing. We actually have a load balancer to steer requests that are generated from outside of the system. And you can use several techniques there to load balance the requests. You can even have application-specific load balancing, but in the results that I showed, there's no. We haven't performed any load balancing similarly to the compared systems. The system we compared with.
Okay. Yeah. Okay. No question. Okay. Okay. Thank you very much. Okay. Very good work. Thank you
very much.
Okay. Bye. Okay. The next paper to present is from the University of Mannheim, and the presenter is Victor. And this paper will discuss how to provide an efficient replication. And okay, please play the video.
Hello, my name is Vitor, and this is a presentation about our paper, Efficient Replication via Timestamp Stability. In our paper, we focus on planet-scale replicated systems. These systems are replicated in order to provide fault tolerance. So if a user is accessing a replica and this replica for some reason goes down, then the user can fail over to another replica and keep accessing the system. Now, these systems are replicated on a planet scale in order to provide low latency. By having replicas deployed all over the world, users can minimize the latency required to access the system. One question that comes up when we have multiple replicas of the same data is whether these replicas are consistent with each other. In this paper, we focus on strong consistency, and in particular, we consider systems that provide the gold standard, the linearizability. This, in a nutshell, means that the system behaves as if all commands are executed by a single thread, and so replication is transparent to users. And the way we're going to achieve this is with state machine replication, or SMR. In SMR, the system is defined by a deterministic state machine, and there is a protocol that determines the order in which commands are executed at each replica. One of the most famous SMR protocols is Paxos, which is leader-based. This means that when a client wants to submit a command to the system, it sends it to the leader replica. When the leader replica receives this command, it forwards it to f+1 acceptors, where f is the number of failures that we want to tolerate. So if we say that f equals 2, then the leader forwards the command to 3 acceptors, one being itself. Then, once these acceptors acknowledge the command, the leader can commit the command, execute it, and then send the result back to the client. So, what are the issues with this approach? Let's now consider that the client is located in Europe. Again, the command needs to be sent to the leader, but this time it needs to cross the Atlantic. After contacting the acceptors and executing the command, the leader sends the reply to the client, again crossing the Atlantic. If we compare this with a client located in North America, we can understand why leader-based protocols can be unfair to faraway clients. Moreover, the leader replica is doing most of the work and can, with enough load, become a bottleneck, so there's no load balancing. And finally, the leader replica is a single point of failure, since if it goes down, the system cannot serve requests until a new replica is elected as the leader. One aspect we haven't discussed about Paxos is how commands are ordered at each replica. In Paxos, the leader assigns the timestamp to each command, and then commands are executed in this timestamp order. So if a replica sees command W committed with timestamp 1, it can execute it right away. Similarly, if it sees command X committed with timestamp 2, it can also execute it as it has already executed the command with timestamp 1, command W. However, if it sees command Z committed with timestamp 4, it can't execute it until it receives the command committed with timestamp 3. Mencius is also an SMR protocol, but with multiple leaders. In Mencius, each leader commits commands in a similar fashion to Paxos, but commands are ordered differently. Since we can have commands committed with the same timestamp, we're going to break ties using the leader identifier. So in this example, we have 3 leaders, A, B, and C. If a replica sees command W by leader A committed with timestamp 1, it can execute it right away, as no command can be ordered before W. If the replica then sees command X by leader B, also committed with timestamp 1, it can also execute it as the command with timestamp 1 by leader A is already executed. However, if it sees command Z by leader A committed with timestamp 2, it can't execute it until it receives the command by leader C committed with timestamp 1. So while Matthew's approach is more fair than Paxos and provides load balancing, it runs at the speed of the slowest leader. And the root problem we have identified here is that a command's timestamp is computed by a single process. To sidestep all these issues, in this paper we propose Tempo, a leaderless protocol in which, instead of having a single process deciding the command's timestamp, we have a majority of processes proposing a timestamp for the commands. Then, the command's timestamp is the highest of these proposals. Again, we have an example, and command W is received by majority A and B, both proposing timestamp 1 for the command. Thus, command W is committed with timestamp 1. Command Y is then received by process A, which proposes timestamp 2, and process C, which proposes timestamp 1. Since the command's timestamp is the highest of the proposals, command Y is committed with timestamp 2. Finally, command X is received by majority B and C, both propose timestamp 2, and thus command X is committed with timestamp 2 as well. So this is how Tempo computes the timestamp of commands. After being committed with a timestamp, commands have to be executed. So now we need to know when it is safe to execute a committed command. For that, we resort to timestamp stability, which tells us that process I can only execute command C after its timestamp T is stable, and that is when every command with a timestamp equal or lower to T is also committed at process I. In the paper, we show that some timestamp T is stable at process I once process I knows all proposals up to T by some majority. If we go back to the previous example, when we see command W committed with timestamp 1, timestamp stability tells us that it is safe to execute command W if we have all proposals up to 1 by any majority. And indeed, we have all proposals up to 1 by majority A and B, and so command W can be executed. However, when command Y is committed with timestamp 2, this timestamp is not yet stable as we don't have all proposals up to 2 by some majority. Intuitively, it's not safe to execute command Y because another command can still be committed also with timestamp 2. This can occur when such command gets proposals from processes B and C, in which case it would be committed with timestamp 2. And this is exactly what happens with command X. Now, when we see these two commands committed, it is safe to execute them as timestamp 2 is now stable. And that's because we have all proposals up to 2 by some majority, for example, A and B. In this example, we have two commands committed with the same timestamp, Y and X. And when that happens, we break ties using their identifiers. So in this example, we execute first X and then Y. One of the main benefits of Tempo is that it provides low-tail latency in a predictable manner. In this experiment, we consider two settings. On the top, we deploy 256 clients per process, while in the bottom, we deploy 512. Here we compare Tempo with 3 other leaderless protocols, Epaxos, Atlas, and Caesar. We can see that these 3 leaderless protocols offer extremely high tail latencies that reach several seconds, making these protocols unusable. Moreover, doubling the number of clients almost doubles the 99.9 latency percentile. On the other hand, Tempo provides a 99.9 latency percentile of around 360 milliseconds, and this percentile is virtually not affected by the increased load. Besides performing well in practice, we prove in the paper that Tempo always ensures progress in a synchronous network. This is not the case of the 3 other leaderless protocols, since there are scenarios where these protocols don't even terminate. In the paper, we show that Tempo can be easily extended to support partial replication scenarios. There, we compare Tempo with Janos, a state-of-the-art protocol designed for partial replication. Our evaluation shows that Tempo can provide a throughput that far exceeds the one of Janos. The paper also describes Tempo's fast-path condition and its simple recovery mechanism. Finally, the paper contains some details about the evaluation framework that we have designed in order to implement and evaluate all these protocols. So, in summary, Tempo guarantees progress under a synchronous network without the need to contact all replicas, which was not the case in previous leaderless protocols. Tempo also provides predictable performance even in contented workloads. And finally, Tempo supports both full and partial replication scenarios, and in both, its timestamping and stability detection mechanisms are fully decentralized. Any questions? Just reach out on Twitter or by email. Have a nice day.
Okay, Peter, IO, all right.
Hello? Can you hear me?
Okay. There is a question from attendee. And as for attending, before you ask the question, please also introduce yourself, your name and your application. And thank you.
My name is Paul Ejil-Shelvan from University of Newcastle, not far from University of Edinburgh. It's an excellent talk. Only at the end, I understood you assume that the network is synchronous. I think it's very essential assumption for you because instead of a single leader proposing the timestamp, you are taking a majority, and the highest of the majority is the final timestamp. So it's possible that 2 nodes see a different majority because in your examples, exact majority, 2 out of 3 proposed for every transaction. But in reality, everybody may propose and 2 nodes may see a different majority. As a result, they may decide different timestamp for different transactions. So the assumption that synchronous network is completely is very crucial, but again, it doesn't sit well with your geo-replication strategy because you are talking about nodes highly distributed. So in that sense, in that context, it's very difficult to justify that assumption of synchronous network.
Mm-hmm. So actually, we only assume synchronous network to prove liveness, not for safety. So the example you were considering, it shouldn't be possible. Now, for liveness, we have to assume a synchronous network, but this is also the case for all the other protocols like Paxos, for example. We can go into details about the example you were thinking, where I guess safety was broken, but it shouldn't be possible, and we don't need to assume that the network is synchronous for that. I hope that answers.
Okay. Thank you. I will read the paper because I'm still not really clear how, there could be a virtual two-facing. I see one majority, therefore I decide on one highest number, and you see another majority, you settle on a different number. So here we need an agreement here. So I will look into the paper and then talk to you. Thank you.
Thanks.
Okay. So Victor, there is a question in the chat. Can you see the chat? On slide 4. Okay. Yeah. On slide 7. Yeah. How do you break ties? Can you hear that?
So on slide 7, how do you break ties between command X and Y? Because Y is a majority for timestamp 2, but the maximum timestamp for X is also 2. So how did you break ties there? So X and Y will have some identifier. In the slide, I was assuming that the identifier of X is smaller than the identifier of Y. And because identifiers are unique, then we break ties using the identifier. And so in that example, X is executed before Y, I think, because it has a smaller identifier.
Okay. And so thank you very much. Very interesting work. Okay, thank you. Yes. So the next paper to present is from the speaker is Xu Sheng from the University of Hong Kong, and this paper will discuss very interesting work in the context of the edge computing. Okay, so please play the video.
Hello everyone, I'm Xu Sheng from the University of Hong Kong. Today I present DAST, the first serializable database that can achieve both low tail latency and high scalability in edge computing. Edge computing is a fast developing computing paradigm that moves the computation results from the cloud data centers far away from clients to the edge of the internet that is close to clients, so that it can exploit clients' data locality and provide low client perceived latency. Edge computing is already widely deployed in many use cases like the CDN networks to improve user experience. Recently, with the development of the ultra-reliable and low-latency communication technologies like the 5G network, a new class of edge computing applications that deal with mission-critical tasks emerges. For instance, a NASA project tries to integrate the management of UAV networks and the management of normal airplanes to schedule air traffics and to avoid collisions. These mission-critical applications desire very low tail latency for stable response time, and at the same time, their rigorous correctness requires serializable transactional support, because serializability is the strongest isolation level and can avoid many application-level bugs. However, as existing edge computing databases target only non-mission critical use cases like CDN networks, they provide only weak isolation guarantees. To make this new trend, in this project, we build a distributed edge computing database that can ensure both low tail latency and scalability. Different from traditional databases, in a typical edge computing database, nodes and clients are divided into regions, and nodes in a region manage only data shards that are most frequently accessed by intra-region clients. The intra-region networks is usually much faster than the cross-region networks, so replication is usually done within each region for low latency. In such a deployment model, client transactions can be divided into two categories. We call a transaction an IRT if it accesses only data shards in this region. Otherwise, we call it a CRT. Because typical edge computing applications show good locality, IRTs take a great portion of all transactions. Under such a deployment model, we summarize 3 technical requirements for an edge computing database that ensures serializability and low tail latency. First, when a cross-region transaction is under coordination, subsequent IRTs should not be blocked. Because the average latency for IRTs is only a few milliseconds or a few tens of milliseconds, but the latency of CRTs can be hundreds of milliseconds. If IRTs are blocked, their tail latency will be very high. Second, a CRT should not be aborted simply on conflicts. A naive approach to meet R1 is to abort CRT whenever it conflicts with IRTs. However, because in the lifetime of a CRT, many IRTs can be submitted and finished. Such a design will cause CRTs to be repeatedly aborted and start. Moreover, if an IRT sees the intermediate result of a CRT, the IRT must be blocked to wait for the commit result of CRT before it can get committed. Third, as an edge computing application may have up to hundreds of regions, the database performance should be scalable to a large number of regions. Although there are many influential geo-distributed serializable databases that can achieve good performance when deployed among a few core data centers, they are not designed to meet the three requirements if deployed on the edge. A key reason is that these systems order transactions in a first-come, first-served manner, based on transactions arrival order at replicas or a central ordering service. These systems can be divided into two categories. The first category takes the deferred update approach, where transactions are first executed locally and then verified globally. However, such an approach generally cannot meet R2, as CRTs can get repeatedly aborted at the verification phase. The second category takes the SMR approach, where transactions are first assigned an order and then executed at relevant nodes according to this order. However, such an approach cannot meet R1 in general. We use a simple example to demonstrate the reason. These are the time axes for two objects A and B in two regions. Suppose a CRT that sets the value of B to A+1 is submitted and it is coordinated using a standard two-phase commit protocol. After object A prepares the CRT, an IRT is submitted to object A, but this IRT must be blocked until the CRT finishes. Moreover, due to partial replication, region 2 does not hold the replica for A. So when object B is waiting for the read value of A and an IRT arrives, the IRT must be blocked as well. Note that such blockings are not critical in traditional geo-distributed databases because all transactions client perceived latency is already high in these systems. But in an edge computing database, if an IRT is blocked, its latency will be tens of times longer. To address this problem, in this paper, we present a new conceptual method, DUST, decentralized anticipation stretch. DUST also takes the SMR approach, but DUST orders transactions based on when transactions coordinations are anticipated to have finished and when transactions are ready to execute. Conceptually, in the previous example, DUST assigns an anticipated timestamp 200 to the CRT and assigns the subsequent IRT a smaller timestamp 120. By doing so, although the IRTs arrive later, it is ordered before the CRT without being blocked. Note that this is not a simple local reordering because region 1 can have multiple data shards with replication, and IRTs can access multiple intra-region shards. Doing a simple local reordering cannot ensure consistency or isolation. To handle the blocks caused by inaccurate anticipation and cross-region data reads, DUST dynamically stretches the granularity of timestamps. For instance, when object B is waiting for the value of way to execute CRT at timestamp 200, it stretches out the granularity of clocks after its clock passing 199 and assigns 199.1 to IRT2, so IRT2 is not blocked. And it can assign timestamps 199.2, 199.3 to following IRTs. By doing so, DUST tackles the blocking issue in the previous page, and DUST protocol can still ensure serializability. A key challenge to realize the conceptual method of DUST is to anticipate a proper timestamp for a CRT without involving a central service for ensuring the system's scalability. The timestamp must be in the future of all participating nodes clocks to avoid the CRT getting aborted. But this timestamp cannot be conservatively large for the CRT's own latency. A strong approach is to let a single node determine the future timestamp for the CRT. However, when the CRT arrives at its participating nodes, their clocks may have already passed the timestamp due to clock skewness or due to network instability, causing the CRT being aborted. To address this challenge, we propose a new two-phase decentralized anticipation protocol that complies with the standard two-phase commit. Consider three objects A and B and C in three regions, and the CRT assessing these three objects. For simplicity, we assume that network is stable and clocks are synchronized, but note that DUST protocol does not need such assumptions. In the first phase, each node anticipates a future timestamp based on the RTT between itself and the coordinator B. representing when it can receive the commit message for T1. Each node also promised not to execute transactions with timestamps larger than its anticipated timestamp to avoid TE get aborted. In the second phase, the coordinator B selects the maximum anticipated timestamp TS max and commit T1 with the TS max. T1 is committed with the maximum anticipated timestamp implies that all participating nodes promise not to execute transaction larger than TS max, so T1 will not get aborted. A problem here is that if we look at the time axis of object A promised not to execute transaction larger than 200, but it can only receive the commit message at time 220. What if IRTs arrive during this time? This is exactly why we need Dust hybrid clock. Object A can start to stretch its timestamp granularity after its clock past 199 because it knows it has promised not to let its clock pass 200. Dust also handles many other practical challenges, like how to handle clock skewness or how to achieve fast failover. Please refer to our long version presentation or read our paper. Overall, Dust can ensure the three crucial technical requirements and ensure serializability. To ensure R1, Dust assigns CRTs for future timestamps representing when they can execute and use the hybrid clock for handling inaccurate anticipation. To ensure R2, Dust use the SMR approach, and Dust two-phase anticipation protocol ensures that CRT is not aborted on clock skewness. Dust is also scalable to a number of regions because committing a transaction only involves participating regions. Dust ensures serializability with no fail risk by ensuring that when a node executes a transaction T with timestamp TS, the node must have executed all relevant transactions with timestamp smaller than TS. This implies that all dependency edges are in ascending timestamp order, so the global dependency graph is acyclic. We have included a proof of Dust guarantee in our paper. Compared to existing work, Dust is the first distributed database that can meet all the three requirements and serializability. While existing traditional serializable databases are not designed to meet all the three requirements if they are deployed on the edge, and existing database for edge computing target only non-mission critical scenarios, so they do not ensure serializability. Dust is substantially evaluated, and our evaluation earns the result reproduced batch from the community. We only cover the first evaluation question due to time limit. You can watch our long version presentation or read our paper for more details. We compare against 3 geo-distributed serializable databases, Janus, Taper, and slog. All systems run the same set of store procedure on the same in-memory DB. We choose TPCC as our major benchmark because it is standardized and well understood. It also shows good spatial locality and it is evaluated by our baseline systems. Although TPCC is not dedicated for edge computing, it has already covered diverse radar patterns that are common in edge computing. The evaluation result shows that Dust can greatly reduce the tail latency for both IRTs and CRTs, while at the same time, Dust can achieve comparable throughput compared to the relevant systems. Now we conclude. Dust is the first edge computing database that ensures serializability, low tail latency, and high scalability. It has the potential to support the deployment of many emerging mission-critical edge computing applications like the real-time traffic management or edge computing-based trading system. Our artifact is evaluated and is accessible from the GitHub link. Thank you all for listening.
Hello, my name is Vasilis, and in this presentation...
Hello, everyone.
Okay, Shisheng, are you okay?
I'm here, yeah.
Okay. Any question from attendee?
Serializability.
Okay, very interesting work. Okay, I have one question. That since this work will be implemented in the edge computing and also can support some real-world application in the context of the edge computing, and since we know that in the edge computing it also have some extra communication with such as the server and also the clients. So do you have some analysis or consideration or performance evaluation to examine how about the network or head communication with the server or the client?
the question is about the network consumption in our system, and we have included data in our paper in the evaluation section. I cannot remember the exact numbers, but the number is not high, and it can be fulfilled by common LAN networks or 5G networks. We have included the data in our evaluation section.
Okay. So there is one question in the chat. Can you check?
Okay. Yeah. I see. This question is about the clock skewness in Dust. Actually, Dust handles clock skewness. Dust only needs the nodes to have a loosely synchronous clock. For instance, nodes can run a NTP protocol, and this is because Dust uses its own hybrid clock to assign timestamp and to determine when to execute transactions. And the physical part of the hybrid clock actually is ahead of the host system clock for offset value, and the offset value is actually adjustable, and it is adjusted by the Dust protocol. For instance, if a node finds that its clock is lags behind compared to other intra-region nodes, it will fast forward the offset value to make it catch up. And we have included the protocol and the evaluation in our paper to show that Dust performance is not sensitive to the clock skewness. Thank you.
Okay. Any other question from attending? Okay. So thank you very much. Okay. Very interesting work.
Thank you.
Thank you. So the next paper to present is the presenter is Vasilis from the University of Edinburgh, and this paper will discuss the impact of modern hardware on strongly consistent replication protocols. Okay, so please play the video.
Hello, my name is Vasilis, and in this presentation, we will explore how modern hardware has changed how we design replication protocols. Specifically, we focus our attention on the performance of replication protocols that offer strong consistency over an in-memory key value store that is replicated, has a read-write API, and is deployed inside the data center. Such protocols can be any of the Paxos variants, Raft, Zookeeper, chain replication, and many more. Historically, such protocols have been designed under the assumptions that machines are single-threaded, data is stored in the slow disk, and communicating over the network is very slow. Under these assumptions, the design guideline for high performance is simple. The protocol must minimize the number of disk access and network round trips that are required to execute a request. However, modern hardware renders these assumptions obsolete. Specifically, over the last 10 to 15 years, the server-grade hardware has changed drastically. We now have servers with many tens of cores. Main memory has been scaled to hundreds of gigabytes, allowing data to be kept in memory. And data centers now commonly deploy user-level hardware offloaded networking with tens or hundreds of gigabits worth of bandwidth and microsecond latencies. Naturally, these advances challenge the conventional wisdom in protocol design, as we no longer need to optimize around disk or network, but instead we must be able to leverage the abundant parallelism found in today's hardware. This gives rise to two important research questions. First, how do existing protocols perform over modern hardware? And second, given this modern hardware, what are the best practices in protocol design to achieve high performance? To answer these questions, we set out to characterize the design space of strongly consistent replication protocols. We do so in 3 steps. The first is protocol selection. Specifically, we develop a taxonomy that structures the design space by classifying protocols based on their operational patterns. Based on this taxonomy, we carefully select 10 protocols that capture the design space. The second step is the implementation. Crucially, in order to draw meaningful conclusions, we need to facilitate a fair apples-to-apples comparison between the 10 selected protocols. To do so, we present Odyssey, a framework that allows us to easily design, measure, and deploy replication protocols over modern hardware. We implement all 10 protocols over Odyssey, facilitating an apples-to-apples comparison between them. Finally, in our design space characterization, we analyze the results of the select protocols, uncovering the best practices for protocol design in the modern era. Let us dive into our taxonomy. We divide the space into 4 quadrants based on the operational patterns of the protocols. Specifically, a protocol can be either leader-based or decentralized, and can either maintain a total order over all writes or a per-key order. Leader-based protocols will steer all writes to the leader node, which will typically order them and propagate them to the follower nodes, typically with a couple of broadcast rounds. In contrast, in decentralized protocols, every node is responsible for coordinating its own writes by broadcasting them to the rest of the nodes. Total order protocols create a total order of all writes and mandate that all nodes must execute writes in that total order. For example, in the figure, we see that 2 writes to different keys X and Y are ordered in all nodes. Conversely, per-key order protocols need only agree on the order of writes to the same key. Using this taxonomy, we select these 10 protocols for evaluation in order to characterize the design space. The arrows in the slide represent optimized protocols over the vanilla approach. All 10 protocols fall under the umbrella of strong consistency. However, their consistency and availability guarantees are subtly different. We elaborate on these differences on our paper. Let's proceed directly to the characterization of the design space, noting that a detailed description of the Odyssey framework can be found in our paper. The results we will see are based on this configuration. Protocols are deployed over 5 servers, each of which has 40 hardware threads, a 56 gigabit NIC, and a Mica key value store with key value pairs of size 48 bytes. Let's dive in. In our paper, we present the design space characterization in the form of a set of general directives and recommendations. In this presentation, we will discuss just 2 directives. The first is that total order should be avoided in read-write systems. We have selected 3 total order protocols, Multipaxos, ZAB, and Dereco. Let us focus our attention on ZAB, which is the protocol at the heart of the zookeeper system. This graph depicts the single-threaded throughput of ZAB in millions of writes per second. In fact, in all our graphs, the y-axis will show millions of writes per second. As we can see, ZAB significantly outperforms classic Paxos, CP in the graph, for single-thread performance. However, when we multi-thread, the situation is completely inverted, as it is now classic Paxos that significantly outperforms ZAB. A quick aside, we have extended classic Paxos to execute read-modify writes, incorporating a flexible Paxos optimization, and we have uploaded the complete specification in archive. So please check it out if you are interested. Coming back to our main story, we have established that ZAB does not scale well with more threads. Let us understand why. Assume this ZAB server could be a leader or a follower with 3 color-coded threads. The server must apply 300 writes in their total order. Each of the threads is responsible for a batch of 100 writes. Threads must work on batches to minimize the required synchronization between them. First, thread 1 applies writes 0 through 99. In the meantime, assume that thread 2 and thread 3 are processing their own writes, exchanging the messages needed to execute them. At a later time, thread 1 finishes applying the writes and can go on to process its next batch. Assume that at this point, thread 2 and thread 3 have both finished the necessary processing and can now apply the writes. However, because writes must be applied in the total order, thread 3 must block, waiting for thread 2. Only after thread 2 has finished can thread 3 finally apply its own writes. The problem, therefore, is that because writes must be applied in total order, threads can only write to the key value store in lockstep. As such, the throughput of the entire system is limited to the rate at which a single thread can apply writes to its local key value store. For this reason, total order protocols do not scale well with more threads. This graph shows the write throughput in millions of writes per second of all 10 protocols when multi-threaded. We can see that the 3 total order protocols, ZAB, Multipaxos, and Dereco, are significantly outperformed by the rest due to their inability to scale with multiple threads. Therefore, for read-write systems, we advise that totally ordering writes should be avoided. The second directive is that leader-based protocols can achieve high performance as long as we ensure they are load balanced. Seeing as total order protocols cannot scale well with threads, let's now focus our attention on per-key protocols, starting with CHT. CHT is a per-key leader-based protocol proposed in POGI 2016. This graph shows the single-thread write throughput of CHT compared to that of Hermes. Hermes is a decentralized per-key protocol proposed in AS+20. We see that Hermes outperforms CHT by a small margin. When we multithread, we see that the gap between the two protocols grows significantly. Similarly to the total order protocols, CHT does not scale well with main threads. However, this time the bottleneck lies with the send bandwidth of the leader. Let us understand why. Here, we see how the CHT protocol executes a write. The follower steers the write to the leader. The leader then broadcasts the write to all nodes, gathers acknowledgements, and then broadcasts a commit message. In our analysis, we can disregard ACKs and commits because the Odyssey framework performs optimizations to eliminate their bandwidth footprint. Instead, the problem is that the first broadcast round is implemented with unicasts, 4 unicasts in this example. Therefore, for each write, the leader sends 4 messages, while each follower receives only 1. The leader saturates its send bandwidth with only a few threads, even though there is a lot of leeway in the receive bandwidth of followers. In other words, the leader creates a load imbalance in the network bandwidth utilization, hindering scalability. There are 2 protocol-level solutions to this problem, having multiple leaders and using a chain instead of a broadcast. Let's start with the multiple leaders. In this optimization, all nodes are denoted leaders. Each leader is responsible for a portion of the keys. Consider this toy example key value store with 50 keys, where leader 1 is responsible for keys 0 to 9, and so on. When leader 5 wants to execute a write to key 25, it must first steer it to leader 3, which then coordinates it. Similarly, a later write to key 40 must be steered to leader 5. Therefore, broadcasting the writes is load balanced amongst the different leaders. As a result, we see that CHT multi-leader, the CHT implementation with multiple leaders, significantly outperforms CHT and approaches Hermes. The second protocol-level solution is to organize the nodes as a chain such that instead of broadcasting a write, the write flows from the head of the chain all the way down to the tail. In this example, a write is steered to the head, which then propagates it down the chain all the way to the tail. As a result, the intermediate nodes share the load of executing a write, alleviating the load imbalance. Note that the tail still does not participate in the write propagation, which means that there is still some imbalance in network bandwidth utilization. This imbalance is demonstrated by the CRAC protocol, which is a variant of the chain replication protocol optimized for read-write systems. CRAC significantly outperforms CHT, but is not as good as CHT multileader because the tail node remains underutilized. Tracking back to our directive, we have seen that leader-based protocols can be load balanced and thus can achieve high performance. Summarizing, in this work, we explore the performance of strongly constant replication protocols over modern hardware, focusing on uncovering the best practices for protocol design. We do so in 3 steps. First, we create a taxonomy based on the operational patterns of protocols. Through this taxonomy, we select 10 protocols. Second, we present Odyssey, a framework tailored towards protocol development over modern hardware. Through Odyssey, we implement all 10 selected protocols, facilitating an apples-to-apples comparison. Finally, we analyze the results of the comparison to provide a characterization of the design space in the form of a set of recommendations for existing protocols and best practices for future design. Please see our paper for more details.
Okay. So, Vasilis, are you here?
Hello.
Hello. Oh, okay. Okay. So, have any question from attending? Okay, I have one question that you mentioned you leverage the multiple leaders, right? This will be address the mentioned problem. But my question is that for one leader, it's just cover a limited size data. I mean that if the covered data is the hot data, and how to address the potential problem of the the load unbalance. I mean that if the one leader maintain many hot data, and many access will access that leader. So that leader will be potentially become the performance bottleneck, right?
Yes, that's a great question and a very good observation. Indeed, if you have skew in the access patterns, then one leader may be just unlucky and have just store the hottest keys, and then everything is still to that one leader. The thing to note here is that in that case, if you know that your workload has some skew, then there are other techniques that should be employed on top of it, right? Because skew itself is a form of locality, and I mean, we as a community, we know very well how to take advantage of locality. So skew, I think in that case, skew shouldn't be a problem actually, but should be an opportunity. Should be viewed as an opportunity. But yes, if you don't do anything smart, then this bad thing can happen.
Okay. Have any question from our attendee? Okay. Okay. So thank you very much. Oh, okay.
Yes, there's a question in the Slack. Let me from Marius. Marius says, could we comment on the latency aspect of all these protocols? If I understand correctly, you focused only on throughput. Could you extract similar guidelines for latency and tail latency? So thank you, Mario, for this question. It's a very good question. In the paper, we show latency numbers and we discuss latency. What we see is that in these highly optimized scenarios, and where you go to memory to find the data, and where you go through RDMA and you have microsecond latency for the network. In all protocols, the latency for request ranges in like a few microseconds, right? Maybe tens of microseconds. And then what really matters is the load, like because the big factor in latency is queuing. So it turns out that throughput is the most important aspect of latency. It is the most important factor in latency, because if you have a system that can do high throughput, then in your required workload, you will be lightly loaded, and then latency will go down, because queuing is really the only thing you should be afraid there. I don't know if that answers your question, and there is more in our paper about latency.
Okay. Yeah. Okay.
Yeah. Hit me again if you have anything else. That's it.
Okay. Okay. So thank you very much, and very interesting and very good work. Okay. Thank you.
Thank you very much. Thank you very much.
Our session have finished, and thank you. Thank everyone for attending on this session, and thank you very much.
So Marco, you can take it over, I guess. Yeah.
Yeah. So do I just speak? Do I need to do anything?
Should we give a 5 minutes break or so, or say, or we can start immediately? Do you want to start immediately, or?
I'm fine. You just tell me, do I need to touch anything, or do you just send me live?
You are live already, so it's
oh, okay. all right. Sorry. All right. Then let's get it started.
Okay.
Welcome to this session. My name is Marco Serafini. I'm from UMass Amherst. I'm honored to chair this session. And we have 5 great papers today. The first is on Flask Graph. It's system for GNN training that addresses a new class of GNN architecture. So very exciting work. Let's start the video.
Hello everyone, I'm Wang Lei from Alibaba Group. I'm very glad to introduce our work on GNN training, Flask Graph, a flexible and efficient distributed framework for GNN training. Here, flexible means that we propose a new programming abstraction for GNN models, and it allows developers to express different types of GNN models easily. Efficient means that Flask Graph also performs other state-of-the-art GN frameworks. Next, I will introduce these two parts respectively. First, I introduce a flexible programming abstraction for GN models. Most GN models fit into the neural multipassing framework, where the computation of each GN layer includes two steps. For each vertex in a graph, it first aggregates the features of its neighbors to compute its neighborhood feature. Then it combines its own feature with the neighborhood feature to update its feature. By investigating state-of-the-art GN models, we find that GN models have diverse definitions of neighbors and neighborhood aggregate schemes. Next, we present a new two-dimensional classification for GN models according to their neighborhood definitions and aggregate schemes. The first class is DNFA model, direct neighbors with flat aggregation. Direct neighbors mean that the neighborhood of each vertex consists of all its one-hop neighbors, and flat aggregation means that the aggregation function only performs a single-step operation. GCN is a DNFA model. Consider vertex A in a sample graph. In each layer of GCN, the neighbors of A are D, E, F, and H. To produce the neighborhood feature of A, the aggregate function just sums the features from the neighbors of A. The second class is INFA model, indirect neighbors with flat aggregation. For INFA models, a neighbor of a vertex can be a vertex from a nearby subgraph instead of its actual one-hop neighbor. Similar to DNFA model, neighborhood information is gathered in a flat manner. For example, PinSage is an INFA model. It has a similar architecture to GCN. However, PinSage adopts an importance-based neighborhood definition. The neighbors of each vertex is defined as the top k visited vertices in several random walks starting from it. If k is set as 2, the neighbors of A are C and G, since C and G have the highest fit counts. Both C and G are indirect neighbors of A. The third class is INHA model, indirect neighbors with hierarchical aggregation. In an INHA model, a neighbor can be any graph structured data. In the neighborhood aggregation, multi-step operations are allowed. MAGN is an INHA model. In MAGN, the neighbors of a vertex are a set of metapath instances. Each instance has a type called a metapath. Each metapath is an ordered sequence of vertex types. In this figure, vertices of different types have different colors, and we have two metapaths, MP1 and MP2. As a result, the neighbors of A are P1 to P5. The aggregation operation of MAGN is performed in a hierarchical way. When computing the neighborhood features of vertex A, MAGN first computes the features of each instance by combining the features of vertices belonging to the instance. It then combines these features of the same metapath type to compute the features of MP1 and MP2. And finally, it aggregates the features of MP1 and MP2 to get the neighborhood features of vertex A. Inspired by the vertex-centric program models like GAS used in the graph processing systems, some GAS-like program models for GN have been proposed. Saga-N is proposed in NeurGraph. The computation of a GN layer is divided into 4 stages: scatter, apply edge, gather, and apply vertex. To compute the neighborhood features, each feature first scatters its feature along its outgoing edges to produce a feature for each edge. It then applies NN operations to generate new edge features. At last, each vertex gathers features of its incoming edges and combines them as its neighborhood feature. At last, each vertex assembles its neighborhood feature and its own gold feature to compute its updated vertex feature. In Saga NN, each vertex computes its feature by combining the feature of its one-hop labels in a flat manner. It's hard to express NFA and NHA models using Saga NN. To solve this problem, Flash graph applies a hierarchical dependent graph. The HDG for each vertex contains two parts, a schema tree and a set of neighbor instances. The schema tree encodes the hierarchical tree structures for label types defined by the GM model. The label instance is a set of labels defined by the model. Each label instance is linked to a leaf in the schema tree to encode its type. If a label instance is beyond a single vertex from an input graph, then HDG collects all its associated vertices in the input graph to the instance. Based on HDG, we further propose a new GN programming abstraction, NAU. NAU introduces a label selection stage to build HDG. Having HDG in place, in the aggregation stage, NAU asks the user to specify an aggregation function as a UDF for each level in the HDG. Then NAU automatically performs the hierarchical aggregation by applying this UDF in a bottom-up fashion. Finally, the update stage combines the old features and the neighborhood feature and outputs new features for the next layer. Next, we outline the sample implementations for GCN, PinSage, and MAGN in the NAU model. In the label selection stage, users only need to implement a UDF for each label type. In the aggregation stage, users need to provide an aggregation function for each level of HDG. With the NAU in place, next we introduce some optimizations for GN training. The first is hybrid execution, where FlexGraph adopts different aggregation operations for different levels of HDG according to the properties of different levels of HDG. Take the HDG for MAGN as an example. Each vertex at level 2 has multiple incoming edges, and we adopt a feature fusion operation at this level. Each vertex at level 1 has only one incoming edge, and the sparse tensor operations are used for this level. Finally, all root or vertices at level 0 share the same schema tree structure. At this level, dense tensor operations are applied. Next, we introduce these three types of operations and why we choose different operations for different levels. The first is sparse tensor operations. To aggregate the neighborhood features using sparse tensor operation, each vertex needs to send its feature to its outgoing edges as edge features. Then each vertex collects its neighbor's features through its incoming edges and applies a user-defined aggregation operations. That means edge feature has to be materialized. Consider vertices at level 2. Each vertex at level 2 has only incoming edge, as each label instance has a unique label type. Such operation will not need to the feature of each vertex has been materialized many times. The second is feature fusion operation. Each vertex at level 2 has multiple incoming edges, and the sparse tensor operations will result in huge memory overhead, as the feature of each vertex has been materialized many times. To solve this problem, in feature fusion operation, each thread first loads the features of vertices at level 3, then performs the aggregation and appends the results to the buffer with respect to destination vertices at level 2. The third is dense tensor operation. dense tensor operation is very efficient in current NN frameworks, but it requires a regular form of the input. This is fully satisfied by the schema tree, as all root vertices share the same schema tree structure. The next optimization is workload balance for distributed training. Existing solutions use different graph partition algorithms on the input graph to solve this problem. However, as we can see, the input graph cannot capture the dependency information among vertices. Therefore, our method is performed on a new induced graph. This graph is created by collecting roots and leaf vertices in the HDG. In addition, instead of using static metrics like vertex weights or edge weights, inspired by application-driven application partition, our method allows users to provide a UDF to define the computation cost of each vertex. Finally, we report the performance of flash graph. First is the performance in a single machine environment. Among all baseline frameworks, flash graph can achieve the best performance, and only flash graph can support efficient training of MAGN. The next is the performance in a distributed environment. On all three GN models, flash graph nearly achieves linear speedups as the increase on machines. That's all. Thanks for your attention.
All right, thank you for your talk. Let's see if we have some questions in the chat. Let's give a couple of minutes for people to, well, 1 minute for people to ask. Otherwise, I have some questions. So let's start with a question. So you built, as part of the optimization you show, you built this hierarchical dependency graph. I was wondering, would it be possible to express transform the input graph into a hierarchical dependency graph and then use the standard one-hop aggregation on the hierarchical dependency graph?
Yes, that's a good question. Actually, we talk about this issue in our paper, in our evaluation part. First, if the actually for an HA model, it can we can think we can perform some gas-like program abstraction on the HDG. Yes, but as we talk about in our paper, if in some situations the HDG cannot be pre-computed in advance, and so instead our program abstraction allow user to easily handle such a situation.
I see. Thank you. Thank you, Lei. Let's see if we have more questions. Actually, otherwise, let me ask another one before we go to the next talk. So you show a lot of interest in the paper, a lot of interesting optimizations on how to optimize sparse operations and irregular operations, and even dense ones, actually. So do you think that these optimizations are specific to your systems, or there are some lessons learned that other GNN systems could use? I mean, do you think that these optimizations are portable in other ways?
Yes, actually, the fusion operation is very similar to the DGL, and this optimization in DGL is called kernel fusion. So our work is aimed to aggregate different operations for different levels of HDG. So actually, like in DGL, they only consider simple and direct labor with flat aggregation models. So our work aim to handle all three types of GN models with very efficiently.
All right, thank you very much, Lei. Let's see if we have more questions from the audience. Otherwise, seems like there aren't. By the way, you can ask questions on the EuroSys Slack channel. There is a channel called Conference Session 3. So you can look for it, Conf Session 3. All right, thank you, Lei, then. And please, let's play the next talk, which is on, let's see, we have a question, maybe 1 second. Okay, just a comment. Cool, so let's move to the next talk, which is DGCL, and this is a communication library for distributed GNN training where the authors show very cool techniques to actually minimize and optimize the communication among nodes, which can be very expensive. So please, let's play the video.
Hello, everyone. I'm going to present DGCL, an efficient communication library for distributed GNN training. Nowadays, graph neural networks are widely used in many areas, including social network, physics systems, and medical molecules. Like many other neural networks, GNN have multiple layers to train. Here we focus on the full graph GNN training. At the beginning layer, each vertex in the graph has a feature, which is a vector to describe its properties. Let's take a look at the computation procedure of a specific vertex, the blue one. In each layer, it aggregates the feature of its neighbors and updates itself to produce a new feature for the next layer. So it follows an aggregate and update pattern in each layer. Like other neural networks, training GNN is very computational intensive, so it's better to train them on GPUs. The focus of this work is to train GNNs on multiple GPUs. In the distributed setting, we first partition a graph to several GPUs, and each GPU trained is subgraphs. However, during the partitioning, the endpoints of the same edges may be partitioned to different GPUs. Therefore, to guarantee the algorithm correctness, each GPU needs to fetch some vertices from other GPUs before the aggregation. So in the distributed setting, the computation pattern of one GNN layer is changed to communication, aggregation, and update. There are systems designed for full graph GNN training. DGL and PYG are designed for GNN training on a single GPU. NeuroGraph and ROC focus on distributed training. However, this system integrates communication and computation in a system, so the communication layer is not general to use. What's more, this system uses naive communication strategies, which are inefficient due to the complex GPU topology. Therefore, we want to build an easy-to-use and efficient communication library for GNN training. So if a system can train a GNN on a single GPU, it can use our library to extend to multiple GPUs. Now let's see why the naive communication strategy is not efficient on GPUs. Peer-to-peer communication is the most straightforward strategy. In peer-to-peer communication, each GPU fetch required vertices from other GPUs directly. However, it has two problems because of the complex GPU topology, which are the unbalanced communication and bandwidth contention. Let us use the DGS GPU server as an example to illustrate the problems. There are 8 GPUs on 2 CPU sockets in a server. Some GPUs are connecting with NVLink, while others are connecting with PCIe and QPI. Different connections between GPUs have different bandwidth. Therefore, in a peer-to-peer communication, Fast link may need to wait for the slow links, which lead to unbalanced communication. What's more, different GPU connections may contend for the same link during the communication. For example, when GPU 1, 3, and 4 send data to GPU 5, they all need to go through the QPI links, which means they will contend for the QPI bandwidth. Motivated by the communication problems of peer-to-peer communication, we designed DGCL, a general and efficient communication library for GNN training. Now let me first introduce the system architecture of DGCL. In this figure, the dark green parts are the components of DGCL and the light green parts are outside DGCL. At the beginning, DGCL reads the input graph and GNN model from users, and then it partitions the graph and plans the communication. The DGCL master sends the subgraph and communication plan to DGCL clients so that they can communicate with each other according to the plan. Finally, the GNN system can do the training as in a single GPU and use DGCL for the communication. Therefore, DGCL is general for different GNN systems. Now let's focus on the core problem, the communication planning. Let's first formulate the problem. The inputs of the problem are the graph partitioning scheme and the GPU topology. We want to design an algorithm to do the communication planning of each vertex while considering the communication balancing, contention, and forwarding. Finally, our objective is to minimize the end-to-end communication time. Given the problem setting, now let's analyze the solution space, which is the communication strategy of each vertex. Let's use a simplified GPU topology as an example. Assume we have 4 GPU and 2 CPU sockets connecting with different links. Assume a vertex is partitioned to the first GPU and it has neighbor on other GPUs, which means we need to send this vertex from the first GPU to GPU 2, 3, and 4. So, what are the possible communication strategies? A most straightforward way is to send from GPU 1 to others directly, as in the peer-to-peer communication. However, it will go through the QPI link to reach GPU 3 and 4, which may be too slow. Another solution only uses the NV link, where we use the GPU 2 and 3 to forward the vertex to GPU 4. Or we can use a more complicated strategy, which we send the vertex to GPU 2 and 3 and use the GPU 3 to forward it to the GPU 4. As we can see, all the strategies of a vertex is a tree, and it's easy to prove that the optimal strategy of a vertex is always a tree. Given the solution space, we use a cost model to guide our algorithm. Assume we know the strategy of our vertices. In our cost model, we first partition the communication strategy into stages, and we assume the communication on the same stage are happen at the same time. So, in each stage, we know the number of vertices going through each link and the speed of each link. We can easily calculate the communication time on this stage, which is the maximum of the vertex count over link speed for all the links. By aggregating the cost of stages, we can get the overall cost for the communication. So in each stage of the cost model, we only consider the slowest link, which encourage our algorithm to balance the communication on different links to minimize the stage cost. Also, all the communication on the same link are aggregated together at the same stage, so the contention is considered naturally in our cost model. Given the cost model, we designed a shortest path spanning tree algorithm to determine the strategy for each vertex. The idea is that we incrementally process the vertex one by one. So the heuristic here is we try to minimize the aggregated cost when deciding the strategy of a vertex. So when we process a vertex, we know the strategy of previous vertices. Let's say the current vertex is partitioned to GPU1 and is requested by GPU2, 3, and 4. From the cost model, we know the incremental cost if we associate a vertex on a link. So at the beginning, we find the smallest incremental cost from GPU1 to GPU2, 3, and 4. Let's say GPU2 has the smallest incremental cost among the 3 GPUs. Then we send the vertex from GPU1 to GPU2, and then we use GPU1 and 2 to find the smallest incremental cost to GPU3 and 4. Let's say this time we pick GPU2 to GPU3. And similarly, we use the same way to reach the GPU4. And finally, we get a spanning tree, which is the communication strategy of the vertex. The intuition behind the algorithm is that each time we extend our spanning tree to the GPU with minimal incremental cost, and at each time it tries to utilize the fast link and avoid the straggler links. We conducted experiments on 2 types of machines with our MV links. We compare with 3 communication baseline: peer-to-peer, replication, and swap. Replication baseline replicate K-hole vertices on GPU to eliminate the communication. Swap baseline use the host memory as the shared memory for the communication. We include 4 datasets and 3 GNN models. We first compare the end-to-end performance to train GNN on different datasets. In each group of the figure, we provide the performance of DGCL, swap, peer-to-peer, and replication baselines. In each bar, the bottom part is the computation time and the upper bar is the communication overhead. From the figure, we can see that DGCL has significantly shorter communication time than peer-to-peer and swap baseline. Average across all graphs and models, the communication time of peer-to-peer is up to 4.5 times of DGCL, where the swap is up to 60 times of DGCL. We also report the performance of DGCL on GPU topology without MV links. In such case, the GPU connection have similar bandwidth, but DGCL still outperforms peer-to-peer communication since it considers the bandwidth contention during the communication. We also give a breakdown analysis of the communication time that DGCL spend on different links. The results show that DGCL can effectively balance the communication time spent on different links. So now let me give a brief conclusion. We start from a communication problem in GNN training and give an analysis of peer-to-peer communication. Then we propose a general communication library with cost model and planning algorithm. Finally, experimental results show that DGCL outperforms other baselines on different datasets, GNN model, and GPU topologies. So please feel free to ask any question.
All right, thank you, Jean-Kun. As usual, let's see if the audience has questions. So I will start with one. So we have seen in the previous presentation that sometimes it's useful to aggregate the networks where you might want to aggregate from a different set of vertices, which might not be all your neighbors. I just wonder if how easy you think would it be to extend your library to deal situations where you're not fetching all the time from all the neighbors, or whether your library actually already supports that.
Yeah, so you mean each time we do not need to fetch all the vertices from other GPUs, right?
Right. Given a vertex, maybe you only need some user application-defined subset.
So in our setting, we only need to fetch some necessary vertex from other GPUs. We don't need to all the neighbors or all the vertices from other GPUs. We only fetch those
remote neighbor of the current GPUs. Yeah.
Right, but I think you assume that the GNN still requires to aggregate for each vertex all its neighbors, right? Regardless whether they are local or not. And then if they are remote, you fetch them, right?
Yeah. So normally GNN has multiple layers. So in each layer, we only need to fetch the one hot neighbor of the current vertex. Yeah. Mm-hmm. So for vertex, for all the vertices in a GPU, in each layer we only need to fetch their one hot neighbor from other GPUs, and then we can continue the computation, and then we go to the next layer. So for the next layer, we also only need to fetch the one hot neighbors. Yeah, we don't need all the vertices for other GPUs. Yeah.
Okay, thank you, Jenkun. Let's see if there are other questions. We have one. So 2 questions. What is the overhead of choosing the best communication strategy? Let's start with that one.
Yeah, so that's a great question. Yeah, so the overhead of the Planet algorithm is about several seconds to or at most 1 to 2 minutes in our experiment. Yeah, we already choose some very large graph. Yeah, so compared with the long training time, I think the complexity of the Planet algorithm is not very large. Yeah, so the cluster is down for one different one. It's down for one and more frequency basically. So during the training, we need to do the communication planning before the training. Yeah, so in each training, so for the training of one GNN model, we need to run the partitioning algorithm once. But if you use the graph for different training, yeah, so you can use the same planning algorithm, planning results. Yeah. So did I answer your question?
Yeah. So the question is whether we should do this once per deployment or once per application. Maybe we have time for one more question. Quick question. Otherwise, all right. So I thank Jenkun. And the next talk, thank you very much, Jenkun. The next talk is OFC. Yeah, it's OFC, an opportunistic caching system for function as a service platforms. And it deals with optimizing the use of memory in this kind of cloud environment. So very interesting work. Let's start with the video.
Hello, my name is Mathieu Bakou, and today, together with Job Mondo, I will present to you OFC, our system for an opportunistic fast caching system. We are talking about function as a service here, so this is fast. It's a cloud paradigm where you build cloud-native applications as a composition of several smaller functions. Each function really is a piece of code written as a function that can scale independently. And you can also compose functions in order to provide each smaller feature of your overall application. It's tied to serverless computing because you don't manage any service that is based on servers. For instance, you don't have any web server in entry. You actually use services like triggers or API gateways provided by the platform. And also on the backend side, you don't use object stores or database servers that you deploy yourself. You use the services provided by the cloud platform. In this picture, we mostly use a pattern for building functions that is called extract, transform, and load. It's very simple. It's because functions are most often stateless. So when actually making a process, you process data by first extracting the data from a remote storage, then you transform the data, and finally you load the data back to the remote storage. And you can see that accessing the remote storage is very central to the well-functioning of the application. And indeed, this is also the main issue when we have a look at the latency of invoking a function. When invoking a function, you have the phase of preparation that is actually a bit long, and it only concerns the fast platform. But when I'm actually executing the function, extracting and loading the data takes the major part of the function latency most often. We are of the order of 100 milliseconds or maybe up to a dozen seconds. And so accessing the remote storage is a big issue, and we have the problem of data locality because we have to access this, well, out of infrastructure, remote storage, and it's even worse for function pipelines where the output of one function must be loaded to the remote storage before being extracted back from the remote storage to the next function, etc. for the whole chain. When we have a look at the past work, obviously the solution is caching. However, most of these existing solutions require to modify the functions to actually make use of the cache, and also to provide explicitly extra resources to provision the cache. Here, what we propose is indeed a caching system, but very adapted to the intrinsic characteristics of the fast platform. In particular, first, the very short latency, I talked about this just before, and also that is very elastic. That is to say, we can scale down to 0, and also we can scale up to a great number of instances very quickly. These changes, linked to the nature of fast computing, are answered by our system, opportunistic fast cache. It's opportunistic because we gather memory that is unused but reserved, and we will see on the next slide why there exists memory that is unused but reserved. This memory is fed into an in-memory scalable system. This makes it suitable for function as a service platforms. And this system indeed is a cache that is transparent, efficient, and reliable. And this is how we provide it, I want to say, for free to the client functions. So indeed, we have unused reserved memory. It comes from the fact that the clients that deploy the functions, they want to accommodate for any workload that their function might encounter, meaning that they over-provision memory. You can see here this on the right, where the function uses maybe 20% of the booked memory here. So this is the first source of unused memory, of wasted memory. The second source is that in fast platforms, we try to reduce the latency of invoking a function by keeping alive the function's runtimes. But for the whole time a function runtime, so I also call this sandbox, the whole time a sandbox is kept alive means that we keep memory reserved. And all of this wasted memory here can be gathered in a cache. However, we need to understand, to know how much memory we can take from a function that is going to be invoked. To do that is very difficult because the relation between memory and any input parameter, such as the input image size, input data size, I would say, so this is the example of an image blurring function, right? And you have a first parameter that is the size of the input, and also it could be function-specific parameters such as the blurring radius here, right? And you can see that the relation between memory usage and any input parameter is very complex. So we have to use machine learning to understand, to predict how much memory can be used. And actually, it's very beneficial to use machine learning in the fast context because we have a lot of information about the functions. For instance, we have the actual explicit list of parameters, and also functions are invoked at a very high rate, meaning that we build a training dataset very quickly. Indeed, we use machine learning, so we actually made a very thorough study of many machine learning algorithms in the paper. Here, I just want to put the accent on the fact that one characteristic that we looked for in machine learning algorithms was the prediction speed. I said that functions are invoked with a latency of the order of 100 milliseconds, so we need to ensure that the prediction takes maybe around 1 millisecond only. And our choice was this decision trees, a very simple trees, not even random forest, because random forest takes too much time to predict. So we decided to use a certain algorithm of decision trees. This is how we answer, how we respond to the challenge of gathering unused reserved memory. And now, Job, we explain to you how we built a caching system from this memory and how we provide it for free to the client functions.
Hi to everyone, my name is Job Vonder. I'm going to present you the details of our in-memory caching system. So our caching system leverages HamCloud, which is a famous in-memory caching system, distributed and also fault tolerant, where we have several nodes that we call master nodes that will store data in the memory based on logged structured mechanisms. And each master is going to also have a backup that we enable to replay the log stored on other masters. So the overall is managed by a coordinator that is going to receive requests from third-party applications that will communicate with the distributed caching system via API that will enable it to read, create, delete, or even update objects in the distributed caching system. So on each invoker node, that is the node that will be responsible to process the function runtime. So we have a RAM Cloud master that will be collocated on this node, and the memory that the RAM Cloud master will use on each invoker node will be managed by a cache agent. So the cache agent here is a component that will perform the cache auto scaling on the invoker node. So we will monitor the cache pressure, so the pressure we are imposing on the invoker's memory with the RAM Cloud master cache system, and based on the situation, it's going to know if you can perform an upscaling or a downscaling. So this component also performs garbage collection in order to periodically free some memory. We must also provide a transparent mechanism that will also ensures consistency with the remote storage nodes. So how do we achieve transparency and consistency? For transparency, we have a proxy component that is going at runtime intercept the function calls to the remote storage nodes and is going to route them to our RC library. And upon reception of the request, the RC library will now be able to perform the demanded request, which is basically going to create, update, or even hide information in the distributed caching system before committing to the remote storage node. So we also ensure consistency in the case where a user goes directly to the remote storage node without passing by the fast platform. So in this case, we have a webhook on the remote storage node that is going to confirm with the caching system that, okay, does the data I have the latest version, and they are going to sync up before sending the result to the user requested on the remote storage node. We evaluated OFC in order to assess the improvement with the execution time of functions with two categories of functions. Single functions, where there is an input that will be processed by the function to produce an output, and multi-stage function, that is a chain of sub-functions where an input will be processed by every function of the chain, and the output of one function will be used as the input of the next function in the chain. We're interested in 5 different scenarios. The first one is using Redis as our distributed caching system, but we needed to update the function in order to benefit from Redis. The second one is using OFC, but with data locality situation that is really nice, where the input needed by the functions is already present in the distributed caching system and present in the local cache of the master node, where collocated with the invoker node that's going to process the function. The third situation is OFC with the input present in the distributed caching system, but not on the node that's going to process the function execution. The fourth situation where the input data is not present in the caching system, so there will be a miss in, when we look up the data in the caching system. And the last situation where the input is on the remote storage node. So these are the characteristics of the servers in the clusters. For time constraint, I'm not going to present every evaluation results here. I'm going to concentrate on some and encourage you to look into the papers for more results. So this is the results for two single functions, where we plotted the execution time and we tried to separate the extract, load, and transform phases. And we can see that when the input is already present in the cache and present on the local node, we are able to overcome Swift by 82% and be really close, really close to the result of Redis. Same observation for multi-stage functions where we overcome Swift by up to 60%. So overall, OFC leverages machine learning and RAM cloud in order to propose an opportunistic caching layer that will benefit to functions without needing some modifications. OFC ensures consistency between the cache and the remote storage nodes, and the preliminary evaluation shows that we can achieve good improvements up to 82% for single functions and 60% for multi-stage functions. So the overall code of OFC is available on this URL that you can also find on the paper. So thank you for your attention, and if you have any question, we will be glad to answer them. Thanks.
All right, thank you, Matthew and Job. We do have a question from the audience. So Mohammed is asking, if a function invocation rate is high, its container memory is not sitting unused, and the wastage you motivated with is not a major problem. On the other hand, if the invocation rate is medium to low, that's when keeping things alive helps with preventing cold starts. Now, for these functions, it would take a long time to observe a representative set of input parameters and find the relation with memory usage, days or weeks. So the question is, how does your system deal with incomplete set of inputs when predicting memory usage during this long bootstrapping period? So before you amass enough time, data to actually decide what's the right thing to do, how does the system adapt?
Yes, thanks for the question. So indeed, there are two parts here. The first part is a misconception. If the function invocation rate is high, it still means that there is unused memory, because the memory is unused not only because the function does not run, it's unused because the function reserves too much memory for any invocation it will ever see. So even when the function is actually running, actually being invoked, you will have unused memory. This was shown in a slide around 1/3 of the presentation. This is one source of unused memory. And the second part of your question is about how we handle functions that have a lower rate of invocation. Well, first, it doesn't happen that often, actually. There are sources that say that maybe at least 95% of functions are invoked at least once per minute, I think, which means that actually the vast majority of functions are invoked very frequently. And even if there aren't, the keep alive policy will still kill the sandboxes. The sandboxes remain alive for about maybe 10 to 15 minutes. Obviously, it depends on the platform. So then you won't have any wasted memory when they are killed. And as for the learning and predicting part, we have put in place, let's say, algorithms to determine whether the model is accurate enough to actually be used to reclaim memory. I will let you have a look at the paper on the actual formulas, but we have we have a maturity threshold that we wait before actually using the predictions to reclaim memory for the sandboxes to feed them to feed it to the cache.
All right, thank you. And actually, I had another question. I think we are running out of time, but I was also wondering about what happens when predictions are incorrect, basically when you do the wrong prediction, but I think you you kind of implicitly answered that you have this kind of startup time where you have this kind of default behavior, right?
Yes, and in addition, we also are very conservative in our predictions in that we don't reclaim all the memory that we predicted we could take. We leave some room for prediction error, of course. Indeed, a major constraint of our system was to ensure that we do not affect too much any function. This is the opportunistic part.
Thank you very much, both Mathieu and Job. And let's move to the next talk, which is C-star. And it's a paper that proposes a new programming paradigm for GNNs and specific optimizations that leverage that vertex-centric programming paradigm. So I will give the, let's play the video, and then we have Yidi to answer questions.
I'm Yidi. In this talk, I'm going to present C-star, vertex-centric programming for graph neural network. Graph neural networks are designed to learn rich information from graph data, such as social networks, knowledge graphs, and more. In the figure below, the performance of GNN models are marked with red boxes. GNNs achieves better performance than traditional methods in many graph tasks, such as node classification and link prediction. The computation pattern of GNN can be characterized as C-star, and we illustrate with the left figure. The pattern of GNN layer is like star from the view of a single vertex. GNN dataset usually contains graph structure and the initial feature of vertices and edges. In the source stage, features of source vertices are transformed using neural network operations. In the edge stage, the feature of source destination and other edges interact with each other. The aggregation stage aggregates the transformed feature to the center node. We show two examples of this C-star pattern on the right. On the top is graph convolutional neural networks, or GCN. GCN simply aggregates neighbors' features by summing them up. Below is the graph attention neural network, GAT. It additionally computes an attention score on each edge, which indicates the importance of different neighbors. Existing GNN frameworks provide various programming abstractions to help users to program GNN models easily. DGL provides the graph abstraction. Feature vectors are grouped into tensor, then stored in the graph. Graph provides methods for conducting computation. For example, updates all executes two functions for the whole graph, one message function and one reduce function. Heterogeometric, PYG, and new graph require users to organize GNN computation into stages of tensor-wise operations. PYG provides message and update, while new graph has SAGA pattern. GraphLearn and OLA focus more on sampling-based training. GraphLearn provides a Gremlin-like API to express the sampling operation. They rely on the tensor operations of deep learning backend, such as gather and the segment sum in TensorFlow. For execution, tensor materialization is the most commonly adopted approach. Users construct input as tensors, and within stages of C-star pattern, tensor operations of deep learning backend are carried out one by one. Across stages, scatter or gather operations are inserted by the users or by the framework. DGL proposes the general-purpose sparse matrix multiplication (GSPMM) optimization, which implements specialized kernels when using built-in message and reduce functions. We identify the limitations of existing GNN frameworks as follows. Though their programming abstractions are expressive enough, users need to cast the vertex-centric pattern into a whole graph and coherent tensor program, which may be non-trivial for complex models, especially multi-head graph attention neural networks. Besides, users need to learn a set of low-level tensor operations or domain-specific APIs. For execution, tensor materialization causes high memory consumption and bad locality due to frequent data movement. GSPMM only covers a limited set of operator combinations and delivers unsatisfying performance due to the kernel design, as we will compare in the experiments. To address these limitations, C-star provides a more intuitive vertex-centric programming model. Users can program GNN models with native Python constructs, such as list comprehension and reduction. C-star then dynamically compiles the user-defined model into fast and efficient kernels. We show GCN and GAT's implementation using vertex-centric programming model. For the GCN model, user writes a Python function with center vertex v as argument. Within the function, users can access the neighbors list with v.inNeighbors. For each neighbor node u, we can access its feature vector by using the dot operator. Then we can use list comprehension to construct a list of neighbors feature. Finally, we sum the list and return the output. For the GAT model, we first compute feature list E by sum center vertex V's feature and its neighbor's feature. Then we perform leaky ReLU and exponential function on the result. The alpha is the attention score, which is computed by normalizing each element in E by their summation. Finally, we multiply the feature of neighbor vertex U with the attention score alpha and return the average. The benefit of vertex-centric programming is bidirectional. Users can implement a GN model easily, and users can learn the GN model by checking its implementation directly. Now we describe the code generation process of C-star. The tracer takes the vertex-centric program and records each operator in the forward computational graph with operator overloading. It also verifies the correctness of user's program. We embed an auto-differentiation module to derive the backward computational graph. Both graphs then go through a series of optimizations. C-star then generates and compiles CUDA kernels for the optimized computational graph. We use GAT to illustrate. The computational graph of GAT is shown in the figure, where rectangles are input data and circles are the operators. The tracer additionally annotates each operator to denote where the operator is executed. For example, the add operator takes input from the source and destination vertex. Therefore, it should be executed on edges. We denote its graph type as E. Leaky ReLU only takes input from the add operator. Therefore, its graph type is also E. We denote some operators' graph type as A, which stands for aggregation. Then the operator fusion optimization fuses the computational graph into two operators marked in the gray region. Please refer to our paper for details of the fusion algorithm. This is the optimized backward graph of GAT. The whole computational graph can be fused into a single operator. Next, we describe how C-star executes the fused kernel. We first exploit the feature-wise parallelism by using FAT. An FAT is a group of consecutive threads. FAT's size is determined by the feature vector size and is set to be a power of 2. For the first few GN layers, the feature vector size is usually large. So we make the feature group size to be large. In the figure, we show a case where feature size is relatively small, 16, and we set FAT group size to be 16. Each FAT group is assigned a single destination vertex. The FAT visits the source edges one by one and carries out the computation and aggregation sequentially. This strategy avoids the aggregation conflict at destination and improves the data locality of destination feature. However, FATs may end up with skewed load, especially for power law graphs, in which some vertices have much higher degrees than others. We also propose dynamic block scheduling. Specifically, we launch as many thread blocks as needed, so that the number of FATs is no less than the number of vertices. This approach alleviates the workload skewness compared with static assignment. It also reduces the cost of atomic-based dynamic scheduling. To further reduce workload imbalance, we introduce vertex degree sorting. Our key observation is that in GNN training, graph structure is either fixed or is independent across mini batches. We can sort the vertices in descending order of their in-degree. The benefits are twofold. First, we can further elevate the straggler problem by assigning early launched thread blocks to vertices in the front. In this case, computation of high-degree vertices can be overlapped with that of low-degree ones. Second, when feature size is small, a thread block can consist several FATs. By sorting, consecutive vertices will have similar degree. Therefore, FATs in the same block will have similar amount of workload. Intra-block load imbalance is reduced. We compare memory consumption and epoch time in C* with DGL and PYG using 3 models on 9 datasets and 3 hardware platforms. C* uses less memory, especially for complex models trained on large graphs. Besides, C* is consistently faster than other systems. C* achieves up to 14 times speedup compared with DGL and 3 times compared with PYG. The better performance is mainly due to operator fusion and the kernel-level designs were presented earlier. We use a neighbor access benchmark to test the effectiveness of the kernel-level designs. The horizontal axis is the feature size of vertices, and the vertical axis is the relative speedup compared with baseline. We use DGL's edge parallel strategy as baseline, and we incrementally add C* design to the scheme. The result shows that C* is more than 900 faster than the baseline. FAT and sorting can significantly improve the performance, especially when feature size is small. To summarize, C* provides a vertex-centric program model to make it easy to write and learn GNN models. C* achieves better performance by applying optimizations such as operator fusion during compilation. This is the end of presentation. Thanks.
All right, thank you very much. So we have Yidi here. I will start with one question. So I think one interesting aspect of your work to me is the way you explore different ways to perform kernel fusion that are tailored for GNNs. So do you think there are interesting opportunities for kernel fusion that you have not addressed yet? Yeah, that's the question.
Yes, I think both kernel fusion opportunities we have already explored because we try to aggressively apply operator fusion towards GNN as the computation of GNN is rather light, and they want to minimize the data movement by leveraging operator fusion. So currently, I think most operator fusion opportunity has been exploited in C*. Yes.
All right, thank you very much. Let's see if we have more questions. Otherwise, I believe in the interest of time, we should move to the next talk. So thank you very much, Yidi. The next talk is profiling data flow systems on multiple abstraction levels. The speaker is Alexander, and this is a very nice talk because it explains how we can make sense of performance in systems that have lots of compilation layers. So let's start with the video.
Hi everyone, my name is Alexander Beischel and I will present our paper Profiling Data Flow Systems on Multiple Abstraction Levels, which was joint work with Timo Kersten, Maximilian Bandle, Jana Gitscheva and Thomas Neumann. In our paper, we show how to profile compiling data flow systems at higher abstraction levels so that all developers of the data flow system can benefit from comprehensible profiling results and optimize their parts of the system. Compiling data flow systems are very versatile and used in multiple areas, like for example in graph neural networks, as you just saw in the previous talks. However, this talk won't be about graph neural networks, but about making your life as developer of a compiling data flow system easier during the performance profiling. And probably every one of you working on a compiling data flow system knows the following situation. So I'm running a data flow expression in a domain-specific language or a query in my data flow system. Now the system parses and optimizes my query to generate query-specific code that is optimized for the underlying hardware. Then we execute this generated code to actually run the query, but for some reason, it's not as fast as I would have expected. As a good engineer, I now want to figure out where my time went lost, so therefore I execute my query again, but this time I profile the execution of the generated code using perf. And now hopefully perf will tell me exactly where my time was spent, so I can tune my system again to make my query super fast. However, these are the results we actually get. And now I see that this particular line of assembly is very expensive, but it doesn't match any of the lines I wrote in the compiling data flow system, and I can't even assign it to a part of my written query. So I'm no step further, and I will have to do a lot of reverse engineering to maybe figure out where my time was lost. But why can't we just attribute our profiling results to the components of our data flow system like we do it all the time in traditional systems? The reason is the following. Compiling data flow systems take a query and transfer it to a data flow graph. Then they perform multiple consecutive lowering steps to perform complex optimizations like operator fusion or reorderings. In the last lowering step, we generate query-specific code optimized for the underlying hardware. Then we compile this generated code and execute it to actually run our query. Now, if we profile our query execution, the samples we get will actually contain results of our generated code, but not of the data flow system. And with the attached debug information, we can assign the instruction pointers of the profiling samples back to assembly or machine IR instructions. But still, the results we see are not parts of our data flow system, but it's the generated code our data flow system generated with the code generation engine. These profiling results now might be useful for the developer of the code generation engine. But for any developer of a higher level in my data flow system, they are too low level to make any use of them. Still, those developers would need profiling results mapped to their components of the data flow system to optimize also their components. In traditional systems, if we don't know to which part a sample belongs, we profile it again using call stack sampling, for example. Then we inspect the recorded call stacks to see to which components our sample actually belongs. However, this is not possible for compiling data flow systems. The reason therefore is the following. Our generated and executed code is actually decoupled from the data flow system itself, because we generate this code with our system's code generation engine, then we compile it and execute it again. So in short, we have a gap between our generated code and the data flow system itself. Now, to get comprehensible profiling results again, we need to re-establish the connection between our data flow system's components and the generated code. And now, inspired by the way debuggers attach debug information to map instruction pointers back to lines of code, we developed tailored profiling to solve this. Tailored profiling re-establishes the connection between the generated code and the data flow system by tracking the connection between the components of the different levels of our data flow graph down to the generated code of our data flow system and preserve this information of the lowering process. Then, when we profiled our query execution, we used this information to map our samples with lines of generated code back to the components of our data flow system. With this, we can then achieve comprehensible profiling results because we now get results for the components we're actually working on. And we do this with two main ingredients, the tagging dictionary and register tagging. Now, what we do is, during the lowering process, we already have all information available to connect the components of the different abstraction levels from the data flow graph down to the generated lines of code. But we usually just drop this information. Therefore, with tailored profiling, we preserve this context and this connection information and then store this information in a central tagging dictionary. For each sample, we then just look up the entry in the tagging dictionary to map the instruction of our generated code in a bottom-up fashion to all the components of our data flow system. And after connecting all the samples to the components in the data flow system, we have comprehensible profiling results again. So now you saw how this works conceptually, but let me just show you how this works in detail in a short example. So for simplicity, for this example, we will assume that we directly lower our data flow graph down to generated code. And we will skip all the intermediate levels and steps, but we explain them in detail in the paper. So when we now lower our data flow graph operators and generate code for them, what we will do is, for each of our generated instructions, we will store a mapping pointing from the instruction that we have generated to the data flow operator for which we actually generated the instruction. You can imagine it just like a hash table where we store for each instruction the responsible operator. And we do this for each of our operators and basically for each of our generated instructions during the code generation. So now if we have a sample with a generated instruction, we just need to look up in the tagging dictionary which operator was responsible for generating it. This works for most of our generated code. However, there is a small catch. We also generate so-called shared functions in our code. That means we generate the function once in our generated code, but then call it from multiple locations of our generated code again. For example, we implement malloc just once for our generated code, but then call it from within the scan and also from within the filter operator. If we now have a sample from executing this shared malloc function, we cannot determine which operator actually called it. So one way to solve this would be using call stack sampling. Again, we record the entire call stack, inspect it to determine from which operator malloc was called. But call stack sampling is quite expensive, and many data flow systems run on native hardware, so we have full control. Therefore, we came up with a far more lightweight solution to disambiguate such shared functions. We call it register tagging, and in difference to call stack sampling, we have very little overhead. So we just have 3% query runtime overhead instead of multiple times our query runtime, for example, sometimes with call stack sampling. And what we do is the following. We exclusively reserve a machine register by telling the compiler to reserve it so that we can only use it for our tagging itself. Then we use this machine register to tag at query runtime which operator called the shared function. Therefore, we just write a unique identification tag in the machine register whenever we call a shared function. Therefore, we enclose this function calls to our shared function with tagging instructions, which basically write the identification tag into the machine register before calling our function malloc. And then, when we take a sample while executing malloc, in addition to just the instruction pointer, we also record the content of our machine register we use for tagging. Then, if we have a sample for a shared function, in order to disambiguate it, if we have multiple matches in our tagging dictionary, we can just inspect the recorded register value, which contains the identification tag. Now, after finishing our function malloc, we just reset the register and we do the same for each call of a shared function. With this, we have a very lightweight alternative to call stack sampling for disambiguation, and now we can map all of our generated code instructions back to their higher level components of the data flow system. So now that I've showed you how tailored profiling works, let's show you what you can get from it. So we've implemented tailored profiling in our production-ready compiling data flow system Umbra, which is a relational database management system. And all the use cases you will see now are real use cases we had after integrating tailored profiling. So what we do with tailored profiling, for example, is we assign for each of our data flow operators how much time we spend for it during the query execution. So then we know exactly how expensive they are. We can also monitor the time and the activity of each operator over the entire query execution time. So therefore, we will see the interaction between different operators, also correlations, and we can even detect local bottlenecks and then optimize them. But we are not limited to any specific events, like, for example, tracking the activity. But tailored profiling can handle all performance monitoring events because it basically just maps our samples back to the components independently of the event. We can therefore, for example, also profile memory access patterns by using memory load as performance event. And just to recap, we can do all of that just by closing the gap between our compiling data flow system and the generated code with tailored profiling. Thereby, we can now map the samples of our executed code back to our system's components and provide useful results for all developers. Our approach is very lightweight and has a high accuracy. We can map back 98% of all samples to our components. Further, we have little implementation overhead, so our approach is easy to integrate and also transferable to many systems. Our current implementation prototype in Umbra already works for profiling code executed on CPUs of multi-core and multi-socket machines, and now we're extending it in the future to heterogeneous compute resources and distributed systems. So thank you very much for your attention, and I'm happy to answer your questions now.
Thank you, Alexander. And I have a quick question, actually. You mentioned that the approach is applicable to many systems. Are there specific assumptions that you do that make it not applicable to some systems? In other words, how do you comment about the applicability of the approach?
Yeah, so I think that the general idea of using the tagging dictionary and register tagging itself works on most systems, but I cannot give you any, let's say, any valid expectation how it works if, for example, we now take network cards into it, so communication between different nodes. Our prototype right now was implemented on a single machine. So for all systems working on a CPU, we know it should be applicable. However, if, for example, you now ship to a GPU, we expect it to work, but it can't guarantee it because our system is not using the GPU itself. However, as long as you do have samples that contain any information like instruction pointer or sysline so that you can map it back to your system itself, it should work.
Thank you very much, Alexander. Unfortunately, I think we have reached the end time of this session. I would like to thank all the speakers and the attendees, and I invite everybody to the next session. Bye.
Okay, so we were planning to play the sponsor video, but maybe the volunteers are not able to do that. If anyone from the General Assembly session want to test the microphone or video, feel free to do that. We still have 5 minutes.
Should I play a video of Edinburgh now?
Yeah, I mean, I think it's okay, but I don't know. Yeah, yes, I think it's okay, but I don't know if anyone wants to do any test. Okay, so yeah, we can see Andy, we can see him, yeah. But I think I saw also Anthony Rostrom. I can see Peter.
Yeah. Okay, you don't have to. You don't have to name everyone there because it's supposed to be. Yeah.
Oh, okay. we can cut it later.
No, it's live stream, so it's okay. Yeah. Okay. Yeah.
Okay.
Hi. Yeah, we can hear you.
I can hear you. Okay, so I think. Sorry, Pramod,
can you announce this on the general list? I would say.
Yes.
Okay, that'd be great because then we can start. Okay, Peter, are you there?
Yes, I am. So shall we start?
Okay, so yes, I think we can start. I think we are on time, just 2 minutes over the schedule. So welcome everyone for the General Assembly. And it seems we are all there. I'm just checking. So I would give it to Peter, who will start the proceedings now. Peter?
Yes, thank you very much, Pramod. So yeah, so this is the EuroSys General Assembly. So this is something that we do every year at the conference, which is an opportunity to hear from the organizers, to hear from the community, and also to discuss any other EuroSys business that we may have. So my name is Peter Pizzo from Imperial College London. I'm currently the chair of the ACM SIGOPS European chapter. So EuroSys is not just a conference, but we're also a SIGOPS chapter in Europe, and therefore we have a set of officers. So there's myself as chair, then we have Dushyant Narayanan as vice chair, Adam Morrison as treasurer, and Luis Vega as our secretary. So this is the current set of officers, and actually one of the things that we're going to do today is hand over to the newly elected set of officers. So what are all the things that the EuroSys chapter does? Well, so what we try to do is we try to be a focal point for European systems research and to promote systems research in Europe. And we have a number of activities. So we run, for example, a job listings website for systems-related jobs in Europe. So the ACM EuroSys chapter is supported through membership. So I encourage everybody who isn't already a member to sign up. We have quite a significant student discount, and we use the income from that membership to fund student travel and to support the EuroSys conference in various ways. Next slide, please. So one other thing that we do is that we also give out a number of awards and prizes, and we've seen those, some of them during the opening today. So the Roger Needham Award for the best PhD dissertation, the Jochen Liedtke Young Researcher Award, and the Test of Time Award. And there will be more awards here during the General Assembly. So in particular, we're going to hear about the EuroSys Lifetime Achievement Award that will be given out by Andy Tannenbaum, and it's an award that we give out every 2 years. So next slide, please. EuroSys is supported by a steering committee. So this is the current membership of the EuroSys steering committee. So I'm not going to read out all of the names, but these are the people who you want to talk to if you have any particular suggestions, feedback, if you want to discuss how we organize EuroSys conferences and how we work with the community. These are the people who you want to chat with. So this is the agenda for this hour. It's very, very packed. I think we've never had so many different agenda items. I mean, part of the problem is that we don't have a banquet to give out awards there. So we're going to do a bunch of things here. So first, we're going to hear from the current EuroSys organizers. So the general chairs are going to talk to us about their experience, and then we're also going to hear from the artifact evaluation chairs, who also have an award to give out, and from the Shadow PC chairs, who will also share an award. And they will hear about finance and sort of the organization of the conference. Then we have more awards. So there's going to be a community service award that will be given out this year, and the Lifetime Achievement Award. And then there'll be also some more business about the EuroSys chapter in terms of the finances that we're reporting and the future running of the conference. And then, as I've mentioned, we need to pass on the EuroSys officer roles to the new set of incoming officers, and this will be then done by Tim, who has very kindly led the election that we ran for those roles. And then finally, we're going to hear about EuroSys next year and where it's going to take place. So given this packed agenda, we have very, very little time for any discussion. So therefore, what we'll do after the General Assembly, we'll simply use Slack to have any further discussion, feedback, and comments from the community. So with that, I'll hand over to Pramod and Antonio, who will talk about EuroSys this year.
Oh. All right, so thank you very much, Peter. On behalf of EuroSys Organizing Committee for 2021, I would like to welcome you all to the General Assembly. My name is Pramod Patotia. I'm a professor of computer science at the Technical University of Munich, as well as at the University of Edinburgh. And along with my colleague, Antonio Bablas, at the University of Edinburgh, we organized EuroSys 2021. So Peter asked us to share our experience for organizing EuroSys. I must say that it was quite tiring, to be honest, because a year back, we thought about organizing the conference in physical location, and we actually planned a lot of things to host the conference from in physical world in Edinburgh. And as you can imagine, we actually had very high hopes to invite you, all of you in Edinburgh, in a beautiful city, actually. And the plan was to organize conference in the central location in Edinburgh. As you can see, the city center. We booked the most prestigious venue in Edinburgh for hosting conferences, right in the George Street. And also, we wanted to host you for banquet in the National Museum. And fortunately or unfortunately, we booked all of these contracts, including catering and everything, and we had to cancel and redo every work. And it was really a massive effort, and it was not possible without our team. So we finally stick to a virtual conference, and our recipe was that we would use only minimal tools. So we didn't want to have too many tools, and we thought carefully about the minimal set of tools that we want to use it, because we don't want to overburden juggling with different tools. And this is how we organized the conference. I explained you in the session in the morning how do we plan to use these tools. This is a slide that I just want to repeat from the morning one. It's an artifact that we were able to keep registration free thanks to our sponsors. We have a really large participation, and these are really high numbers, more than 1,600 participants, and covering large number of students, as well as large presence of European systems community here as well. But unfortunately, female participation is low. But overall, we have a record participation in EuroSys this year. We are very thankful to our program chairs, namely Lorenzo Albisi and Christian Carter, who actually did a phenomenal job. And as you can see that we did really a lot of new things this year. So we did actually 3 new things, and this was not possible without their help. We were able to introduce a new something called revision stage, like databases and programming languages, and also artifact evaluation, which will be covered later in the by our artifact evaluation chairs. Yeah, so overall, the idea behind these 3 changes was to actually, we wanted to improve the review and program quality. And I think we can all see that it actually helped us to make some forward steps in these directions. And I'm very, very happy. We are very happy that we were able to adopt these 3 new things within a strict timeline. So as you can imagine, that incorporating revision stage with artifact evaluation is not so easy, but the team managed to do so. So we are very, very proud. For workshops, it was a mammoth task taken by Jana and Jolst from our workshop chairs, and they were able to actually include a record number of workshops. As far as we can check it out, it was EuroSys 2008 in Glasgow that had a similar number of workshops, but we were able to actually have 8 workshops. And as you can see, that these workshops are an integral part of our community, and we are very happy that they were well received and well attended yesterday. In addition to that, we were able to continue our efforts to promote young researchers. And this direction, we had two programs that were running. One was the doctoral workshop, EuroDW, that we run annually with EuroSys. And this year it was chaired by Boris and Irene. And in addition, since PhD students are the ones who are suffering from this COVID stuff, we actually also put a lot of effort in mentoring aspects. And this year, Pedro and Natasha were able to help us to actually run this mentoring sessions. Lastly, we also wanted to spice up the program, and this is why we incorporated AMA sessions, Ask Me Anything, and we actually had a lot of fun. I received very positive feedback from all of you, and this is managed by Vasia, and we had 5 phenomenal speakers, as you must have heard from Andy, Willie, and Anna Mary, and it was a lot of fun. So we will have 2 more speakers aimed up tomorrow. And I think it was a good initiative actually aimed at community building, and people were asking really both technical and non-technical questions, and it is fun to actually listen to these speakers as well. With that, I would give over to Martin Kleppmann, who would be representing our artifact evaluation committee. So Martin, please.
Great, thank you, Pramod. So I led the artifact evaluation together with my co-chairs, Cristiano, Giuffrida, and Cornelius Curtis. Thank you very much to them for helping a lot with this process. So a little bit of background on what artifact evaluation actually is. The background here is really trying to improve the reproducibility of scientific research, essentially. And so typically with the review process at a conference like EuroSys, the reviewers will review the PDF of the paper, but not any of the work that's actually behind it. And so what we've tried to do here is to also evaluate the work that went into a paper, which means the source code, the configuration for running the experiments, any data sets that came from this, maybe any models, any tests, any benchmarks, and so on. And there are 3 possible badges that authors of papers can get if they want to. So the whole process is voluntary, but authors could apply for up to 3 badges, and these are standardized by the ACM. The essence of these badges is artifacts available, means that the artifact that is the code or any other things has been made publicly available in some way that is permanent and hopefully durable. Artifact functional means that we actually ran the code and made sure that it was working for some definition of working. And results reproduced is the strongest of the 3, which says that actually we ran through all of the experiments and made sure that the results of the experiments matched what is claimed in the paper for all the main claims in the paper. And so this requires actually the experiments to be complete as well, and for the outputs, the results to be within the error tolerances of what the paper advertises. So a few words on the process of how we did this. So we did artifact evaluation for the first time at EuroSys. It's kind of a new idea in the systems community, even though it's been done for a while in the programming languages community, for example. We recruited a committee of people who helped with the artifact evaluation. We had 50 members of this artifact evaluation committee, so huge thanks to them. They put in a lot of work because actually running an evaluation can be quite a significant amount of work of actually making sure you get everything running and interpreting the results and reviewing the code and so on. So we had a very nice mixture, any PhD students, but also some postdocs, some software engineers from industry who came. We had an open self-nomination process for people who could self-nominate themselves if they wanted, and we selected the committee members from this. Because we had so many committee members, we only needed each individual member to do 1 evaluation, which was great because that way the workload for each individual was not too great. And we had each artifact independently evaluated by 2 or 3 of the committee members. You can find the full results, including the badges that we awarded to each of the papers, on this website here, where we've teamed up with OSDI and SOSP to put together an artifact evaluation website for the systems community. So I think it's time to for the awards. So we have awarded one Best Artifact Award, with which we want to recognize an artifact of unusually high quality. And we considered a number of criteria for this, in particular, the quality and completeness of the code and the documentation and the tests, and how easy it was to run the experiments and to reproduce the results. And we had particularly good feedback on this particular paper that from the reviewers. It's called a Site-to-Site Internet Traffic Control, and it's by Frank Kankaliosi, Akshay Narayan, Pratish Goyal, Ratika Mittal, Mohammed Alizadeh, and Hari Balakrishnan. So huge congratulations and great work for doing such an excellent artifact, where the reviewers commented that the code was highly readable, the automation was very well set up, and so we would like to recognize and thank the authors for putting so much effort into their artifact. Next, we have an award for the reviewers, and so as we recognize that it's a lot of work to do a good artifact evaluation, we also wanted to recognize some of the members of the Artifact Evaluation Committee who put in particular effort to conduct a very thorough evaluation, to very clearly discuss in their review what was evaluated, what the results were, what the outcome was, and so on. And so our award here goes to Al-Amjad Tariq Istaif from the University of Cambridge. Thank you very much, Amjad, for your excellent review and your help on the Artifact Evaluation Committee. And because we had so many great reviews, we also would like to make 3 honorable mentions to 3 further members of the Artifact Evaluation Committee. In no particular order, this is Daniel Hugenroth, Salvatore Signorello, and Bingyu Shen. So thank you to all of them and all of the other members of the Artifact Evaluation Committee for their great work and for helping promote the cause of better scientific reproducibility. That's all from me. Thank you.
Hi, I'm Noah Zilberman, and I co-chaired the Shadow PC together with Kostin Raichu. Next, please. So for the Shadow PC, we had the self-nomination process where we had selected 90 Shadow PC members of all the applications. The requirement to be a successful applicant was to be for the first time on a Shadow PC, simply because otherwise we would have had too much or a TPC that is too big, and to be either a PhD student or an early career researcher. We had 80% PhD students, 12% postdocs, and 8% more early career researchers in industry. And these applicants came from 19 different countries all around the world, from Japan and Australia to North America. The main goal of the Shadow PC is to promote early career researchers. So our goal was not just to provide feedback to the authors, but also to help early career researchers in our community to grow, to understand how the review process works and to practice before they become PC members as a EuroSys next year. Next, please. So all in all, we received 136 of the papers that were submitted to EuroSys and that opted to take part in the Shadow PC process. Each paper was reviewed in 3 rounds. So a paper received between 4 and 7 reviews. We had a virtual PC meeting that lasted 2 half days and where we discussed about 40 papers. Now, before the Shadow PC meeting, we also had a rehearsal where we provided the Shadow PC members also an introduction to how a PC meeting works. So things like what is the role of the discussion lead, how to prepare for the meeting, how to present your considerations, and how we achieve a decision. All in all, the Shadow PC has accepted 52 papers, 4 revised decisions, and 81 reject decisions. And we had the 2/3 match with the main TPC decisions. Next. And we are also happy to give some awards to our wonderful Shadow PC members. Next. So one slide back, if you don't mind. Okay, so I'd like to say before we give the awards that our Shadow PC members actually did a really, really great work, all of them. We had quite a long discussion before we have decided on the awards, because how do we weigh what is really a great PC member? But eventually we have decided that I'd like to thank again all our wonderful Shadow PC members. We're going the wrong way around. And yeah, next, please. And the Distinguished Shadow PC Reviewer Award goes to Ike Kuntz from RWTH Aachen. Congratulations to you, Ike. You've done an excellent work, and this is the time to cheer for him on the Slack. We also would like to give an honorable mention to Reto Ackermann from UBC, who also did an excellent work as a Shadow PC reviewer. So thank you, Ike. Thank you, Reto. Congratulations to you both, and thanks again to all the Shadow PC members.
Yeah, hi everyone. My name is Tudor David, and I'm one of the sponsorship chairs together with Amitabh and Tianyin. Next slide, please. So let me start by saying a really big thank you to all the sponsors that you see listed on this slide, in particular, given the nature of this year's conference. When we started talking with sponsors, our intention was to have a physical event. We had negotiated perks that were tied to the physical nature of the event. We hoped for the longest time that would happen, but eventually we had to switch to the virtual event, and we had to go back to our sponsors, offer them new perks tied to this virtual nature of the event. And yeah, we were very happy that all of them continued to sponsor EuroSys and not one of them pulled out afterwards. In fact, we were able to get even more sponsors after the event switched to virtual. And it's due to our sponsors that we're able to make registration free for this year's EuroSys and attract the widest audience possible. We're happy that we have more than 1,500 registrations. One thing to note is that in comparison to last year's EuroSys conferences, we added 2 high-tier sponsorship levels, Diamond and Platinum, in case some companies want to provide a higher level of support for EuroSys. We're very happy to have already had a first Diamond sponsor, so thank you, Huawei, for that. And besides my sponsorship co-chairs, I'd really also like to acknowledge the work that Pramod and Antonio have done. They went way beyond their duties as chairs, and some of the names that you see on this slide, some of the sponsored names are due to their effort as well. Next slide, please. Right, so a couple of words about our financial bottom line. So because of the sponsors that you saw listed on the previous slide, we have an income of almost $100,000. Some sponsors used dollars, other British pounds, which is why this amount in USD fluctuates a bit from day to day, but we're around that sum. Given that we ended up having a virtual event, our expenses were pretty low, around $3,000. Now, this doesn't include everything. It doesn't, for instance, include prizes and so on, but we don't expect to have expenditures that are much higher than this sum. So the bottom line is that we're left with a surplus of around $90,000, which will stay with EuroSys, and it will be used for the organization of the following year's conferences. And that's very useful because funding tends to vary from year to year, and I think we've had years when we had a deficit instead of a surplus, so this will be very useful. So that's what I wanted to say. Again, a really big thank you to all of our sponsors for making this conference possible. And yeah, back to you.
Okay, so it's back to me. So it's Antonio from General Chairs. Thank you, Tudor, Amitabh, and Jinshu for all your groundwork in grabbing the interest from several sponsors among 3 different continents. So now I have quite a long number of thank you slides, but I will try to do it as fast as possible. First, the proceeding chairs, Cheng Li from USDC and Pierre Olivier from the University of Manchester, they worked around the clock with ACM to come up with the proceedings in a timely fashion, despite the complicated timeline due to the artifact evaluation. So next. Yes, we would like to also thank the publicity chairs, Vijay Chidambaram from UT Austin and Boris Groth from the University of Edinburgh, as well as the publicity volunteers such as Kostis Cafe from Stanford, Yakovos Kolokasis from University of Crete, and Job Mondo from University of Edinburgh. Next. We obviously also want to thank the award committee chairs for their work and being very responsive and available all the time. Andy Tannenbaum for the Lifetime Award that we will see very soon. Herbert Boss for the Lidke Award and Joe Crowcroft for the Roger Needham Award. Next. So definitely there were a lot of groundwork, right? And ACM helped in setting up the contracts and with the proceedings. Special thanks to James Clark Peoples and Adrienne Grishti. And obviously the EuroSys officers were fundamental for setting up the conference and taking very important decisions such as moving the conference online. So thanks to Peter, Dushan, Adam, and also Luis. Next slide. So yeah, obviously there were also many other people such as the local organization team that helped a lot. At the beginning, this, as Pramod was saying, these people helped for setting up the conference local here in Edinburgh, but then they were sort of repurposed as online organization team. So thank you to Paul, Valentin, Tom, Dimitra, Micho, and also Anjo. And yeah, last slides. We had a lot of volunteers, and these are the photos, the screenshot. So this is the first, there are 2 from the mock conference that we ran previous week all together. Maybe you can also show the next slide. It was a lot of fun, and it was really a great experience. So yeah, thank you to everyone. And now, next slide. I will let actually Pramod introduce the Community Service Award. So at least we switch.
Thanks, Antonio. I think the Community Service Award actually is the special award that is given this year. It's not given by EuroSys, but the request came all the way from the officers and even further up. So we are very happy that we are giving a special Community Service Award this year. This will be a one-time award that is given as for a special person. And the special person is Adrienne Collier, for the author of the morning paper. I am sure all of you who are working in systems community have read Adrienne's blog. He has been tirelessly working for last 7 or 8 years, writing blogs every morning. I don't know how he was able to get so much energy, waking up early and reviewing a paper and writing such a beautiful blog every day for 7 years or so. And EuroSys is very, very happy to award Adrienne this award. So Adrienne, do you want to say a few words for if you can, please.
Yeah, thank you, Provel. I mean, I'm very honoured to be receiving the award. It was most unexpected. I think most appropriately, I'd like to thank kind of all the researchers here who publish these wonderful papers, because without you, obviously, the morning paper could never have existed. And reading your papers has given me many, many hours of pleasure, joy, and even at times pure excitement. And over and above that, I think I'd also like to thank kind of all the PC members for their tireless work behind the scenes. As a kind of like a very interested external observer, sort of watching and following closely these communities, it always gave me and gives me a lot of confidence to know that sort of each paper at a conference such as EuroSys has been carefully vetted by sort of many experts before making it to the proceedings and before sort of like I started to kind of tackle it and try and understand it. And that really meant that I could stand on the shoulders of giants when I was kind of trying to trying to read and grasp with these papers. So I'd just like to thank you all, and I look forward to reading many more of your wonderful papers in the future. Thank you.
Thank you very much, Adrian, for accepting this award. And I would hand over to Professor Andy Tenenbaum for the next award, please.
Okay, am I on?
Yes, you are.
Okay, Ant, I hope you're out there somewhere in EuroSpace. You never know with this kind of virtual conference. But in any case, assuming you're there, it's a great pleasure to confer the EuroSys Lifetime Achievement Award on Ant Rostrom. You've been from Microsoft Research. You've been dedicated your entire professional life to systems research in Europe. Your research has been very impactful. Your papers have received over 34,000 citations. Many of them have been not only highly influential in the research community, but also contributed techniques that are now widely deployed in production systems. I'd like to highlight just a few of your contributions. Your seminal work on peer-to-peer systems and applications, including Pastry, Splitstream, Scribe, paved the way for a wave of innovation on building scalable, resilient, and efficient distributed systems. These techniques proposed in your peer-to-peer papers have been adopted across the industry. For example, they are at the core of several Microsoft cloud services. Your work on high-performance, cost-effective storage systems, such as Everest, Pelican, and PAST, are also highly influential. It redefined how modern cloud storage stacks are designed to achieve reliability and performance targets at reduced costs. You've made important contributions to networking, most notably on predictable data center networks. Finally, over the past few years, you bootstrapped a new research activity called Optics for the Cloud, which investigates optical storage, networking, and computation. This highly innovative work using femtosecond lasers to write information in blocks of glass. This can be very effectively used for archival storage because glass is extremely durable and lasts on the order of tens of thousands of years. Okay. This work is already in the process of being productized. You've been a great supporter of EuroSys and systems research in Europe. You've been a member of the EuroSys PC twice and of the PC chair once. You've taken many European PhD students as interns, and you've mentored many more. In summary, you're a role model for systems researchers in Europe. The breadth and quality of your research, the impact of your work, your support for young researchers in Europe, and it means that you fully deserve this Lifetime Achievement Award. I offer my heartiest congratulations to you, Ant.
Thank you very much. It means an awful lot to me to receive this award, and I want to thank the committee. I feel incredibly honored to have received this, and it was a complete surprise when I heard that I had won it. I'm incredibly proud of EuroSys. I'm incredibly proud of the fact that I've been able to spend most of my career, in fact, all of my working career in Europe doing systems research. I'd also like to really thank all the people I've been able to work with over the years. I've worked with an amazing set of people as interns, as collaborators, as colleagues at Microsoft, but also as professors or in other roles at universities. And I've learned so much from everyone that I've worked with. And I've been exceptionally lucky. And I'd just like to say thank you very much again. And yeah, thank you. It's just such a great honor. And I'm sort of basically speechless. So thank you very much.
Hey, thank you very much. Yeah, congratulations, and to all of the other prize winners. So next, we're going to hear about EuroSys Finance. So I think it's over to Adam.
We cannot hear you.
Oh, sorry. Somebody had to speak while muted. So hello, everyone. It's my pleasure to present the financial report of the EuroSys ACM chapter. Can we move to the next slide, please? So the EuroSys ACM chapter is a non-profit organization. It has a full membership that costs 40 euros a year, and students and members from Eastern Europe have a discounted rate of 10 euros. and every EuroSys member is entitled to a free membership in SIGOPS. As you can see on this slide, membership numbers are stable from last year, but we do have a bit of a decrease since 2019, mainly due to student memberships that lapse and students not upgrading to full members. So I encourage all of you who are interested in supporting system research in Europe and EuroSys, especially students, to join the EuroSys ACM chapter. Next slide, please. So the next order of business is the report on the financial status of the chapter. And in this chart, you can see the chapter's bank balance at the time of the conference over the past year. And as you can see, the chapter is in good financial state. We now have a little more than 100,000 euros in the bank. Next, please. And finally, this slide breaks down the financial status of the chapter over the years. The green bars show income of the chapter, which consists of the membership fees and any surplus from the conference. The red bars show expenses, which are mainly costs related to running a non-profit organization, which is a legal entity, as well as some costs related to the conference, such as travel grants and in some years and other expenses. And the orange circles are simply the income minus the expense each year. And we can see, for example, that in 2019, there was an increase in income because EuroSys 19 had a surplus. And next year, we'll see a similar increase. And that's basically it. Thank you very much.
Thank you, Adam. So now we're going to hear from Dushyant, who will ask people to step up and think about organizing future EuroSys conferences. Dushyant.
Thanks, Peter. Can you hear me?
Yes.
Great. I just have one slide, which is the next slide, if you could advance. First of all, let me say what a fantastic job the organizers have done, both this year, and I'd like to call out the organizers of last year's EuroSys. It is hard for us to switch from a community that values face-to-face interaction into one that's forced into an online forum. And given that constraint, I think the last EuroSys have been a great success. For EuroSys 2022, fingers crossed, we're very much hoping that we can go back to the format we all know and love, which is to bring everybody to a place in a beautiful European city that we explore, as well as meet everyone face to face, have those technical discussions in person that make EuroSys so valuable to many of us. So you'll be hearing soon about EuroSys 2022, so I'll not steal that thunder. But please, if you'd like to bring EuroSys to your city or region or country to showcase your geographic area, your department, please do reach out to any members of the steering committee, to the officers. You'll find out soon who our new officers are going to be, or indeed to one of us now on Slack. It's a great opportunity not only to help the community, but also to showcase your particular bit of Europe. So please do think seriously about EuroSys 2023 and onwards, whether you'd like to be a part of hosting it. Thank you.
Thanks, Dushyant. So now Tim Harris will introduce the new officers and the associated election.
Hi, thank you, Peter. I'm Tim Harris from Microsoft in Cambridge. Have the next slide, please. So, as we've heard, EuroSys has 4 elected officers, and these come up for re-election every 2 years, and officers can serve at most 2 terms. And it happens that this year, all of the elected officers have served the maximum time in those roles. And so we needed to identify a new set of officers to take on these positions. Looking back at my email on 5th of August last year, it doesn't quite seem so long ago. I was asked to run the elections this time around. I was one of the officers a few times ago, so I think the feeling must have been that I would not be wanting to serve a second stint. Kindly helped by Anne-Marie Kamrak, Lou Beschwerer, and John Wilkes in running the election. And the process we took is the same as we have for the last few officer elections. We publish an open call for self-nominations on the members list, and then the election committee solicits additional nominations to fill in any gaps to make sure we have at least one candidate for each of the positions. And in this case, we had exactly one candidate for each position. And so we just proceeded with a simple online form in lieu of having a kind of informal show of hands, as we sometimes have done at the conference business meeting. Next slide, please. Pleased to say we had a reasonably good turnout from the members, 40 votes from the 64 members. And for each of the positions, we asked members to support the nomination, and we had over 90% support in each case, I'm pleased to see. So the next slide, please. I'm happy to announce the incoming set of officers, therefore. Pascal Felber is the new chair for EuroSys. Evangelia Calvinaki is the vice chair. Kostas Magoutis is the secretary. And Dan Alistar is the treasurer. I'm sure I join with many people in saying I'm very happy to see EuroSys moving on in such capable hands. And of course, once again, to thank Peter and his team of current officers for such excellent work over the previous years. Thank you.
Thank you very much, Tim. So thanks for organizing the election. Congratulations to the new officers. It's great to see people in the community stepping up and continuing to serve EuroSys. And we as current officers, we will do a peaceful transition of power to the new officers. So the last thing that we're going to hear about is EuroSys next year. And as Dushan said, hopefully again as a physical conference. So can we hear from David about EuroSys 2022?
Hello, thank you. I'm gonna to share. I hope that you can see my screen and see me and hear me. Okay, so thank you very much. I would like to thank you, the steering committee, for giving me the opportunity and the huge responsibility to organize EuroSys 2022 next year in, so I'm gonna to say where. So as you already give some idea. So the big question is where and how. So as it has been said, we are very confident to do it and to going back to what we are used to do in traditional conferences. So we are very confident that it will not be virtual next year, but it will be a physical conference and face-to-face meeting, hopefully. The big question is where. So as you can guess from, I have an accent, and my accent potentially tell you where I come from. So I have a French accent. So yes, it will be in France. But now the next question is where in France? For those that already have attended to the last edition in France, it will be it was 6 years ago in Bordeaux. So this year it will not be in Bordeaux, but it will be in another city of France. So I will try to give you some idea. So it's close to Saint-Michel. I think that you may know Saint-Michel. It's a very nice place and very famous place. It is also close to Saint-Malo here. Saint-Malo is very well known as a city of coursers, and it's an historic port and one of the most touristic place in the region. And you can also find many feudal castle around. So I hope that you already guess where it is. We have also many pedestrian streets and places without COVID, of course, as you can see in the pictures. There are also some huge park and gardens. I'll try to increase your desire to come and to attend next year's. There are also in the city center many pedestrian streets with very old houses, which we call Maison à Colombage. So I didn't know how to say it in English, but I have looked, and it's usually said, I don't remember how to say it. You have also many beautiful buildings in the city center. So here, for instance, it's only the post office of the city. So as you can see, it's very typical and very nice. So one more time, we have also a Maison of Colombage. So yes, in English, it's half timbered houses, as far as I remember. So it's very typical of the city. It's typical of the city. You can also find a parliament. So it's quite rare because, in fact, Brittany was an autonomous region in France a long time ago. So you have it has its own parliament. We also have opera for those that want to go to some opera, and here also is the tunnel of the city. And one more time, many pedestrian streets with many bars and typical streets in the city center. And there are also many beautiful places, as I even don't know yet, so I don't know where it is, but it's in Rennes, and it's also very beautiful. So where it is, as you can guess, it's in Rennes. So where is Rennes? Rennes is in the west of France. So in Brittany, don't be confused with Great Brittany, which is just above. And so it's a very nice region, as you have seen. And so Rennes is it's very easy to access to Rennes. So for the period of the conference, Rennes will be at the center of Europe, but more seriously, Rennes is very close to Paris. It's just 1 hour and 25 by train. And of course, you can also join Rennes by plane. So it's only 1 hour flight from Paris. And of course, it's very well connected to the rest of Europe. You have also direct flight from different places in Europe. So it's very easy to access. And for those that are outside Europe, it's also easy to access from Paris, as it's very close to Paris in train and plane. So more precisely, the conference will take place in the city center of Rennes, in the Congress Center, which is located here. So it's very in the center of Rennes, so in the old part of the city that correspond to the pictures that I've just shown before. As you can see, it's very close to the train station. It's mostly 20 minutes by foot. And also here, this is really the center part of the city. The conference will take place more particularly in a convent that has existed since the 14th century. And it's very an interesting place because at this time they were already organizing conferences in Brittany. And so we will be also in that place. And don't be worried, even if it's very old, it's also very modern. It has been renovated a few years ago, at least 2 years ago. And we will have very beautiful auditorium, 400 seats, because we are expecting that you will come numerous next year, and you will all come to attend the conference. And we have all the facilities traditionally that we can encounter in this auditorium. The place is still modern. We have some modern part in the convent, even it's a very old place. And we will have many meeting rooms, of course, some workshop lunch, for instance. And also we also organize the gala dinner. I'm sure that you don't know anymore what it is about, but we will try our best to remember you. So we'll organize the World Conference at the same place. It's a huge place. It's a huge convent, in fact. Another pictures here about the convent. And of course, in Rennes, we also have some food specialties. As you know, food is very important in France, as well as wine. And so you will have the opportunity to try oysters, of course, but one of the most famous specialty in Brittany is, of course, galettes. So it's all about, it's a thing to try. So of course, in the city center, you will have many facilities to find an hotel, there is many kinds of hotel according to your budget. So you will find 5-star, 4-star, 3-star, 2 stars, and even 1 star a little bit farther from the city center. Yeah, so you will have many kinds of hotel around Rennes. So in order to be sure that everybody can attend and find its adequate place. So now let's talk about the organization team. So the team has a strong experience in system and ACM conferences. It's a subtle mix between senior members that you all know very well, and also junior and very promising researchers that are active in the EuroSys community. So we'll have Jim Muller that will act as a local chair, Julia Awal that acts as a publication chair, but also all the members that are very active in the community, such as Guillaume Pierre that will act as a financial chair, and also Sonia Ben Mokhtar that will act as publicity chair, and Laurent Réveillère that you potentially also know as we organized together in 6 years ago EuroSys in Bordeaux. So he will this time act as sponsor chair and also as wine chair. As you know, wine is very important. We will have also Alan Chana, which is a very promising researcher that will act as a sponsor chair, and also Yiming Kui from the University of Hong Kong that will act also as sponsor chair, Erwan Lemerer and Renaud Lachaise as workshop chairs, and finally François Tajani, that I'm sure you know also, that will act as a web chair. So this is the team. We still are searching a sponsor chair for the US. For the US. So if you have any suggestions, I'm open to hear you. And that's it. So I hope to all see you next year in Rennes physically in 2022.
Great, thank you very much, David. I mean, those photos look amazing. So thanks a lot for the invitation to Rennes next year. So this brings us to the end of the General Assembly. So thank you very much to all the speakers and everybody to keeping with the time limit, so we finished with time to spare. So one thing that I would like to do again is thank again our general chairs, Pramod and Antonio. I mean, they've done an amazing job. They've stayed on top of things so far. So incredibly well, and it is so much work to run a conference, to first organize a physical conference and then switch to virtual, as Dushyant was saying. So I think they're really fantastic. So let's give them a big hand. Okay, so my suggestion now is that we'll have any follow-on discussion on Slack in the general channel. So if there's any feedback that you have, either to the existing officers, to the incoming officers, to the steering committee, to the organizers for next year, I mean, so please share your comments, use Slack, give us feedback. And with that, let's close the General Assembly. Thank you very much. And let's enjoy the rest of the conference. Thanks.